Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me. If I'm perfectly audible and visible to every one of you. Let me know quickly in the chats, everyone. Welcome back people. Welcome back again to your Unacademy NEET English channel. So let me know quickly in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly in the chats, people. Everybody in the chats. Everybody in the chats. Welcome back. I think, yes, I am perfectly audible and visible to everyone. Yeah? So my dear students, as you all must be knowing, today we are going to cover one more important chapter of your chemistry, of your grade 12 particularly, which is your chemical kinetics. Yeah? So, today it's going to be the chemical kinetics chapter, which will be done and dusted. Okay? Well, the session duration is going to be like, I think, 8 to 9 hours. Okay? 8 to 9 hours, I'll be standing here in front of you, and I'm pretty much sure you guys are going to be with me till the end. Yeah? Are you ready for that? I would want to know first of all in the chats. Are you ready to be with me till the end? See, this particular chapter, like all the chapters which we completed here on this particular channel, again, this particular chapter will be started from the basics, from the scratch. Whether you have studied the chapter before or not, does not matter. All the things, all the theory, all the problem patterns which can be asked from the chapter chemical kinetics will be done and dusted in this particular session itself. Okay? So let me know first of all in the chats. Guys, I want the chats to run fast. Okay? I want you guys to be active in the chats completely. Okay? So let me know quickly in the chats if you guys are ready to be with me till the end. Yeah, let me know quickly in the chats with some fire emojis. Everybody. Everybody. Yes, in between, I'll be giving you certain breaks as well. In between, I'll be giving you certain breaks as well. You don't worry about that. But make sure you guys be with me till the end. Yeah, I know I'm live after so long. After, I think, almost 10 days. Yeah, I'm here in front of you. Perfect. Now let's get back to the business again, the way we used to. Perfect. Okay, one question. Have you studied this chapter before? Yes or no? Yes or no in the chats. That's it. Have you studied this chapter before? Yes or no in the chats. Everybody. Everybody in the chats. Have you studied this particular chapter before? Yes, Kiran, it's okay. It's okay. If you have not studied equilibrium, if you have not studied thermodynamics, and you want to study this chapter, you can do that. You can directly start with this chapter. Okay, you don't worry about that. All right, I can see majority of the students have not studied this particular chapter. That's okay, completely fine. No need to worry. It is just one thing I'm expecting from you. Whatever things I'll be mentioning on the screen, I would want you guys to take a note of every single thing. Anyways, I'll be sharing the handwritten session PDF as well. Handwritten PDF of this particular chapter I'll be sharing in my Telegram. I hope you guys are already the part of it. If you are not the part of my Telegram, just join the Telegram channel, Wassim Bhat Chemistry Official, right? In which I keep on sharing the handwritten PDFs of all the chapters which we complete here on this particular channel. And apart from that, I'll be sharing the DPP of this particular chapter as well. Once we complete this chapter today, right, at the end, I'll be sharing the DPP of this particular chapter which you will be doing on priority tomorrow itself, right? And that DPP will be shared on the Telegram, Wassim Bhat Chemistry Official. Okay? And one thing I'm promising you, if you guys are following this particular lecture completely till the end, you will be in a position to solve each and every question from the chapter Chemical Kinetics. Okay? Don't worry about anything. Just follow the chapter till the end, watch the lecture completely with me live, and I'm assuring you one thing, all the types of the questions which can be framed from the chapter Kinetics when it comes to your NEET examination or even JEE Mains examination, you should be in a position to solve each and every question. That's my promise to you. Okay? So should we start already? Should we start, people? Should we start? Should we start? And by the way, there were a lot of students among you who wanted me to teach in English, right? That means Hindi. So on 4th of November, we are starting one batch for NEET 2025 students, right? And this is the set of the teachers who are going to train you in this particular batch. But remember, this batch is in English language, okay? It is the Phoenix All-Star Fast Track batch for all the NEET UG 2025 students, wherein me, Anushka ma'am, Anmol sir, Seep ma'am, Akansha ma'am, Pratik Jain sir, and Anubhav sir, we are going to train you particularly in physics, chemistry, and biology, in which we have scheduled 450 plus live lectures, right? 15 plus tests will be there, and the batch is going to be in English language. Okay, and this is a paid batch, by the way, and the cost of this particular batch right now is 2,999. So all those students who wanted to be the part of my English batch, this is the batch for you. Okay, the link to enroll into this particular batch is in the description box of the video. You can go to the description box of the video, click on the link, and eventually you'll enroll yourself into this Phoenix All-Star Fast Track NEET 2025 batch. Okay, for all those who wanted to be the part of my English batch. Perfect. Should we start, people? Should we start? Should we start? Should we start? So quickly, let me give you the overview of the chapter first. Let me exactly tell you what is going to be the sequence of this particular chapter. What all topics we are going to cover first and later on. Okay, let me give you exactly the sequence of the topics which we shall be covering in the today's session. Perfect. Have a look, guys. First of all, we will be starting with something called as average rate of reaction. That is going to be the first topic of the today's discussion. Average rate of reaction. After average rate of reaction, we shall be discussing about instantaneous rate of reaction. We shall be discussing about instantaneous rate of reaction. Once we are done with instantaneous rate of reaction, we shall be discussing about the graphs which are related to average rate and instantaneous rate. Once we are done with the graphs, then we shall be discussing about the rate of reaction as per stoichiometry. Rate of reaction as per stoichiometry. Please take a note of all these points. I mean, all these topics. This is going to be the sequence of the topics which we are going to cover in the today's session. Okay. So, rate of reaction as per stoichiometry, which includes your rate of disappearance, appearance, etc., and all the questions related to it. Right after that, we shall be discussing about the law of mass action. And once we are done with law of mass action, we shall be directly jumping into the rate law. And from the rate law, after the rate law, we shall be discussing about the types of the reactions. Once we are done with the types of reactions, then there comes one more terminology, that is molecularity. Molecularity of the reaction. And after molecularity of the reaction, we shall be discussing about the order of the reaction. Once we are done with the order of the reaction, then we shall be discussing about relation between different rate constants. Relation between different rate constants. Then comes your units of rate constant. Units of rate constant. Okay. Then comes your significance of order. Significance of order. And after that, we'll jump into the experimental determination of order. Experimental determination of order. Once we are done with the experimental determination of order, then we shall be moving into the zero order kinetics. Zero order kinetics. After zero order kinetics and its different parameters, we shall be discussing about the first order kinetics. After doing the first order, we shall be discussing about the gaseous first order reactions. The gaseous first order reactions. Once we are done with the gaseous first order reactions, then we shall be discussing about the parallel first order reactions. Parallel first order reactions. After the parallel first order reactions, we shall be discussing about calculation of order from half-life. Calculation of order from half-life. Calculation of order from half-life. And after this calculation of order from half-life, I shall be discussing Arrhenius equation with you. Arrhenius equation, which is what you call as temperature dependence of rate. And right after that, I shall be discussing about the effect of catalyst. Effect of catalyst on the rate of the reaction. Right after that, we shall be discussing about a theory which all of you must have heard once, that is your collision theory. Once we are done with the collision theory, we shall be discussing about the factors affecting rate. Factors affecting rate. Okay? So basically these two terms will come into the factors affecting rate only. And after that, once we are done with factors affecting rate, we shall be discussing about the mechanism of the reaction and different types of questions framed from this particular topic. So this is going to be the sequence, this is going to be the flow of the topics which we shall be covering in the today's session. Okay, and with this, we will be done with one more chapter of physical chemistry, that is your chemical kinetics. Perfect. And my dear students, at the same time, in the today's session, I've added a lot of new questions. Okay, there were some topics which I did not teach you in the earlier marathons of chemical kinetics. In the today's session, all the topics which I have not taught before on YouTube, all those topics also I'll be covering in the today's session. Okay? Perfect? Perfect, people. So should we start? Should we start? Quick in the chats. I hope you got to know the session flow exactly what we are going to do. So without wasting any sort of further time, let's get going now. Okay? Let's get going and let's get started with the chapter. Let's get going. Let's get started with the chapter now. Okay? Now, so first of all, what is chemical kinetics all about? If you ask me this as the first question, what is chemical kinetics in general? How do we define the chemical kinetics? My dear students, let me tell you, this chemical kinetics, it is basically the branch of chemistry that deals with the rate of reaction, number one. It is the branch of chemistry that deals with the rate of reaction, factors affecting the rate of reaction, factors affecting the rate of reaction, and the mechanisms involved in a chemical reaction. So first of all, in this particular chapter in chemical kinetics, what are we going to discuss basically? We are going to discuss about a term that is what you call as rate of reaction. We are going to discuss about what all factors are there which are going to govern the rate of the reaction. And we shall be discussing about the mechanisms which are involved in the chemical reaction. So all these things, they come under the heading chemical kinetics. Okay. Now, before starting this particular chemical kinetics, there are some basic things which are required. Some basic things. What are those basic things which are required to start this chapter? What are those basic points which you should know first of all? Let me note down all those basic points first of all. And I believe these points already you would be knowing. If not, then have a look right now. The first point which I'm mentioning over here, my dear students, I'll write a statement. The statement is like this. As the chemical reaction proceeds, concentration of reactants. As the chemical reaction proceeds, concentration of reactants decreases with time, and the concentration of products increases with time. Increases with time. As the chemical reaction proceeds, concentration of reactants decreases with time, and the concentration of products that increase with time. Let's understand the meaning of this particular statement first of all. Have a look, guys. For example, imagine that I've got a chemical reaction A gives B, where A is the reactant, B is the product. Where A is the reactant, B is the product. Now, my dear students, first of all, imagine that this reaction is taking place in a container. Imagine that this particular chemical reaction, it is taking place in a container. I'm assuming volume of this particular container is V liters. Volume of this particular container in which this reaction is taking place. I'm assuming volume of the vessel, volume of the reaction vessel is how much? That is V liters. Now, my dear students, if I define a term, concentration, which is represented by square brackets, concentration. What is concentration exactly all about? How do we define the term concentration? Concentration is nothing but moles per unit volume in liters. For example, if I want to define the concentration of reactants, concentration of reactant will be simply number of moles of reactant divided by volume of reaction vessel in liters. Similarly, concentration of product, that is nothing but moles of products divided by volume of the reaction vessel in liters. So first thing, concentration is defined as moles per unit volume. Concentration of reactant means moles of reactant divided by volume of the vessel in liters. Concentration of product means moles of product divided by volume of the vessel in liters. As simple as that. Now, my dear students, remember one simple thing. If I write time t is equal to 0, time t is equal to 0 means that the reaction has not started yet. Time t is equal to 0 means that the reaction has not started yet. If the reaction has not started yet, that means the reactant has not got converted into product yet. That means the reactant has not got converted into product yet. So can I say, initially at time t is equal to 0, I'll be only having reactant in the container. Initially at time t is equal to 0, I'll be only having a reactant in the container. There will be no product initially in the container because the reaction has not started yet. There will be only moles of reactant present in the container at time t is equal to 0. Yes, because the reaction has not started yet. A has not got converted into B yet. So in the container at time t is equal to 0, you will only find A in the container. There will be no B in the container at time t is equal to 0. Right? Now, my dear students, as the reaction starts, as this A start getting converted into B, as this A start getting converted into B, what is going to happen with time? I would say number of moles of reactants in the container will decrease with time, and the number of moles of products in the container will increase with time, right? As the reaction proceeds, as A starts getting converted into B, the number of moles of A are going to decrease with time. The number of moles of B are going to increase with time. Yeah? Now, people, if the moles of reactants are decreasing with time, can I say concentration of reactant will be decreasing with time as well? Because both are directly proportional. Similarly, as the moles of product are going to increase with time, I would say concentration of product is going to be increasing with time as well. Right? So as the reaction proceeds, moles of reactants decrease with time, and eventually concentration of reactants also decrease with time. Moles of product increase with time, therefore concentration of product also increases with time. That is the statement which I mentioned over here. As the reaction proceeds, concentration of reactant decreases with time, concentration of product that increases with time. Correct? Correct, people? I believe this is clear. If this is clear, then we can simply plot two basic graphs over here. We can simply plot two basic graphs over here. The first graph is going to be between concentration versus time. Concentration versus time. For the reactants. For the reactants. For the reactants. Tell me one thing. At this particular point, can I say this particular point represents T is equal to 0? And at T is equal to 0, concentration of reactant is maximum. With time, concentration of reactant decreases. With time, concentration of reactant decreases. So the graph over here is simply going to be like this. And I would say this particular graph is valid for what? It is valid for reactants. Because we know with time, concentration of reactant decreases. Yes. Similarly, if you want to plot a graph, if you want to plot the same graph for the products, the graph is between concentration versus time. Now you are going to tell me at time t is equal to 0. At time t is equal to 0, initially, moles of product in the container will be 0. If moles of product are 0 at time t is equal to 0, therefore concentration of product will be 0 initially, right? Because concentration is moles per unit volume. If moles of product initially are 0, therefore concentration of product initially will be 0. Now, my dear students, you know, as the reaction proceeds, with time, moles of product increases, and eventually concentration of product also increases. So this particular graph, it is valid for what? It is valid for product. So these are the first two graphs which I would want every one of you to remember from now onwards. So from now onwards, when I say with time, what happens to concentration of reactant? Your answer should be with time, concentration of reactant decreases. With time, concentration of product increases. As simple as that. Yes? If this particular point is clear, then I'm going to move on to our first topic. What is that? That is going to be your average rate of reaction. Average rate of the reaction, which I'm going to represent with RAV. So, my dear students, what is this average rate of reaction exactly all about? Let's get to know. See, guys, average rate of reaction, which I'm representing with RAV, it is defined as change in the active mass, basically. But I'm not using the term active mass here. Let me directly use the term concentration here, so that we can understand all these things quickly. I'm writing change in the concentration of either reactant or product. Average rate of reaction is defined as change in the concentration of either reactant or product in a given interval of time. in a given interval of time. Change in the concentration of either reactant or product in the given interval of time. So RAV, I can write it like this. I can write it, change in the concentration of either reactant or product divided by time interval. What does it mean? You'll get the idea in some time. And one thing I'm adding over here, I'm adding plus and minus here. Why did I add this plus minus here? You'll also understand this in some time. Have a look what it means now. Have a look what it means now. So first thing, average rate of a reaction. Average rate of a reaction, it is defined as change in the concentration of either reactant or product in a given interval of time. What does it mean? Have a look, people. Understand properly. For example, imagine that I've got a reaction. A gives B. This is the reaction. A gives B. Okay? A gives B. Let's say I'm writing a term T1 here. Let's say at some time T1. Let's say I'm analyzing this particular reaction at some time T1, which can be 5 seconds, 20 seconds, 50 seconds, whatever. Let's say I'm analyzing this particular reaction at some time T1. And after analyzing this reaction, for example, I got to know that concentration of reactant at time T1 is C1. For example, at time T1, which can be 5 seconds, 10 seconds, 20 seconds, right? Let's say the concentration of product is C3, for example. Similarly, I'm choosing one more time T2. I'm choosing one more time T2. I'm choosing one more time T2. Okay? Let's say at time T2, I'm again analyzing the same reaction. And I got to know at time T2, the concentration of reactant, for example, is C2. And concentration of product here is, for example, C4. Okay? I've got the reaction with me. A gives B, which is taking place in some container. I chose a time T1. At time T1, I analyzed this particular reaction. And I got to know at time T1, the concentration of reactant is C1. At time T2, the concentration of reactant is C2. At time T1, the concentration of product is, for example, C3. The concentration of product at time T2 is, for example, C4. Okay? So first of all, understand one thing. Which time interval did I choose over here? My dear students, I'm choosing this particular time interval. From T1 to T2. From T1 to T2. And this time interval, T1 to T2, I'm representing with delta T. And delta T will be nothing. It will be T2 minus T1. This is the time interval which I'm choosing over here. This is the time interval which I'm choosing over here. And my dear students, in this time interval, T2 minus T1, do you see concentration of reactant is changing as well as concentration of product is changing? As you can see properly, in this time interval, concentration of reactant is also changing, concentration of product is also changing. And how exactly they are changing? If you look carefully, I will simply say one thing. T2, I'll simply say one thing. T2 will be less than that of C1. Do you agree with that? C2 will be less than that of C1. Right? Because you know, as the reaction proceeds, concentration of reactant decreases with time. Concentration of reactant decreases with time. Similarly, concentration of product that increases with time. So I can say C4 will be greater than C3. C4 will be greater than C3. Now, my dear students, the time interval that I have chosen over here. For example, I want to calculate average rate of reaction. For example, I want to calculate average rate of reaction in this time interval. For example, I want to calculate average rate of reaction in this interval. My dear students, you can calculate average rate of reaction either with respect to reactant or you can calculate average rate of reaction with respect to product. Now, if I am calculating average rate of reaction with respect to reactant, what I'll be doing? Look at the definition. Change in the concentration of either reactant or product in a given interval of time. This is my given interval of time. This is my interval of time, right? And I want to calculate average rate of reaction with respect to reactant in this interval. So what I'll be doing? I'll be writing change in the concentration of reactant in the time interval delta T, right? Change in the concentration of reactant in the time interval delta T. Now people tell me one thing. Tell me one thing. What is the change in the concentration of reactant? The concentration of reactant is changing from C1 to C2. So, change in the concentration of reactant will be final concentration of reactant minus the initial concentration of reactant divided by time interval is simply T2 minus T1. One more thing, people. One more thing. I already told you C2 is less than C1. If C2 is less than C1, that means C2 minus C1 will come out to be negative. It will come out to be negative. But if I ask you, have you ever seen rate coming out to be negative? Have you ever seen rate coming out to be negative? What is rate? The speed with which the reaction takes place, right? Rate can never be negative. But over here, it's coming out to be negative. But we know rate can never be negative. So, what I'll be doing, here only I'll be multiplying with the minus sign so that this minus and this minus makes the overall term as positive. Do you understand why I use minus over here? Because if I'm not using minus over here, then rate is coming out to be negative. But rate negative does not have any significance. Okay? So that is the reason why I introduced minus sign in the beginning. So that this minus and the minus coming out to be from here, that will make it at the end as positive. Perfect? Now similarly, my dear students, if you want to calculate average rate of reaction with respect to products, in the same time interval, what you will be doing? You will be writing change in the concentration of product divided by time interval delta T. Perfect. What is the change in the concentration of product? Well, the concentration of product is changing from C3 to C4. So final is C4 minus initial is C3 divided by time interval, that is T2 minus T1. And already I know C4 is greater than C3. If C4 is greater than C3, I would say the value will come out to be positive only. So here you do not have to multiply with minus sign. You can keep plus in the beginning. Right? Perfect. My dear students, whether you want to calculate rate of reaction with respect to reactants or you want to calculate rate of reaction with respect to products, in the same time interval, the rate of the reaction coming out to be from reactants and rate of reaction coming out to be from products, that will be the same in the same time interval. Am I clear with this? Am I clear with this, people? Quick. Am I clear with this? Everybody? Yeah? Perfect? Perfect, people? Now, you can do one more thing. You can just express all this stuff graphically too. And how exactly? Have a look. For example, I'm plotting a graph here. The graph is between concentration versus time. Let's say I'm making the graph for reactants. And you know, with time, concentration of reactant decreases. Let's say here I'm choosing time T1 and here I'm choosing time T2. Now, my dear students, at time T1, what is the concentration of reactant? At time T1, the concentration of reactant was C1. At time T2, what is the concentration of reactant? At time T2, the concentration of reactant is C2. Yeah? Now, do you see one thing? C2 is less than C1. Correct? For example, I want you guys to calculate the average rate of the reaction in this time interval. First of all, this time interval is going to be represented by delta T, which is equal to nothing but T2 minus T1. This is the time interval which I'm talking about. So I want to calculate the rate of the reaction in this time interval. Perfect. Now, how would I be doing it? I'll write average rate of reaction with respect to reactant will be equal to change in the concentration of reactant. Change in the concentration of reactant, which will be final concentration of reactant minus initial. So it is simply going to be C2 minus C1 time interval T2 minus T1. Now we already know C2 is less than C1. If C2 is less than C1, the value comes out being negative, but rate cannot be negative. So over here, I'll have to multiply with the sign minus so that eventually it comes out be positive. Yes, I believe this is clear. I believe this is clear. Perfect, guys. Similarly, my dear students, if I want to plot one more graph like this, between concentration versus time, and this graph which I'm going to plot, I'm plotting it for the products. And here I'm choosing time T1, here I'm choosing time T2. And you know, at time T1, what was the concentration of product? At time T1, the concentration of product was C3. So this is your C3. And similarly, at time T2, the concentration of product was C4. Now you can see C4 is greater than C3. C4 is greater than C3. Now, my dear students, for example, I want to calculate rate of the reaction in this time interval, which I'm representing with delta T, which is nothing but T2 minus T1. So I can simply say average rate of reaction with respect to product will be equal to change in the concentration of product, which will be final concentration of product, which is C4, minus initial concentration of product, which is C3, divided by time interval T2 minus T1. Now already we know C4 is greater than C3. If C4 is greater than C3, the overall value comes out be positive only. So here you're not supposed to multiply with minus, you'll be multiplying with plus sign only. Okay? Perfect. Perfect, guys. I believe it is clear to every one of you. Now. Ideal students, take a note of one more thing. The minus sign with which I'm multiplying over here and the plus sign with which I'm multiplying here. First of all, I'm multiplying with minus in terms of reactants. I'm multiplying with plus in case of products. Now, this minus and plus has got the significance as well. One of its significance, you got to know. One of its significance, you got to know. One more. The negative sign indicates that the negative sign with which I'm multiplying over here. This indicates that concentration of reactant decreases with time. And similarly, the plus sign with which I'm multiplying here, it represents that the concentration of products increases with time. So take a note of these two things as well. So let me know once in the chats if all the things are crystal clear till here or not. Quickly. Quickly, people. Everybody in the chats. Perfect. Chemical equilibrium is completed long back. You can go to the live section. Chemical equilibrium we have completed. Okay, guys. So I hope you got the significance of minus and plus. Minus sign indicates that the concentration of reactant decreases with time. Plus sign indicates that concentration of products increase with time. And I hope you got to know why we multiply with minus sign and plus sign. In short, I hope you got to know why we are introducing this plus and minus over here. Okay? I hope this is clear. Yeah? Perfect. Now, let's move on, guys. Let's move on. There is a term called as instantaneous rate of reaction. Instantaneous rate. How do I exactly define the term instantaneous rate? Let me first of all write its definition. Instantaneous rate is defined as the rate of reaction at a particular instant of time. Rate of reaction at a particular instant, or you can write it like this. It is defined as change in the concentration of either reactant or product in a very, very short interval of time. In a very, very short interval of time. Let's get to know what it means. My dear students, I believe in physics, you would have studied average speed and instantaneous speed, right? I hope you know that. In physics, how do you represent average speed? Average speed is represented like this, delta x divided by delta t. Or average velocity, you represent at delta x divided by delta t. And my dear students, if you want to convert this average velocity into instantaneous velocity, what do? You use limit. You use limit and approach this delta t towards 0, right? So what exactly you are going to do in order to convert average velocity into instantaneous velocity? You are going to make the time interval very, very, very small. Very, very, very small time interval. See, it's simple. Here you can see this was the time interval. The time interval was bigger. It was a big time interval. Perfect. Now, here you were defining the average rate of reaction. If you are going to make this time interval very, 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 very small, as if you are going to make this time interval very small. So on the line, it should be represented like a point on this particular time axis. It should be represented like a point. But you should know that it's not a point. It's a very, very, very small time interval. Did you get this? Yeah? So, what I'm trying to say is, in order to convert average velocity into instantaneous, you're going to make the time interval very small. And in that very small time interval, wherein delta t approaches towards 0, whatever is going to be the rate of the reaction, that is something which you call as the instantaneous rate of the that's something which you call as instantaneous velocity here, which is represented by dx by dt. This is how you are going to represent all this stuff in physics. Now here again, the concept is same. Here again, the concept is same, guys. The concept is same. Have a look. Delta C upon delta T. It represents average rate of reaction, wherein the time interval is slightly bigger, right? Now I'm going to use the limit in which I am approaching this delta T towards 0. Time interval I'm making very small. This is something which I'll be now calling as instantaneous rate of reaction. How do I represent it? This is something which I'm going to represent with dc upon dt. This is something which I'm going to represent with dc upon dt, right? And my dear students, what is meant by dc upon dt? What is meant by dy upon dx? In physics, you write dy upon dx. What is that dy upon dx? That is the slope of tangent at a point on y versus x curve. Here, what is meant by this dc upon dt? Graphically, it represents the slope of the tangent at a point on concentration versus time curve. On concentration versus time curve. And you must be knowing, slope of the tangent is also calculated with the help of this tan of theta. But here, I would be mentioning plus minus tan theta. Why plus minus? You should be in a position to answer this now. Have a look. Let's make it a little more clear. See, guys. For example, here I'm plotting a graph. The graph is between concentration versus time. This is the graph, concentration versus time. For example, I'm making the graph like this. First thing, it's understood that this is the graph for the product. Now, my dear students, imagine I'm selecting a very, very, very short interval of time. This small interval of time I'm selecting. Very, very small interval of time, wherein delta t approaches towards 0. This very, very small time interval of time. in this very small interval of time. For example, I want to calculate rate. So which rate it's going to be? It's going to be instantaneous rate. It's going to be instantaneous rate. So what I'll be doing? What I'll be doing? My dear students, I'll be drawing a tangent at this particular point. After drawing the tangent at this particular point, I will be measuring this particular angle. I'll be measuring this particular angle. Let's say this angle is theta here. Okay. The angle which the tangent makes with the positive x-axis in the anti-clockwise direction. That is theta. The angle which the tangent makes with the positive x-axis in the anti-clockwise direction. That is theta. If I calculate this theta, after calculating this theta, I'll just take tan of theta. Well, this tan of theta here is going to give me the instantaneous rate of reaction. This tan of theta here is going to give me the instantaneous rate of reaction. This tan of theta is going to give me the slope of the tangent at a point on concentration versus time curve. Yes, simple. And you would be seeing the theta comes out to be acute here. If theta is acute, that means tan of theta will eventually come out to be positive only, right? If theta is acute, that means theta, it's in first quadrant, and all trigonometric functions in the first quadrant are positive. So tan of theta will come out to be positive here. Tan of theta will come out to be positive here. So you need not to multiply with minus here. You are going to keep plus in the beginning only. Okay. Now similarly, if I want to make one more graph between concentration versus time, and imagine the graph is like this. So this graph is valid for what? This graph is valid for the reactant. Now similarly, at this particular point, for example, I'm drawing the tangent. Let's say this is the tangent. After drawing the tangent, I'll be calculating this angle, which the tangent makes with the positive x-axis in the anti-clockwise direction. I'm calling this as theta. Well, after calculating this theta, I'm going to calculate tan of this theta. Well, this theta is obtuse here. If theta is obtuse, tan of theta will come out to be negative. Tan of theta will come out to be negative. What is tan theta? Tan theta is instantaneous rate. So instantaneous rate here is coming out to be negative. That's not possible. Perfect. So what I'll be doing? I'll be multiplying with minus sign here only, so that eventually it comes out to be positive. So I hope you got to know what is the significance of this plus and minus here. Am I clear with this? Say it in the chats quickly, everybody. Say it in the chats quickly, everyone, if this is super clear. Yeah? So what is the difference between average rate and instantaneous rate? When we define instantaneous rate, the time interval delta t, that's taken very small, delta t approaching towards 0. Yeah? And when we talk about the average rate, there, time interval is not taken that much small. Okay? All clear with this? All clear with this, people? Quick, in the chats. Perfect. This was all the basics. This was all the basics of your average rate and instantaneous rate. Now, let's move on to one more point. What is that? That is the rate of reaction. Rate of reaction as per stoichiometry. Rate of reaction as per the stoichiometry. See guys. For example, imagine that you have got a balanced chemical equation like this. N1A plus N2B, it gives N3C plus N4D. Imagine this is one balanced chemical equation wherein N1, N2, N3, N4. Imagine these are the stoichiometric coefficients of reactants and products. Imagine that I've got a balanced chemical equation in which N1, N2, N3, N4. N1, N2, N3, N4. They represent the stoichiometric coefficients of reactants and products. Now, my dear students, here I'm defining some terms. See, one thing which you already know. Reactants, they disappear with time. Since I told you already, reactants, they get consumed with time, right? That's something which we have discussed. So I would say, in short, reactants disappear with time. They get consumed with time. They get consumed with time. But if I talk about products, products get formed with time. Products get formed with time. Right, people? So here I'm going to define two terminologies. Two terminologies I'm going to define here. One is going to be rate of disappearance. One is going to be rate of disappearance. And this rate of disappearance, I will be defining for reactant. Rate of disappearance, I'll be defining for reactant. Because we know reactants, they disappear with time. They get consumed with time. Yeah? They get consumed with time. Perfect? Right, people? So, rate of disappearance, I'll be defining for reactants. Let's say I'm choosing this reactant A. So, how do I mention rate of disappearance of A? How do I represent the rate of disappearance of A? Rate of disappearance of A. With what rate A disappears? With what rate A disappears? Okay? With what rate A disappears? How do I represent it? I'll be starting with a minus sign. Because this A is a reactant that disappears with time. And this minus represents that. It represents that A is disappearing with time. Now, with minus, I'll be writing change in the concentration of A divided by time interval. This is how I'm going to represent the rate of disappearance of A. This is how I'm going to represent rate of disappearance of A. Similarly, if I want to represent rate of disappearance of B, can I do that? Absolutely we can. Rate of disappearance of B. B is again the reactant. B is again the reactant. So again I'll be starting with minus sign. Change in the concentration of B divided by time interval delta T. This is how I'm going to represent rate of disappearance of B. This minus sign represents disappearance. This minus sign tells you that B disappears with time. Okay. Similarly, my dear students, I want to define one more term. That is the rate of appearance. Rate of appearance, or I can say rate of formation. Of what? Rate of formation of C. C is the product. C is the product which gets formed with time. Which gets formed with time. So I'll be starting with plus sign. Change in the concentration of C divided by time interval delta T. Right? This is something, this particular term I'll be calling as the rate of appearance of C. Rate of appearance of C. Yeah? Right, people? Similarly, my dear students, I can say rate of appearance. Rate of appearance of D or rate of formation of D. How do we represent it? Now you should be in a position to do it. It's plus change in the concentration of D divided by time interval. So my dear students, remember these terms. What is rate of appearance and what is rate of disappearance? How do we represent them? You have to remember this because entire chapter is going to revolve around all these stuff. Okay? Right? Right, people? Perfect. Yeah? I believe this particular stuff is clear. So remember one thing. Whenever you'll have to write rate of disappearance, you'll start with minus sign. Whenever you'll have to write rate of appearance, you'll start with plus sign. Okay? All clear? All clear, guys? If this is clear, then I'm going to define one more term. I am going to define one more term. What is that? I will be defining rate of the reaction. I will be defining a rate of the reaction. These were the rate of disappearances and appearances of reactants and products. Right now I was talking in terms of reactants, products. Right? Now I'm talking about rate of reaction. Now my system is basically changing. Initially my system was reactant and product. Initially my system was reactant and product. I was checking with what rate reactant is being consumed, with what rate product is being formed. Now I'm changing the system. I'm calling the system as the reaction. Now I'm going to define the rate of the reaction. How do we get the rate of reaction? Rate of reaction is calculated. Like what? It is calculated like this. Rate of disappearance or appearance of a reactant, rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient of that particular reactant or product. My dear students, just look at one thing. When I was defining rate of disappearance and rate of appearance, I never divided with stoichiometric coefficient. I never divided or multiplied with stoichiometric coefficient. But now, when I'll be defining rate of reaction I can define either with respect to A, or with respect to B, or with respect to C, or with respect to D. I can define rate of reaction with respect to A, with respect to B, with respect to D, with respect to C. And when we define rate of reaction, how do we do it? Rate of disappearance or appearance of a reactant or product is divided with the stoichiometric coefficient. What does that mean? Have a look. Have a look, people. Have a look. Let's say I'm taking the balanced chemical equation like this. N1A plus N2B, it gives N3C plus N4D. It's a balanced chemical equation. Imagine that I want to calculate rate of reaction with respect to A. I want to calculate rate of reaction with respect to A. How will I be writing it? Since A is the reactant, so I'll be writing rate of disappearance of A. I'll be writing rate of disappearance of A first. Rate of disappearance of A divided by stoichiometric coefficient of A. What is the stoichiometric coefficient of A? That's N1. So this is how you are going to write it. Minus 1 by N1, change in the concentration of A divided by time interval. This particular term is going to give you the rate of the reaction in terms of A. This particular term is going to give you the rate of the reaction in terms of A. Similarly, you can calculate the same rate of reaction in terms of B as well. B is again the reactant. So again, you'll be starting with minus sign. 1 divided by stoichiometric coefficient now is not N1, now it's N2. Here you are going to write change in the concentration of B divided by time interval delta T. This particular term also is going to give you the rate of the reaction. The rate of the reaction in terms of what? In terms of B in the same time interval delta T. Okay. Similarly, my dear students, you can calculate rate of reaction with respect to C as well. C is the product. So I'll be starting with plus sign. Because as per the formula, rate of reaction is rate of disappearance or appearance. Now I'm calculating rate of reaction with respect to C. So I'll have to use the term rate of appearance of C. So I'll be using the term plus 1 by stoichiometric coefficient here is N3, change in the concentration of C divided by time interval delta T. Similarly, in terms of D, it's going to be plus 1 divided by N4, change in the concentration of D divided by time interval delta T. My dear students, all these terms which I have kept in boxes, all these terms are going to give you what? Rate of reaction. Whether you want to calculate rate of reaction by solving this term, or you want to calculate rate of same reaction by solving this term, or you want to calculate rate of reaction by solving this term, or you want to calculate rate of reaction by solving this term, you will be getting the rate of reaction same by solving all these terms, because everywhere you are choosing the same time interval delta T. Okay? Rate of reaction at a particular temperature, that's always fixed, that's always constant. Whether you want to calculate that rate of reaction with respect to A, then you have to solve this term. With respect to B, solve this term. With respect to C, with respect to D. Right? Am I clear with this? Am I clear with this? Yeah? Perfect. And my dear students, this particular equation which you got over here, this is something I'll be calling as differential form of rate. This is something I'll be calling as differential form of rate. differential form of rate. You know, 2 years back, one of the question was asked in your NEET examination, and see how basic the question was. You were given with the reaction N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. This was the reaction that was given. And you were supposed to write the differential form of rate for this reaction. I think you should be in a position to do that. You should be killing this, right? So you would be writing like this. Rate of the reaction is equal to, with respect to N2. N2 is the reactant. So start with minus 1 divided by, stoichiometric coefficient is 1. Change in the concentration of N2 divided by time interval delta T. Or you can calculate rate of reaction with respect to H2. Start with minus sign. 1 by, stoichiometric coefficient is 3. Change in the concentration of H2 divided by time interval delta T. Or you can calculate rate of reaction with respect to NH3. So start with plus 1 by, stoichiometric coefficient is 2. Change in the concentration of NH3 divided by delta T. And this was the answer of the question. This was the answer of the question. Do you see this? Do you see this, people? The reaction was given in this format, and you were supposed to just write its differential form of rate. And that's how you write the differential form of rate. I believe it's clear. I believe it's clear to everyone. And if it is clear to everyone, then let me write one more clear-cut statement over here. Statement is like this. For a homogeneous gaseous phase reaction, carried out at constant temperature, rate can be expressed in terms of pressure as well. Rate can be expressed in terms of pressure as well. What does that mean? Let's have a look what it means. Hey guys, imagine that my reaction is like this. N1A gas plus N2B gas. Let's say it gives N3C gas plus N4D gas. Imagine this one balanced chemical equation. My dear students, first thing, all the reactants products are in gaseous phase. All the reactants products have got same phase. So it is the example of the homogeneous reaction. And since all the reactants products are in gaseous phase, so I must say this is one homogeneous gaseous phase reaction, which is carried out at some temperature T. It is carried out at some temperature. Now guys, have you heard about this particular equation? PV is equal to nRT. Yes, you would have, right? Have you heard about this particular equation? P is equal to N by VRT. N by VRT, nothing else. N by VRT, right? Okay. What is this N by V called? N by V is called as concentration. R and T. So my dear students, my point is for gases, we define concentration as well as we define pressure. For gases, we define concentration as well as pressure. And for a homogeneous gaseous phase reaction, you can calculate rate either in terms of concentration or in terms of pressure. You can calculate rate either in terms of concentration or in terms of pressure. Because for gases, concentration as well as pressure, both the things are defined. Now understand. First thing. If I form the differential form of rate, so I'll say rate of reaction is equal to, in terms of A, it's minus 1 divided by N1, change in the concentration of A divided by time interval, is equal to minus 1 upon N2, change in the concentration of B divided by time interval. Similarly, in terms of C, it's plus 1 divided by N3, change in the concentration of C divided by time interval. In terms of D, it's plus 1 divided by N4, change in the concentration of D divided by time interval, right? So, this is what you call as differential form of rate, you know it. This is what you call as differential form of rate, you know it already. Now, my dear students, what can we do from here? Understand. I can say rate of reaction is equal minus 1 upon N1 delta change. Instead of concentration of A, understand what can I write? Look at this particular equation. Can I say PA is equal concentration of A, RT. Similarly, PB is equal concentration of B, RT. PC is equal concentration of C, RT, etc., etc. So, in place of concentration of A, can I write PA divided by RT? Yes, I can do that. So, PA divided by RT, and over here in the denominator it's delta T. Similarly, minus 1 upon N2, I can write change in the, instead of concentration of B, I can write pressure of B divided by RT, and with it you have got delta T as well. Similarly, it's plus 1 divided by N3, change in the, instead of concentration of C, I'll write pressure of C divided by RT multiplied by delta T. Similarly, in place of concentration of D, I'll write pressure of D divided by RT, and with this I'm writing delta T. Now, my dear students, one thing that's evident, delta T, I'm sorry, RT. I'm cancelling everywhere. So I'm getting the final equation as minus 1 upon N1 change in the pressure of A divided by time interval delta T is equal to minus 1 upon N2 change in the pressure of B divided by time interval delta T is equal to plus 1 upon N3 change in the pressure of C divided by time interval delta T. Similarly, plus 1 upon N4 change in the pressure of D divided by time interval delta T. This is something again which you will be calling as the differential form of rate only. This is also the differential form of rate. Okay? Remember just one thing. Just remember one thing, people. Just remember one thing. Whenever you'll be solving this term or this term or this term or this term, understand at that point of time, you're calculating rate in terms of what? See, here you have got concentration. Here you have got time. Concentration means moles per unit volume. So moles, liter inverse. And for example, time in seconds. So the units of rate here will be in moles per liter per second. Or if time is in minutes, moles per liter per minute, moles per liter per hour, per month, per year, whatever. So when you'll be solving this term or this term or this term or this term, that means you are calculating the rate of the reaction in terms of moles per liter per second if time is in seconds. But when you are solving this term or this or this or this, that means at that point of time, you are calculating rate in terms of what? See, here you have got pressure. For example, pressure is in ATM. Let's say time is in seconds. So then that means you are getting the rate in terms of ATM second inverse. If time is in minutes, ATM minute inverse. Time is in hours, ATM hour inverse. Pressure is in bar, bar second inverse, bar minute inverse, etc., etc. Okay? So remember these two things. Whenever rate is to be calculated in moles per liter per second, solve any of these terms. Whenever rate of the reaction is to be calculated in terms of ATM second inverse, solve any of these terms over here. I believe it's super clear to everyone. If yes, I would want everyone to let me know in the chats right now, if it is clear to everyone. Quickly, guys. Quickly, everybody. Everybody in the chats, quick. All clear till here? All clear till here? Perfect. Amazing. Now let's try to solve equations which can be framed out of the concepts that we discussed till now. Okay? Let's try to solve few questions so that you'll understand where do we use all the stuff which I told you till now. This is the first question, my dear students. Look at it properly. As per this particular question, I'm given with a balanced chemical equation. This is my balanced chemical equation. Okay? Now, before looking at the question, people, do one thing. Write the differential form of rate. Write the differential form of rate before looking at the question. This should be always your first point. Write the differential form of rate. So rate of the reaction is equal. I'll start with minus 1 divided by stoichiometric coefficient 2, change in the concentration of N2O5 divided by delta T. It can be also equaled plus 1 divided by 2, change in the concentration of N2O4 divided by delta T, which will be also equaled in terms of O2 plus 1 by 1, change in the concentration of O2 divided by time interval delta T. So you wrote your differential form of rate. Number 1. Now look at the question. The question says, if the rate of appearance of O2, how can you write the rate of appearance of O2 mathematically? If you remember, my dear students, whenever we write rate of disappearance or rate of appearance, we have got nothing to do with the stoichiometric coefficients at that time. But when we write the rate of reaction at that point of time, we have to do something with the stoichiometric coefficient. We have got something to do with the stoichiometric coefficient, right? Look at this particular statement. If the rate of appearance of O2, how do I write the rate of appearance of O2? The rate of appearance of O2 will be written like this, plus delta O2 divided by delta T. This is what you call as the rate of appearance of O2. As per question, it's given to me as 0.5 moles liter inverse second inverse, right? What am I supposed to calculate? Rate of disappearance of N2O5. How do I write disappearance of N2O5? Minus change in the concentration of N2O5 divided by delta T. This is something which I call as the rate of disappearance of N2O5. So rate of appearance of O2 is given. Rate of disappearance of N2O5 is to be calculated. And one thing which I'm repeating again and again, whenever we are writing rate of appearance or rate of disappearance, at that point of time, we have got nothing to do with the stoichiometric coefficients. That's why I did not introduce stoichiometric coefficient here. Now, my dear students, the differential form of rate which you have mentioned over here, in the differential form of rate, I'll be taking two terms. One is the term which is related to N2O5, that is this particular term, and one more term that is related to O2, that is this particular term. I'm just going to equate these two terms. I'll write them like this. Minus 1 by 2, change in the concentration of N2O5 divided by delta T is equal to, you can equate it with this particular term, delta of O2 divided by delta T, right? Now people, this 2 you can take here, you can say minus delta of N2O5 divided by delta T is equal, this is going to be 2 times delta O2 divided by delta T. So my dear students, tell me just one thing. This 2 I'm writing as such. Delta O2 divided by delta T. Delta O2 by delta T. That's 0.5. The value comes out to be 1 mole liter inverse second inverse. If you look carefully, what did you calculate? You calculated this particular term. And this particular term, you call it as rate of disappearance of what? Of N2O5. I believe I'm clear with this. Yeah? Done and dusted? This was the first type of the simple question that can be asked. People. All right. Look at this one. I'm given with a reaction 2 times NH3 gives N2 plus 3 times H2. Calculate the rate of reaction in the interval 5 to 15 seconds. Interval 5 to 15 seconds. That means this particular interval we are talking about. 5 to 15 seconds. This interval. This interval means delta T is equal to 15 minus 5. That's 10 seconds. So this is my interval. I need to calculate rate of reaction in this interval. Okay. Now, my dear students, tell me just one thing. Look at this particular graph. With the time, the concentration is decreasing. And you know, with the time, concentration of reactant decreases. So this is the graph which is valid for the reactant. and reactant here is NH3. So this graph is valid for NH3. This is the graph which is given to me for NH3. Okay. Now, what do we need to calculate? Rate of reaction in this interval. So, can I write rate of reaction in terms of NH3? I'll start with minus sign, 1 by stoichiometric coefficient, change in the concentration of NH3 divided by time interval. We are done. It's going to be minus 1 by 2. Change in the concentration of NH3. What is the initial concentration of NH3? That is 0.6. What is the final concentration of NH3? That's 0.2. So final minus initial. Divided by time interval is how much? 10 seconds. Solve this. Get the answer in moles per liter per second. Done and dusted. People are saying it's coming out to be 0.02. Okay, I believe you. So it is 0.02 moles liter inverse second inverse. This is the rate of the reaction in the interval 5 to 15 seconds. I believe you are getting this. I believe you are getting this particular stuff. Look at one more type of question. Look at one more type of question, people. You are given with the reaction. You are given with the reaction. And there is some data that's given to me. This is the data that's given to me. I have to get the relation between K1, K2, K3. How you are going to do this? Simple. I told you already, before looking at the question, your first thing should be to write the differential form of rate. So write the differential form of rate. So I'll say rate of reaction is equal. In terms of N2O5, start with minus 1 by stoichiometric coefficient 1. You can write change in the concentration of N2O5. So you can write delta of N2O5 or you can write D of N2O5. Right now I'm writing D of N2O5 because in the question the data is in terms of D only, right? Divided by dt is equal. In terms of NO2, start with plus 1 by 2. Change in the concentration of NO2 divided by dt. Similarly, write it with respect to O2 plus 1 divided by stoichiometric coefficient is 1 by 2. Change in the concentration of O2 divided by dt. Perfect. So you wrote the differential form of rate. You wrote the differential form of rate. Now, if you wrote the differential form of rate, my dear students, tell me one thing. Minus d of N2O5 by dt. Minus d of N2O5 by dt. Instead of this, can I write K1 multiplied by concentration of N2O5? Yes, I can do that. Is equal to plus 1 by 2. dNO2 by dt. dNO2 by dt. Instead of this, I can write K2 multiplied by concentration of N2O5. Yes, can be done. Is equal to. This 2 can come up. When this 2 comes up, I'll be left with dO2 by dt. dO2 by dt is equal to K3 multiplied by concentration of N2O5. So my dear students, N2O5, N2O5, N2O5 cancels out. So I'll be getting K1 is equal to K2 divided by 2, which is equal to 2 times K3. Okay. Now, just do one thing. Take the LCM of denominators. Take the LCM of denominators. And people, if you take the LCM of denominators, LCM will come out to be 2. LCM will come out to be 2. So multiply throughout by 2. It becomes 2 times K1 is equal to 2 gets cancelled. So this K2, this becomes 2 to the 4. So 4 times K3. This is the relation between K1, K2 and K3, which you were supposed to calculate. Done? This is one more type of question that can be asked. Simple and basic. Look at this question. Look at this particular question. You are given with a balanced reaction. XA gives YB. XA gives YB. This X and Y, these are the stoichiometric coefficients of reactants products. Some data is given to me. Some data is given to me. What am I supposed to get? I'm supposed to get the value of X and Y. Now, how exactly? How exactly? How exactly? See guys, first thing. If I write the differential form of rate for this particular equation, how am I going to do it? With respect to A, I'll be starting with minus 1 by stoichiometric coefficient X, right? Change in the concentration of A divided by time interval dt is equal. In terms of B, plus 1 upon Y. Change in the concentration of B divided by time interval dt. This is my differential form of rate. This is my differential form of rate. Now, what can I do from this? Understand. If you look at the given data, this particular term is given in terms of log to the base 10. This term is given in terms of log to the base 10. This term is not given in terms of log. So my first point would be to convert this particular term into logarithmic form. Yeah, that would be my first point. And how exactly am I going to do that? I'll be writing log of minus dA upon dt is equal to, it's going to be log of d of b upon dt plus 0.3. 0.3 is basically log of 2, right? To the base 10. Log 2 to the base 10, that is 0.3. Correct? Now guys understand. So it is a log of minus d of a upon dt is equal to, see, log m plus log n. Log m plus log n, you should be knowing log of m into n. So log of db upon dt multiplied by 2. Write that 2 here. Okay. Now this is log, this is log. If you take nt log on both the sides, it becomes minus d of a divided by dt is equal to 2 times d of b divided by dt. Correct? My dear students, if you take 2 here in the denominator, so it's minus 1 by 2. D of a divided by dt is equal to d of b divided by dt. Now, if you look at this particular equation, have a look. This expression and this expression. Compare the two expressions. Just compare the two expressions. And when you compare the two expressions, you're sorted. See, d upon dt, minus 1 upon x, minus 1 upon 2. That means x has to be equal to what? X has to be equal to 2. 1 upon y, 1 upon 1. So y has to be equal to 1. And this x and y, you are supposed to calculate. Done? Right, people? All clear with this? Quick. Everybody in the chats. Is this particular question clear? Is this particular question clear to every one of you? Everybody in the chats, quick. Everybody in the chats, people. Yes, Kirtana, you can do that too. You can do that too. You can do that too. Okay. Basically, in this question, you have to look at the options. You have to look at the options, basically. From the options, you will be selecting 2 and 1. If there is no 2 and 1, there will be one more option, wherein y will be 1 by 2. Right? Wherein y will be 1 by 2. Perfect? I believe this is super clear to everyone. Let's move on now. Look at this particular question. Look at this particular question. Look at this particular question, guys. Will you be able to solve this? You are given with a reaction which is carried out at 300 Kelvin. Pressure of reactant NO falls from 5 atm to 2.5 atm in 10 seconds. Calculate the rate of reaction. First, in terms of moles per liter per second. Second, in terms of atm second inverse. Okay. So how am I going to do it? Just a second. Let me fix the wire here. Okay. Now see, guys, how this sort of a question will be solved. Let's first of all solve the second part of the question. Let's first of all solve the second part of the question. Let's calculate the rate of reaction in terms of atm second inverse. Now see, rate of reaction will be equal to, in terms of NO, I'll be writing minus 1 upon 2 pressure of NO divided by time interval delta T. Okay, so this is going to be minus 1 by 2. Change in the pressure of NO. The pressure of NO falls from 5 atm to 2.5. So final pressure of NO minus initial pressure of NO divided by, in how much time? In 10 seconds. You are done. I told you already, if you remember, whenever you are solving this sort of a term, that means you are getting the answer in terms of atm second inverse. This is done. Solve this and sorted. Okay. Now, Whenever you will have to calculate rate of reaction in moles per liter per second, in moles per liter per second, what do you need to do? In moles per liter per second, you'll be writing minus 1 by 2. Instead of, minus 1 by 2, then you'll be writing change in the concentration of NO divided by time interval delta T. This is the expression which I'll be using to calculate rate of reaction in terms of what? Moles per liter per second. Right? Now, my dear students, I can write it like this, minus 1 by 2. Since I'm not given with the concentration of NO, I do not know what is the change in concentration of NO. But I know one thing, delta of, instead of concentration of NO, I can write pressure of NO divided by RT multiplied by delta T. I hope you remember. We have discussed this. We have discussed this. So it's going to be minus 1 by 2. Change in the pressure of NO will be final pressure of NO minus initial pressure of NO divided by R value. R is the gas constant. How much is its value? 0.0821. Or you can write 1 by 12. 1 by 12. Temperature is given to me as how much? 300 Kelvin. Delta T, time interval, is given to me as 10 seconds. If you solve this particular term, your answer will come in moles, liter inverse, second inverse. Why is that? Because I told you already, if you are using this particular term to calculate rate, your answer is going to be in ATM second inverse. If you are using this particular term, right, to calculate rate of reaction, your answer is going to be in moles per liter per second. This is something which I told you in the beginning itself, right? I hope you remember. If you do not remember, let me just go back to that particular slide wherein you can understand and remember things correctly. Where was that slide wherein I told you this? Yes, this was the slide. When you solve any of these terms, you are getting rate in moles per liter per second. When you are solving any of these terms, you are getting rate in ATM second inverse. Perfect. I feel this is clear. I feel this is clear. Look at this particular question now. Look at the question and tell me in the chats whether you will be able to solve this question on your own or not. You are given with a reaction. All right. My first thing always is to write the differential form of rate. So write the differential form of rate. I'll say rate of reaction is equal to, in terms of H2O2, start with minus 1 by stoichiometric coefficient 1, change in the concentration of H2O2 divided by time interval delta T is equal, in terms of water, plus 1 by stoichiometric coefficient 1, change in the concentration of H2O divided by time interval delta T. In terms of O2, start with plus 1 by stoichiometric coefficient 1 by 2. So 1 by 1 by 2 comes out to be 2, change in the concentration of O2 divided by delta T. This is your differential form of rate. This is your differential form of rate. Okay. By the way, you can modify the question like this. Just a second. Calculate rate of reaction in moles liter inverse second inverse, right? As well as rate of appearance in moles liter inverse second inverse. This will be mentioned in the question itself. This will be mentioned in the question itself. Now, we are almost sorted. We are almost done. If the concentration of H2O2 changes from this to this in 15 seconds, calculate first of all rate of reaction. I can calculate rate of reaction by solving this particular term. I can write rate of reaction is equal to minus. What is the change in the concentration of H2O2? That has to be final minus initial. Final is how much? 0.05. Initial is how much? 0.5. Divided by time interval is how much? It is 15 seconds, right? The answer is going to be in moles, liter inverse, second inverse. So this question is done. You have calculated rate of reaction. Second, calculate the rate of appearance of O2. Rate of appearance of O2. How do I write rate of appearance of O2 mathematically? I'll be starting with plus sign. Then I'll be writing delta O2 divided by delta T. Nothing to do with the stoichiometric coefficient. This is something which I call as rate of appearance of O2. This is something which I call as the rate of appearance of O2, which needs to be calculated, right? So what I'll be doing here? What I'll be doing here? Just do one thing. Just equate these two terms. Just equate these two terms. When you equate these two terms, you write something like this. Minus delta of H2O2 divided by delta T is equal to, look at this particular term, 2 times delta O2 divided by delta T. Now from this particular equation, you can write like this. Delta O2 divided by delta T is equal to, this 2 will be here in the denominator. So it will be minus 1 by 2 delta of H2O2 divided by delta T. What do we call this particular delta O2 by delta T as? Delta O2 by delta T is what I call as the rate of appearance. Rate of appearance of what? Rate of appearance of O2 is equal to minus 1 by 2. Change in the concentration of H2O2 will be equal to final minus initial. Final is 0.05. Initial is 0.5. Time interval is how much? 15 seconds, sorry. Yeah, 15 seconds. Solve this particular term. The answer will be in moles, liter inverse, second inverse. I believe you can easily solve all the types of the questions which can be asked from a rate of disappearance and appearance, because I've showed you all the types of the patterns which can be asked from this topic. If yes, I would want everyone to write it in the chats quickly. I would want everyone to write it in the chats quickly. Break, I'll be giving you exactly at 8 p.m. 8 p.m. will be our first break. So we have to wait for 1 more hour. Quickly, people. Everybody in the chats, quick. Everybody in the chats, quickly. Quickly, people. Everyone in the chats. Just tell me whether you'll be able to solve all the questions or not. That's great aesthetic videos. You're enjoying the sessions. Amazing. That's great. Keep on doing the same. Just write it in the chats quickly whether all the things are clear or not. It does not take more than 2 seconds to write in the chats. Just write it quickly. Perfect. Let's move on then. Let's move on. I want you guys to be active in the chats. Okay? Because this is the only way I can check whether you guys are getting the things or not. So you need to be active in the chats. Perfect. Let's move on to one more important topic, which we have studied in chemical equilibrium recently, right? Chemical equilibrium, we have studied this topic. But here we are going to again study the same topic. Law of mass action. My dear students, the law of mass action, first of all, let me tell you, it was given by 2 scientists. The name of the first scientist was Goldberg and T. Vage. These were the 2 scientists which gave the concept of law of mass action. Now, this law of mass action It is a complete theoretical concept. It is a complete theoretical concept. It does not have any experimental background. Okay, let me tell you, the law of mass action which we are going to study now, the law of mass action, it's all theoretical. It does not have any experimental background. Okay, now what this law of mass action says? My dear students, the law of mass action says that the rate of the reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficients. Raised to the powers of their respective stoichiometric coefficients. Before making you understand this particular statement, let me tell you one thing which you are going to remember from now onward. Look here, guys. Whenever you see any reactant or product in aqueous state, whenever you see any reactant or product in aqueous state, that means in the bracket, if aqueous is mentioned, for that particular reactant or product which will be in aqueous state, its active mass is basically its concentration. Its active mass is basically its concentration. Whenever you see any reactant or product in gaseous state, whenever you see any reactant or product in gaseous state, its active mass, you can take its concentration or you can take its pressure. Because I told you already, for gases, concentration as well as pressure, both the things are defined. Whenever you see a reactant or product in pure solid state or pure liquid state, their active masses are taken as constant, and the value of that constant, for our convenience, we take it as 1. We take it as 1. So remember this particular stuff. Whenever you see any reactant or product in aqueous state, its active mass is concentration. Gaseous state, its active mass is either concentration or pressure. Solid or pure liquid, its active mass is taken as constant, and that constant, for our calculation purpose, we take that equal to 1. Okay? Now people understand what the law of mass action says. My dear students, from law of mass action is going to give us the idea about the rate of reaction only. And as per law of mass action is concerned, rate of the reaction is directly proportional to the product of active masses of reactants. So I'll write active mass of A multiplied by active mass of B raised to the powers of their respective stoichiometric coefficients. What is the stoichiometric coefficient of A? That's N1. So it's raised per N1. Here it's raised per N2. Here it's raised per N2. So law of mass action is simply going to tell us rate of reaction is directly proportional to the product of active masses of reactants, products of active mass of reactants raised by their stoichiometric coefficients. Now, my dear students, do one thing. Rate of reaction is directly proportional to active mass of A. A is given in aqueous state, and for aqueous species, we use the term concentration. So I'll simply write concentration of A raised per N1 multiplied by concentration of B raised per N2. With the help of this particular stuff, you can remove the proportionality. You can take a constant here, K. This is concentration of A raised per N1, concentration of B raised per N2. So as per law of mass action, this is one more way of calculating rate of reaction. As per law of mass action, this is one more way of calculating what? Law of calculating rate of reaction. So rate of reaction is equal to rate of reaction is equal to the product of active masses of reactants. The product of active mass of reactants raised to the powers of their stoichiometric coefficients. Okay, and the stoichiometric coefficients here are N1, N2. Let me tell you, this law of mass action purely gives us what? It gives us the idea about the rate of reaction only. This is one more way of calculating rate of reaction as per law of mass action. This is one more way of calculating rate of reaction as per law of mass action. And let me tell you, when you use law of mass action to calculate rate of reaction, you would be calling this particular rate of reaction as the theoretical rate of reaction. Theoretical rate of reaction. All right. My dear students, it's pretty much simple. For example, I'm giving you the reaction. This is the reaction which is given to me. And I'm telling you, I'm giving you the value of concentration of A, concentration of B at some instant of time. and at that instant of time, I want you to calculate rate of reaction, you can simply use law of mass action and you can get the theoretical rate of the reaction. Okay? You can get the theoretical rate of the reaction. I hope you're understanding what I'm trying to say. So law of mass action gives me the idea about the theoretical rate of reaction. And as per law of mass action, rate of reaction is directly proportional to the product of active masses of reactants raised by their stoichiometric coefficients. As simple as that. Now understand. Now understand. My dear students, remember one thing. Remember one thing. Whenever you will be given with a reaction, there are basically two ways. There are basically two ways to calculate rate of the reaction. There are basically two ways to calculate rate of the reaction. Either you will be calculating rate of reaction theoretically. You will be calculating rate of reaction theoretically, or you will be calculating rate of the reaction experimentally. You will be calculating a rate of reaction either theoretically or experimentally. Okay? You've got two ways to calculate rate of a reaction. Either you'll be calculating rate of reaction theoretically with the help of law of mass action, or you can carry out certain experiments for the reaction and calculate its rate. Okay? The rate of reaction which we calculate theoretically, I'm denoting that with RT. The rate of the same reaction which we calculate experimentally, I'm denoting that with RE. Now, my dear students, there are some reactions for which the theoretical rate and experimentally determined rate, they come out to be equal. But there are some sort of reactions as well wherein theoretical rate and experimental rate, they do not come out to be equal. They do not come out to be equal. What does that mean? That means your law of mass action, from which you get the theoretical rate, it always does not give you the correct results. Okay? That means with the help of law of mass action, you do not always get the correct result to calculate rate. Perfect? I hope I'm clear with this. I'm again repeating the same thing. In order to calculate the rate of the reaction, we have got two ways. Either I'll be calculating rate of reaction theoretically, or I'll be calculating rate of reaction experimentally. There will be some reactions wherein the theoretical and the experimentally determined rate will come out to be equal. But there are again some type of reactions wherein the theoretical and experimentally determined rate of the same reaction do not come out to be equal. What does that mean? That means this law of mass action. That means this law of mass action from which we calculate the theoretical rate, it always does not give us the correct results, right? Now, my dear students, we want to get correct results from this particular expression. We want to get correct results from this particular expression. So, we are going to modify this expression now. We are going to modify this expression now so that that modified expression always gives us the correct results of rate. Yeah? We are now going to modify this particular expression so that that modified expression is always going to give us the correct result, the correct values of the rate, the actual value of the rate. Now, what is that modified result? That modified result would be called as the rate law. That would be called as a rate law. So, what is a rate law, first of all? It is the modified law of mass action. It is the modified law of mass action. Okay? It is the modified law of mass action. It is based on what? It's based on law of mass action only. It is based on law of mass action. It is just in the law of mass action, certain changes were made. And what were the changes which were made? Have a look. If I have got the reaction N1A plus N2B, it gives products. Let's say this is the balanced chemical equation. What rate law says? Rate law says that rate of reaction is directly proportional to the product of active masses of reactants. Active mass of A multiplied by active mass of B. But here, you are not going to write directly as the powers as stoichiometric coefficients. You are not going to take the powers as a stoichiometric coefficient here. Here you are going to take the powers as X and Y. X and Y. In the earlier case, the powers were taken directly as n1 and n2, which was the stoichiometric coefficients. Here, you are going to take the powers as x and y. You are going to take the powers as x and y, right? And let me tell you, this x and y, they are calculated experimentally. They are calculated experimentally. They are calculated experimentally. Now, I can write it like this. Our rate of reaction is directly proportional. Instead of active mass of A, I'll write concentration of A raised per X, concentration of B raised per Y. If you remove the proportionality sign, you'll be getting a constant K, A raised per X, B raised per Y. Now, this particular equation, I will be calling as a rate law. I'll be calling as a rate law. So, what is the difference between law of mass action and rate law? In law of mass action, you take the powers as n1 and n2 directly. But in rate law, the powers are calculated experimentally, which are represented by x and y. Okay, that is the difference between law of mass action and rate law. Perfect. This particular R over here, this is something which we call as rate of reaction. Rate of reaction. This K over here, this is something which you call as a rate constant of the reaction. This is something which you call as a rate constant of the reaction. This X and Y, which we calculate experimentally, X is something which you call as order of the reaction with respect to A. Y, I'll be calling as order of the reaction with respect to B. If I add these two, X plus Y, this is something which I call as the overall order of the reaction. Well, these are the names given to X, Y, and X plus Y. These are the names which are given to X, Y, and X plus Y. Right? Am I clear with this? Did you understand what is the difference between law of mass action and rate law? In law of mass action, the stoichiometric coefficients are always taken as, the powers are always taken as the stoichiometric coefficients. But in rate law, these powers are calculated experimentally. These powers are calculated experimentally. Okay? Right, people? Now, one more thing. As I told you, I can say now, since the powers are calculated experimentally, so can I say rate law? Rate law, is it experimental or theoretical? Rate law is experimental basically, because these powers are calculated experimentally. So this is experimental basically. This is experimental basically. Now comes a point. For example, you have got the reaction. You have got the reaction, for example, any reaction. Okay. How many ways do we have to calculate the rate of the same reaction? We have got two ways. Either I'll be using law of mass action to calculate the rate of reaction, or I'll be using rate law. There are two ways by means of which I can calculate rate of the reaction. Either I'll be using law of mass action or I'll be using rate law. When I'll be using the law of mass action to calculate the rate, that rate of the reaction I'll be calling as theoretical rate. When I'll be using rate law to calculate rate, I'll be calling that as experimental rate of reaction. Yeah. If you want to write the expression of both, you can do that. It's going to be K, concentration of A raised by N1, concentration of B raised by N2. Similarly here, it's going to be K, concentration of A raised by X, concentration of B raised by Y. Let me assume that the reaction that's given to us is N1A aqueous plus N2B aqueous. Let's say it gives products. This was the reaction that was given to me. Okay. Now, if this is the reaction that's given to me, I've got two ways to calculate its rate, either with the help of law of mass action or with the help of rate law. Perfect. What is the difference between the two? Here the powers are stoichiometric coefficients. Here the powers are calculated experimentally. Now, I told you already, people. There are some reactions in which the theoretical rate of reaction comes out to be same as that of experimentally determined rate. There are some reactions in which the rate of reaction which we get from law of mass action, same rate of reaction we get from rate law as well. So for those particular reactions, I must say X value will be equal to N1 and Y value would be equal to N2. Okay, I believe this is clear. Similarly, my dear students, I told you there are some reactions for which the theoretically determined rate does not come out to be equal to experimentally determined rate. So for those reactions, X value won't be equal to N1 and Y value won't be equal to N2. Right? Right, people? And later on, after some time, you'll understand one thing. This particular stuff is followed by which reactions? You call those reactions as elementary reactions. What are elementary reactions? You'll get the idea in some time. So elementary reactions are the ones for which rate of the reaction with the help of law of mass section or rate of the same reaction with the help of rate law. You'll be getting the same value for elementary reactions, right? This is something which you'll understand in some time. Just wait for it. Perfect. I believe you got the essence of the law of mass section and rate law. Right, people? Now, if you look carefully, this was my rate law. In the rate law, this R represents rate of reaction. This K represents rate constant of the reaction. Now, my dear students, since this R, experimentally determined rate of reaction is equal to K, concentration of A raised power X, concentration of B raised power Y. If I say, if concentration of A as well as concentration of B, both are equal to 1 molar, can I say at that point of time, your rate of reaction is nothing but rate constant? If concentration of A as well as B, that means concentration of all the reactants, if I'm keeping as 1 molar, at that point of time, your rate constant becomes equal to the rate of reaction. So how can I define rate constant? I would say rate constant is nothing. I would say rate constant K is nothing but it is the rate of the reaction. It is the rate of the reaction when concentration of all the reactants, is taken as 1 molar. Okay, is taken as 1 molar. When concentration of all the reactants is taken as 1 molar, at that point of time, whatever will be the rate of reaction, that is something which we'll be calling as rate constant of the reaction. Yeah, that is something which we'll be calling as rate constant of the reaction. I believe I'm clear with this. Now, my dear students, this rate constant, there are some characteristic features of this rate constant which you are going to remember. The first and the most important thing, rate constant K of the reaction, it gives us the idea about the speed with which the reaction takes place. Rate constant of the reaction gives us the idea about the speed with which the reaction takes place. Okay, the first thing. More the rate constant of the reaction, faster is going to be the reaction. Right? More the rate constant of the reaction, faster is going to be the reaction. Okay? Lesser the rate constant of the reaction, slower is going to be the reaction. So rate constant of the reaction is going to give us the idea about how fastly the reaction is proceeding. That reaction whose rate constant is more, that reaction will be faster. That reaction whose rate constant is less, that reaction will be slower. Okay? Every single reaction has got a particular value of rate constant at a particular temperature. Every reaction has got a unique value of rate constant at a particular temperature. And by comparing the rate constants of different reactions, you can talk in terms of the speed of the reaction. Okay? I hope I'm clear with this as well. Every single reaction has got a particular value of rate constant at a particular temperature. Okay? Every reaction has got a unique value of rate constant at a particular temperature. Now, the rate constant, it depends on the temperature. And this particular point we'll understand when I'll be teaching you Arrhenius equation today. For now, you can just remember one thing. When you increase the temperature of the reaction, the rate constant increases. So remember for now, your rate constant of the reaction, that's directly proportional to temperature. When you increase the temperature of the reaction, rate constant increases. And if rate constant increases, I would say eventually rate of the reaction increases. I would say rate of the reaction increases. I would say rate of the reaction increases. Okay? I would say rate of the reaction increases. And this rate constant of the reaction, it has got nothing to do with the initial concentration of reactants. Rate constant of a particular reaction has got nothing to do with what? Initial concentration of reactants. Why? Because the rate constant is defined when the concentration of reactant reaches 1 molar. Okay? Rate constant is defined when concentration of reactant reaches 1 molar. So we have got nothing to do with the initial concentrations of reactants. Right? So these are the 4 important things which I would want everyone of you to remember from now onwards about rate constant. First point. Rate constant gives us the idea about the speed of the reaction. More the rate constant, faster the reaction. Lesser the rate constant, slower the reaction. Number 1. Every reaction has got a particular value of rate constant at a particular temperature. Number 2. Rate constant of the reaction depends on temperature. If you increase the temperature of the reaction, rate constant of the reaction increases. And if rate constant of the reaction increases, what does that mean? That means rate of the reaction will increase. Rate constant has got nothing to do with the initial concentration of reactants. It is independent of the initial concentration of reactants. I believe I'm clear with this as well. Okay. Now, my dear students, one more important thing. What is that? We classify reactions into 2 types. We classify reactions into 2 types. One is called as elementary reaction, or you can call it as the simple reactions. We have got 2 types of reactions, elementary or simple. Elementary or simple. Another one is going to be the complex reaction. What are elementary reactions? Let's have a look. Elementary reactions are the ones which are completed in a single step. Any reaction that gets completed in a single step. Any reaction that gets completed in 1 step. Any reaction that's completed in a single step. You'll be calling that particular reaction as the elementary reaction. And my dear students, this is important point. Law of mass action is truly valid for elementary reactions. Law of mass action is truly valid for elementary reactions. What does that mean? For example, this is an elementary reaction. If this is an elementary reaction, that means it would be getting completed in 1 step. Now we say for elementary reactions, the law of mass action is truly valid. How can we understand this? Have a look. My dear students, in order to calculate rate of reaction, how many ways do we have? We have got 2 ways. Either I'll be using law of mass action or I'll be using the rate law. Either I'll be using law of mass action or I'll be using the rate law. If I'll use law of mass action, I can write rate of the reaction, which is theoretical rate, is equal to rate constant. For example, concentration of A raised per N1, concentration of B raised per N2. But if I use the rate law to calculate rate, I'll write experimentally calculated rate is equal to rate constant, concentration of A raised per X, concentration of B raised per Y. And in case of elementary reactions, law of mass action is truly valid. What does that mean? That means whether you want to calculate rate of the reaction with the help of law of mass action, or you want to calculate rate of the reaction with the help of rate law, for elementary reactions, both these values will come out to be same. So theoretical rate and experimentally determined rate will come out to be same, which is telling you that the value of X, when you calculate experimentally, it will come out to be same as that of N1. The value of Y, which you calculate experimentally, will come out to be same as that of N2. Okay? So remember from now on. Remember from now onwards. Whenever you will see the elementary reaction, in case of elementary reactions, whether you want to calculate rate with the help of law of mass action or you want to calculate rate with the help of rate law, from both the things, you'll be getting the same results. You'll be getting the same results, right? Okay, perfect. Or now we can directly say, in case of elementary reactions, you can say experimentally determined rate will be always equal to K, A raised power N1, B raised power N2. Because X after calculating will come out to be N1, Y will be coming out to be N2 only. Okay, I believe I'm clear with this. Right? Similarly, guys, there is one more type of reaction which you call as complex reaction. What is a complex reaction? Complex reaction is not completed in just one step. Complex reactions are completed in more than one step. Any reaction that gets completed in more than one step, any reaction that gets completed in more than one step, you call that reaction as the complex reaction. Okay? And remember one thing, the steps which are involved in the complex reaction, that are elementary. That are elementary. What does it mean? Have a look. Have a look, guys. For example, I'm taking a reaction NO plus Br2. Let's say it gives NOBr2. Let's say it gives NOBr2. Now this NOBr2 which I'm writing over here, NOBr2 plus NO. Now it gives 2 times NOBr. It gives 2 times NOBr. Perfect. If I add these two reactions, what all things will get cancelled out? NOBr, NOBr2 will get cancelled out. NO plus NO makes it 2 times NO. Plus what? Plus Br2. It gives me what? It gives me 2 times NOBr. Correct? Tell me just one thing. Whether this particular reaction, whether it's getting completed in one step? No. It is getting completed in more than one step. It is getting completed in more than one step. So, any such reaction which is getting completed in more than one step, you call that particular reaction as the complex reaction. But, see, this complex reaction is getting completed in how many steps? 2 steps. Let me tell you, the steps which are involved in the complex reaction, they're always elementary. So this particular step will be elementary in nature. Similarly, this particular step will be also elementary in nature. The steps which are included in the complex reaction, they're always elementary in nature. Remember this particular point as well. Okay. And one more thing. For example, the first step is the fast step. The second step is the slow step. Remember, that step which is the slowest step, that determines the overall rate of the complex reaction. The step which is slowest in nature, right? That is going to determine the overall rate of the reaction, and that slowest step is something which you call as rate determining step. That slowest step is what you call as rate determining step. I believe these 3 points you are going to remember from now onwards. Okay, related to complex reactions. Perfect. Now, my dear students, there is one more concept. That's what you call as molecularity. From this again question can be asked. What is molecularity? Let me first of all tell you, molecularity is again what? It's a theoretical concept. Molecularity is again a theoretical concept. It does not have any experimental background. What? Molecularity, right? Molecularity, it's completely a theoretical concept. Now, what this molecularity is all about? Okay, what kind of information it gives us? See, guys, we have to discuss one theory in this chapter. That's what you call as collision theory, right? That's called as collision theory. One theory which we have to discuss in this chapter, that's what you call as collision theory. And what collision theory says? Collision theory says that for the reaction to happen, for the reaction to proceed, the reacting species must collide first. The reacting species must collide first. Okay. Now, what is molecularity? Molecularity is defined as the number of reacting species. Which can be atoms, ions, or molecules. The number of reacting species which must collide simultaneously to form the product. That's something which you call as molecularity. The number of reacting species which must collide simultaneously to form the products. See, as per collision theory, which we are going to discuss later on in detail, right? But right now, one point I would require from collision theory. Collision theory says that for the reaction to happen, for the reaction to proceed, reacting species must collide first. Okay? Then reaction can happen or cannot happen. That is a different debate, which I'll be discussing afterwards. Only one thing which you are going to remember here, as per collision theory is concerned, the reacting species, which can be atoms, ions, or molecules, they must collide first. Now, how many reacting species are colliding simultaneously to form the products? That defines molecularity of the reaction. For example, For example, look at this particular reaction. In this particular reaction, your reacting species are molecules, H2 molecule, I2 molecule. So how many? I'm assuming two molecules here are colliding to form the product. If two molecules are colliding to form the product, so I would say molecularity of this reaction is 2. Okay. In this reaction, 2 plus 1, 3 molecules are colliding to form the product. I would say molecularity of this reaction is 3. In this particular reaction, two reacting species are colliding to form the product. I'll say molecularity of this reaction is 2. Okay. In the first case, here you will directly say molecularity of this reaction is 1. Now, what does that mean? Molecularity of the reaction is 1. Remember, whenever you have got only one reactant, particle, its collision is considered with the wall of the container. Or its shake-off is called as collision. Its shake-off is considered to be a collision. Or leave it aside, just remember, if you have got only one reacting species, its collision is considered with the wall of the container. Perfect. So the number of reacting species which must collide simultaneously to form the product, that's something which you call as molecularity. Here, molecularity of the reaction is 1. Molecularity of the reaction is 2. Molecularity of the reaction is 3. Molecularity of the reaction is 2. Now, if I ask you one thing, what do you think is the molecularity of this reaction? Half of H2 plus half of I2 gives HI. What do you think is the molecularity of this reaction? What you are going to say half molecule, half molecule. So in total, one molecule is colliding. That will be your answer. Yeah. So technically, its molecularity should be 1. Which is not the case. Here, my dear students, whenever you have got this type of the example, where the stoichiometric coefficients of reactants are fractions, where they are fractions. So first of all, first thing would be, you are supposed to convert these fractions into natural numbers. How you are going to convert these fractions into natural numbers? What I'll be doing, I'll be multiplying this reaction throughout by number 2. I'll be multiplying this reaction throughout by number 2. So that 2 gets cancelled, it becomes H2. 2 gets cancelled, it becomes I2. It gives 2 times HI. Right? Now tell me the molecularity of this particular reaction. Molecularity of this particular reaction will be 1 plus 1, 2. So if the molecularity of this reaction is 2, that means molecularity of this reaction will be also 2. Okay, remember this particular example. If the stoichiometric coefficients of reactants are fractions, convert them into simplest natural numbers first. Then whatever is going to be the molecularity of the new reaction, same is going to be the molecularity of the old reaction. One more thing. The concept of molecularity, it is defined only for elementary reactions. The concept of molecularity, it's only and only given for elementary reactions. It's only defined for elementary reactions. Remember this, right? Remember this. The point is, molecularity of the reaction is defined only for which reactions? It's defined only for elementary reactions. Concept of molecularity was given particularly for which reactions? Elementary reactions only. Now, look at this statement. This you should be in a position to understand on your own. Molecularity of the reaction can never be 0, can never be fractional, can never be negative. What if I say molecularity of the reaction is 0? What does that mean? That means 0 molecules have collided. Does not make any significance. Right? If I say molecularity of the reaction is negative, -3, -4, what does that mean? -3 molecules have collided. Does not make any significance. If I say molecularity of the reaction is 2.3, what does that mean? 2.3 molecules have collided. Does not make significance. Remember, molecularity of the reaction can never be 0. It can never be negative. It can never be fractional. Okay? And those reactions which have got molecularity greater than 3, they exist, but they are rarely observed. They are rarely found. Those reactions which have got molecularity greater than 3, they are rarely observed. Why is that? Why is that? See, if you look at the definition says the number of reacting species which must collide simultaneously. So collision has to be simultaneous. Collision has to be simultaneous, right? Now, for more than 3 molecules to collide simultaneously, I would say more than 3 molecules to collide simultaneously, the probability of simultaneous collision, the probability of simultaneous collision of more than 3 molecules, that's very less, right? The probability of simultaneous collision of more than 3 molecules, that's very less. That is the reason those reactions which have got molecularity greater than 3, they are not frequently seen, they are rarely observed, right? Because the probability of simultaneous collision, the probability of simultaneous collision of more than 3 molecules, that is rare. Its probability is less. Okay? Its probability is less. You can remember it like this as well. You can remember it like this as well. See, let's say these 2 molecules have to collide. They'll do the direct collision. Let's say now 3 molecules have to collide simultaneously. If these 3 molecules have to collide simultaneously, its probability of simultaneous collision is comparatively less than that of first case. Now, if 4 molecules have to collide simultaneously, the probability of simultaneous collision here is even less. If probability of simultaneous collision here is even less, that means reactions with molecularity greater than 3, they exist but are rarely observed. I believe this is clear. Look at this particular point. I told you molecularity concept was given only for what? Elementary reaction. That means molecularity of the complex reaction. Molecularity of the complex reaction does not have any significance. Remember, in the complex reaction, since I told you the steps involved in the complex reaction, they are elementary. So this step, both are elementary. This is elementary in nature, this is elementary in nature. The steps involved in the complex reaction, they're elementary. If I write the net reaction is going to be this gets cancelled. NO makes it 2 times NO plus what? Plus Br2 gives what? 2 times NOBr. So this particular reaction is not complete in one step. It is complete in more than one step. So this is my complex reaction. And molecularity concept was not given for complex reactions. Molecularity concept was given for elementary reactions. Now, the steps which are involved in the complex reactions, they are elementary. If the steps are elementary, that means each step here would be having their individual molecularity. So what will be the molecularity of this step? Molecularity of this step will be 1 plus 1, 2. Molecularity of this step will be how much? 1 plus 1, 2. But molecularity of the complex reaction, it does not have any significance. It has no meaning. Okay, because molecularity concept was given for what? It was given particularly for elementary reactions only. Right? So remember, molecularity was given for elementary reactions. Right? The steps which are involved in the complex reactions are elementary. So their molecularity is defined. But the molecularity of the overall reaction is not defined. The molecularity of the complex reaction is not defined. I mean, it does not have any physical significance. Right? Perfect. I believe this is clear. And my dear students, based on molecularity, you are going to classify reactions into certain types. That reaction whose molecularity is 1, you call that particular reaction as unimolecular reaction. That reaction whose molecularity is 2, you call that as bimolecular reaction. That reaction whose molecularity is 3, you call that as trimolecular reaction. Perfect. So based on molecularity, we can classify reactions into certain types as well. Right? So this was all about molecularity. I hope you are going to remember them from now onwards. Okay? All clear with this? All clear with this, people? All clear with this? Now comes one more topic. That's order of the reaction. My dear students, order, it's slight idea I gave you already. Okay, what is order? Order is defined as the sum of the powers of the concentration terms involved in the rate law or rate expression. For example, this is my balanced chemical equation. If I write a rate law for this balanced chemical equation, how do you write it? You are going to write K, concentration of A raised power X, concentration of B raised power Y. Okay? This is your rate law. This is the rate law for this particular reaction. If this is the rate law for this reaction, then this X would be called as order with respect to A, y would be called as order with respect to B, and x plus y would be called as the overall order of the reaction. It would be called as the overall order of the reaction. Okay, it would be called as the overall order of the reaction. So the point is pretty much simple. What is order? Order is nothing but, order is defined as the sum of the powers, of all the concentration terms, the sum of the powers of all the concentration terms involved in the rate law. So this x plus y is basically going to give us the order of the reaction. Yeah? Now, my dear students, tell me one thing. What do you think? Is order going to be theoretical or experimental? Let me tell you, in order to calculate order, what do we need? We need x and y. And if you remember, this x and y in the rate law is calculated experimentally. So order is what? Order is experimentally determined. Order is experimentally determined. Why is that? Because in order to calculate order, we need to write the rate law. In the rate law, whatever powers we get in the concentration terms, right? Those powers are calculated experimentally. So eventually I can say order is the experimentally determined quantity. Now, unlike molecularity, since order is experimental, right? Unlike molecularity, molecularity cannot be zero, molecularity cannot be negative, molecularity cannot be fractional. But remember, order can come out to be zero as well. Order can come out to be positive as well. Order can come out to be fractional as well. Remember this. These are all facts which I'm giving you. These are all facts which I'm giving you. Right? These points have been checked experimentally, basically. Orders of the reaction, it can be zero. There are some reactions which have got zero order. There are some reactions which have got positive order. There are some reactions which have got fractional order. But remember one thing. Order with respect to any reactant. Order with respect to any reactant. That means I'm talking about x and y separately. Order with respect to any reactant can be negative, but overall order of the reaction can never be negative. Remember, x can be individually negative, y can be negative, but x plus y can always come out, is always going to be positive on. It will never be negative. It will never be negative. Okay, it will never be negative. So for example, let's say you've got a reaction like this. Let's say you've got a reaction like this, N1A plus N2B, it gives products. For example, you're writing its rate law. Let's say its rate law came out to be R is equal to K, concentration of A, raised power -1, concentration of B, raised power 2. So see, order with respect to A is negative. Order with respect to B is positive here. But overall order will be 2 plus -1, which will come out to be 1 only, which is not negative. So order with respect to any reactant can be negative, but overall order of the reaction can never be negative. Remember this particular statement as well. This can be directly asked in your exam. Okay. Now, this again one important statement. For the elementary reaction, order is equal to molecularity. What does it mean? For the elementary reaction, order is equal to molecularity. For example, you have got the reaction like this. 2 times A plus B, it gives C. Let's say it's a balanced chemical equation. I'm assuming the reaction is elementary. If the reaction is elementary, so we can define its molecularity. What will be molecularity of this reaction? 2 plus 1 comes out to be 3. Molecularity is 3. Molecularity is 3, right? Molecularity is 3. Now, for example, I want to calculate its order. In order to calculate the order, what do I need to write? I need to write rate law. Rate law says that R is equal to K. Concentration of A raised power X, concentration of B raised power Y. But since the reaction is elementary, and for the elementary reactions, law of mass section is truly valid. That means this X will come out to be same as that of 2. The Y will be coming out to be same as that of 1. Right? So I would say order of the reaction, overall order of the reaction here, will be simply X plus Y. That means 2 plus 1. That means 3. Look at this particular statement now. Statement is simply telling you, if you have got the elementary reaction, in case of elementary reactions, order and molecularity will be always the same. In case of elementary reactions, I must say, order and molecularity, they're always same. Remember this particular point as well. Remember this particular point as well. And similarly, one more important point I'm giving you. Remember a zero order reaction. A zero order reaction can never be elementary. A zero order reaction can never be elementary. Zero order reaction is always complex. Do you see why? Do you understand why? Tell me why. In zero order reactions, a zero order reaction can never be elementary. What is a zero order reaction? Zero order reaction is the one whose order is zero, right? A reaction whose order is zero, you call that a zero order reaction. If the zero order reaction was elementary, if it was elementary, then its molecularity also should have been, zero. Because for elementary reactions, order and molecularity is same. But molecularity is equal to zero. Does it have any significance? It does not have any sort of significance. It does not have any sort of significance. So remember this statement directly. Whenever you will see the zero order reaction, my dear students, zero order reaction, it can never be elementary. It is always complex. Remember this particular point. This is super important. This is super important. A zero order reaction must be complex. It can never be elementary. Okay? Perfect. Right? Somebody is asking, Wassim sir, who is your favorite physical chemistry teacher in Kashmir? Guys, give him the answer. Give him the answer. All clear to there? All clear till here, people? Yeah? Give him the answer. Give him the good answer. He needs that. I believe all the stuff is clear till here. Now I think we'll take a break for 30 minutes, but only if you guys are going to be back on time. If yes, then let's take a break. This is not the dinner break. Dinner break will take at 10:30. Okay, this is just the casual break. Right? So break till, what is the time now? It's 8. So let's take the break till 8:30. And I would want every one of you to be back on time. Okay? Be back on time. Everyone. Everyone. Perfect? Because after the break, actual stuff. After the break, actual stuff is going to come. Okay? Maran, I have no idea what he's talking about, yeah? Who's my favorite physical chemistry teacher in Kashmir? If I had some favorite, he should have been here, right? Hello, see you after the break. Welcome back. Welcome back, guys. Welcome back. Is everyone back? Yes. Let me know once in the chats if everyone is back. Perfect, perfect, perfect. So guys, can you let me know in the chats whatever things we have discussed till now, if every single thing is clear to everyone? I want to know this first of all, then we'll move ahead. Whatever things we have discussed till now, is every single thing clear? Quickly, let me know in the chats. Whatever things we have discussed till now, are all the things clear? Questions we'll be doing in some time. Just wait. Just wait. Questions we shall be doing in some time. First, we have to cover some concepts, important concepts, which are required to solve the questions. Okay, so I think let's get going then. Let's get started. So people, now our topic is going to be relation between different rate constants. A relation between different rate constants. My dear students, in a chemical reaction, there are different rate constants which are used. Have a look. First of all, I'm going to write few terms over here. The first thing I'm writing, that is Ka. I'm writing a term Ka over here. I'm writing a term Ka over here. Similarly, I'll be writing a term Kb over here. In the similar way, I'll be writing a term Kc and Kd. These are the four terms which are mentioned over here. Ka, Kb, Kc and Kd. Let me tell you this Ka over here, I'll be calling this term as a rate constant for disappearance of A. This Kb over here, I'll be calling as the rate constant for the disappearance of B. Similarly, this Kc over here, I'll be calling as the rate constant for the appearance of C. The rate constant for the appearance of C. In the similar way, this Kd I'll be calling as the rate constant for the appearance of D. Okay? So Ka, Kb, Kc and Kd. Ka is what I call as rate constant of disappearance of A, rate constant of disappearance of B, rate constant of appearance of C. And this Kd I'm calling as the rate constant of appearance of D. Number one. Number two, this K reaction, I'm calling this as the rate constant of the reaction. I'm calling this as the rate constant of the reaction. Now, my dear students, there is a relation between rate constant of the reaction and these individual rate constants. There is a relation between the two. Rate constant of the reaction and the individual rate constants of these reactants and products. What is that relation exactly? Let me directly give you the result. I'm not deriving the result. I'm just giving you the result and I'll show you how to apply that result. Okay. Now, that result is something like this. I will write rate constant of disappearance or appearance of a reactant or product. Of a reactant or product. It is always equal to rate constant of the reaction multiplied by stoichiometric coefficient of the reactant or product. This is one direct result. This is one direct result. For example, I've got the reaction N1A plus N2B. Let's say it gives N3C plus N4D. Let me assume rate constant of this reaction is this K reaction. This K reaction represents the rate constant of the reaction. Okay. Now, my dear students, I can write rate constant of disappearance of A. Rate constant of disappearance of A. I can write it as rate constant of reaction multiplied by the stoichiometric coefficient of A, that is N1. Similarly, rate constant of disappearance of B, I can write it as rate constant of reaction multiplied by stoichiometric coefficient of B. Similarly, Kc, rate constant of appearance of C, I can write it as rate constant of reaction multiplied by stoichiometric coefficient of C. Rate constant of appearance of D, I can write it as rate constant of reaction multiplied by stoichiometric coefficient of D. Okay. Now, people, understand one thing. From this first equation, can we calculate rate constant of reaction? I will say rate constant of reaction as per this equation will be equal to Ka divided by N1. Ka divided by N1. Similarly, from the second equation, I can say rate constant of reaction is nothing but K2 divided by K2 divided Ka, sorry, this is Kb. Kb divided by N2. Similarly, from the third equation, I can say rate constant of the reaction is nothing but it is Kc divided by N3. Kc divided by N3, right? And similarly, from here, I can say rate constant of the reaction is equal to Kd divided by N4. Kd divided by N4. Now, my dear students, if you look at all these things here, I can formulate one simple statement. I can formulate one equation. Equation is going to be simple. See, K reaction is this, K reaction is this, K reaction is this, K reaction is this. I can say rate constant of the reaction is always equal to rate constant of disappearance of A divided by N1, which can be also equal to rate constant of disappearance of B divided by N2, rate constant of appearance of C divided by N3, rate constant of appearance of D divided by N4. This is one important expression which I would want every one of you to remember, because from this expression, one simple question can be framed over here. Okay? But be careful with all these things. Yes, guys, it's Kc here. K3 or Kc. Okay, it's Kc divided by N3. Right? So this particular expression I would want every one of you to remember. Why I want this particular expression to be remembered? Just to solve one simple question. And the question is this. Have a look. We are given with a balanced chemical equation. Okay? We are given with a balanced chemical equation. K1, K2, K3 are the individual rate constants of these reactants products. Right? We have to find the relation between K1, K2 and K3. This K over here, it represents rate constant of reaction. Can't I simply say, if you look at this particular reaction, can't I say rate constant of the reaction has to be equal to Ka. Ka means K1 here, divided by its stoichiometric coefficient is 2, is equal to K2 divided by stoichiometric coefficient. Similarly, K3 divided by stoichiometric coefficient. Right? Now, my dear students, just do one thing. Look at these denominators and take the LCM of these denominators. What is the LCM of 2 and 3? LCM of 2 and 3 is 6. I'll be multiplying throughout with 6. Right? So, it's going to be 6 times K1 by 2 is equal to 6 times K2 divided by 3 is equal to 6 times K3, right? When you solve this, it's going to come out to be 3 times K1, 2 times K2, and 6 times K3. This is going to be the relation between K1, K2 and K3, which we were supposed to calculate. I believe this is clear to everyone. I believe this is clear to everyone. We were supposed to get the relation between K1, K2, K3, and here we have got the relation between K1, K2 and K3. Clear, people? Is it clear to everyone? Let me know once in the chats quick. Let me know once in the chats quick if this is super clear to everyone. It is just, you have to remember this particular result. That's all. This is the relation between rate constant of the reaction and the individual rate constants. Perfect. Now, moving ahead. What are going to be the units of rate constant? What are going to be the units of rate constant? Understand properly, guys, what exactly I'm going to say. This is also one important point. For example, you have got the reaction like this, A gives B. I'm assuming order of this reaction is N. Let's say order of this particular reaction is N, correct? If I write rate law for this particular equation, if I write rate law for this particular reaction, how do I write its rate law? I'll be writing rate of reaction is equal to rate constant multiplied by active mass of A raised per order. That's N, right? Now this active mass, I can elaborate it as R is equal to K. Instead of active mass of A, I can write concentration of A raised per N, or instead of active mass of A, I can write pressure of A. I can write pressure of A raised per N. I'm assuming this is in gaseous phase, and similarly, this is also in gaseous phase. And for gases, we define concentration as well as we define pressure. Okay. Now, my dear students, K over here will be equal to R divided by concentration of A raised per N. Similarly, K over here can be written as R divided by pressure of A raised per N, where N is the order of the reaction. Right? I already assumed order of the reaction as N. That's why in the power here, I directly wrote as N. Correct? Right? Because over here, we have got only one reactant. If there is one reactant, what does that mean? That means whatever is going to be the order with respect to A, same is going to be the overall order of the reaction. Correct? Same is going to be the overall order of the reaction. Because there is only one reactant. So whatever is order with respect to A, same is going to be the overall order of the reaction. I'm assuming the overall order of the reaction is N, which has to be equal to the order with respect to A. Right? So order with respect to A here, I wrote as N. Perfect. Now guys understand. What are the units of this particular term are rate here? Since I'm writing rate in terms of concentration here, and rate is rate in terms of concentration. It's moles, liter inverse. Let's say time is in seconds. So second inverse divided by. Here you have got concentration. Concentration means moles per unit volume. So it's moles, liter inverse, raised per what? Raised per N. Perfect. So moles, liter inverse, raised per N. So unit of rate constant here is going to be moles, liter inverse, raised per 1 minus N. And if time is in seconds, so second inverse with it. If time is in minutes, then you can write minute inverse. Time is in hours, then here you can write R inverse. Perfect. This is one of the general unit of rate constant. Similarly, here, my dear students, rate I have expressed in terms of pressure. And if you're expressing rate in terms of pressure, let's say the pressure units are in ATM, time is in seconds. So the unit of rate is going to be ATM second inverse here. And unit of pressure, for example, pressure is in ATM. So ATM raised per N. So I would say here the unit of rate constant is going to be ATM raised to the power 1 minus N. If time is in seconds, so it's going to be second inverse. So these are the general units of rate constant which you are going to remember. Over here, this N represents the order of the reaction. Now understand properly. Let's say you have got a zero order reaction. Let's say you have got a zero order reaction. In case of the zero order reaction, what is the value of N first of all? N has to be 0. Rate constant units in general are supposed to be moles, liter inverse, raised per 1 minus N. Let's say time is in seconds, so second inverse. Or it can be written as, let's say pressure is in ATM. ATM raised power 1 minus n, second inverse. Now, in case of zero order reaction, n value is 0. If n is 0, so it's going to be moles liter inverse. 1 minus 0 is 1 and second inverse. Or one more unit can be ATM raised power 1 minus 0 is 1, and with it, you'll be writing second inverse. These are the units of the rate constant for the zero order reactions. For the zero order reactions, right? Now, my dear students, imagine that you're got a first order reaction. Imagine that you're got a first order reaction. For a first order reaction, if you have got a first order reaction, that means n value, which represents order of the reaction, that's 1. If n is 1, put the value of n as 1 here. So 1 minus 1 is 0. Anything raised power 0 is 1. So units of rate constant here is going to be simple second inverse. Or if time is in minutes, so minute inverse, hour inverse, whatever, right? Similarly, here also it's coming out to be what? ATM raised power 1 minus n. n is 1. So 1 minus 1, 0. Anything raised power 0 is 1. So second inverse only. Correct? So in general, you can write it as time inverse. Time raised power minus 1. This is valid for what? This is valid for first order reactions. Similarly, my dear students, if you will be having similarly second order reactions, if n is equal to 2, if n is equal to 2, that means I'm talking about the second order reaction. If n is equal to 2, that means I'm talking about the second order reaction. In case of the second order reactions, n value is 2. So 1 minus 2 is minus 1. So K can be written as moles liter inverse whole raised power minus 1. And with it, I'm writing second inverse. Or you can write it like this. ATM raised power 1 minus 2 is minus 1. And with it, you'll be writing second inverse. Perfect. Right? And my dear students, eventually, you can convert this in different form as well. This is mole liter inverse raised power minus 1. You can write it like this. Mole inverse, liter inverse is liter, and this is second inverse. You can write it like this as well. Perfect. So, I would say the unit of rate constant, it depends on what? It depends on order of the reaction. Units of rate constant depends on what? It depends on order of the reaction. So, based on the order of the reaction, you are going to decide the units of the rate constant. Right? Perfect. I believe this is clear. Now the point is, what is the significance of order? What kind of information order gives us? What kind of information order gives us? See guys, it's pretty much simple. Just understand what kind of information order gives us. Let's say you've got the reaction A gives B. I'm assuming that order of this reaction is equal to 0. I'm assuming that order of this reaction is equal to 0. Right? Since you have got one reactant here, if there is only one reactant, I can say whatever is going to be the order with respect to A, same is going to be overall order of the reaction because there is only one reactant. Since there is only one reactant, so whatever is going to be order with respect to A, same is going to be the overall order of the reaction. Correct? Now, if you want to write the rate law for this reaction, rate law R is equal to rate constant. Let's say concentration of A raised power what? Raised power order. Raised power order with respect to A, and order with respect to A as well as overall order of the reaction. That's 0. Perfect. For example, if the same reaction was of first order, if the same reaction was of first order, then how would you write its rate law? R is equal to K, concentration of A raised power order, that's 1. If the same reaction was second order, if the same reaction was second order, how do we write its rate law? R is equal to K, concentration of A raised power 2. Now, from the order, what kind of information you are getting? From the order, what kind of information you are getting? Understand. Understand. My dear students, anything raised power 0 is 1. So, it tells you that rate of reaction is independent of the concentration of reactant. Right? If you want to change the concentration of reactant, nothing is going to happen to the rate of this reaction. If you modify the concentration of reactant, if you want to increase the concentration of reactant or decrease the concentration of reactant, nothing is going to happen to the rate of reaction in case of zero order reactions. But if you talk about first order, reaction, if you double this, this is going to double. If you triple this, this is going to triple. If you make this 4 times, this becomes 4 times, right? Perfect. So in case of first order reactions, what kind of information you are getting? You are getting one simple information, that rate varies linearly with the concentration of reactant. Rate varies linearly with the concentration of reactant. Similarly here, order of the reaction is 2. That means if you make this 2 times, 2 ka square, this becomes 4 times. If you make it 3 times, 3 ka square, this becomes 9 times. If you make it 4 times, 4 ka square makes it 16 times, right? So order is going to let us know, order is going to tell us how many times rate of the reaction is going to change on changing the concentration of reactant. Order is simply giving us the information about how many times rate of reaction is going to change on changing the concentration of reactant. Like in zero order, rate does not change on changing the concentration of reactant. Right? Perfect. Similarly, here, rate varies linearly with the concentration of reactant. Rate varies with the power of 2 with the concentration of reactant. So I would say the order, the significance of order, what kind of information order gives us? Order of the reaction gives us the idea about how much the rate of the reaction changes on changing the concentration of reactants. As simple as that. Am I clear with this? Am I clear with this? Let me know once in the chats quick. Let me know once in the chats quick. So my dear students, let's see what kind of basic questions can be formed till now. Let's see what kind of basic questions can be formed till now. One simple and basic question. We are given with the reaction A gives B. We are given with the reaction A gives B, whose rate constant is K. It is found that rate doubles when the concentration of A is increased 4 times. Rate is doubling when the concentration of A is increased 4 times. Find the order of the reaction. See, the simplest way of solving this sort of a question. This is the reaction that's given to me. Since there is one reactant, if there is one reactant, so I would say the order of the reaction with respect to A is going to be the overall order of the reaction, and let that order of the reaction be N, which I'm supposed to calculate. I'm supposed to calculate the order of the reaction. I'm supposed to get the value of N. Let me write its rate law first of all. Well, you know, in order to calculate order, first thing which we are supposed to write, that's rate law. And rate law says that R is equal to K, concentration of A, it's going to be raised per order, raised per N. Let me call this simply as equation number 1. Now, as per the question, it is found that rate doubles when the concentration of A is made 4 times. So rate initially was R, now it's becoming 2R. When is it becoming 2R? When you are making the concentration of A 4 times. So initially it was A, now it is 4 times A. So how many equations we got? We got 2 equations. Now it's time to simplify these 2 equations. As simple as that. How do you simplify them? How do you simplify them? Let me just divide the second equation by the first equation. If I divide second with first, so 2R divided by R will be 2 is equal to K and K cancel, A raised per N cancel. This is going to be 4 raised per N here. This is going to be 4 raised per N. What has to be the power of 4 such that LHS RHS becomes equal? I would say N value here should be equal to 1 by 2. Then only 4 raised per 1 by 2 comes out to be 2. So N value has to be equal to 1 by 2. And what was this N? N was the order of the reaction. So I would say order of this particular reaction is nothing but 1 by 2. Is it simple? Isn't it simple, guys? For example, this is your one more question. This is your one more question. The rate of the reaction becomes half. The rate of the reaction becomes half when the volume of the vessel is doubled. Yeah? Rate of the reaction becomes half when the volume of the vessel is doubled. Just a second. Okay. The rate of the reaction becomes half when the volume of the vessel is doubled. Find the order of this reaction. Okay, guys, again a simple and basic question. You have got the reaction A gives B, whose rate constant is K. I'm assuming order of this particular reaction, for example, is N. Well, in order to calculate order, what do we need? We need rate law. So write rate law over here. I would say R is equal to K, concentration of A raised per N. Perfect. Now, in the question, they are saying the rate of the reaction becomes half when the volume of the vessel is doubled. So let me convert this equation in volume form. How exactly? I'll write R is equal to K. Instead of concentration of A, I'll write moles of A divided by volume of vessel. Because concentration is moles per unit volume, right? Right, people? I believe this is clear. Yeah. So instead of concentration of A, I wrote moles of A divided by volume of the vessel. Let me call this equation number 1. Now, as per the question is concerned, what is happening? The rate of the reaction becomes half. So initially the rate of reaction was R. Now it's becoming R by 2. When is it becoming R by 2? When volume of the vessel is doubled. So initially the volume of the vessel was V. Now the volume of the vessel becomes 2V. Right? Calling this equation number 2. Calling this equation number 2. Yeah? Right? So as per the equation, when volume of the vessel is doubled, rate is becoming half. So now divide the two equations and you are done. Perfect. If I divide equation 1, for example, with equation 2. If I divide equation 1 with equation 2, R and R gets cancelled. On the left side, I'll be left with 2. On the right side, K and K gets cancelled. NA by V gets cancelled. On the right side, it becomes 2 raised power N. So when can be 2 raised power N equal to 2? When can be LHS RHS equal? If the value of N comes out to be 1. And what was this N? N was basically the order of the reaction. Right? Simple. Correct, people? I believe this is also clear. Let's say you have got the question like this. Let's say you have got the question like this. A plus B gives C. This is the reaction. Rate is doubled when the concentration of B is doubled. Rate is doubled when the concentration of B is doubled. And rate increases by the factor of 8 when concentration of A as well as B are doubled. Calculate the order. Calculate the order. Again, a simple and basic question, guys. The reaction that's given to me is A plus B gives C. This is my reaction. Let's say its rate constant is K, and I'm assuming order of this particular reaction. I'm assuming order of this particular reaction with respect to A is, for example, X. With respect to B, it's Y. Okay? Now, if I want to write the rate law, R is equal to K, it's going to be concentration of A raised power X, concentration of B raised power Y. This is my rate law. This is my rate law, calling this equation number 1. Now, as per the question, rate is doubled. So initially it was R, now it is 2R. Rate is doubled. When? When the concentration of B is doubled. Keep all the other parameters same. When the concentration of B is doubled. Now it's 2 times B raised power Y. Calling this is equation number 2. Calling this is equation number 2. Yeah? Just a second, guys. Hello? What's up? How are you? मैं लाइव ही हूँ अभी बेसिकली लाइव सेशन में अच्छा ओके व्हाट्स अप हाउ आर यू ओके वेयर आर यू should I tell students who is calling me yeah okay चलो see you take care bye bye okay look here now. So this was my equation number 2 now. Now, as per the question is concerned, there is one more statement that's mentioned. Rate increases by the factor of 8. Rate increases by the factor of 8 when the concentration of A as well as B are doubled. Now, the rate is increasing by the factor of 8. So initially it was R, now it's 8 times R. But when is it becoming 8 times R? When concentration of A as well as B is doubling basically. So it's going to be K 2 times A raised power X, and here it's 2 times B raised power Y. I'm calling this equation number 3. I am calling this as the equation number 3. Okay? Now, my dear students, look carefully. Whatever things were mentioned to me in the question, I framed all those things in the form of equations. First of all, I wrote the rate law. As per the statement number 1, rate is doubling when the concentration of B is doubling. Then, rate is becoming 8 times when concentration of A as well as B, both are doubling. Yeah? Perfect. Now, it is just the matter of calculation. I just need to solve these equations and get the value of X and Y. Right? And how exactly am I going to solve these equations? Let me do one thing. Let me divide equation 2 with equation 1. If I'm dividing 2 with 1, R and R gets cancelled. So it's 2 on the left side. On the right side, this K and A gets cancelled. BB gets cancelled. So I'm left with 2 raised power Y on the right side. So from this particular equation, I can conclude Y value is nothing but Y value is 1. Yeah? Y value is 1. So I got the value of Y. I got the value of Y. Now similarly, if I divide equation 3 with equation 2, if I divide equation 3 with equation 2, so R gets cancelled, 8 by 2 comes RB 4 is equal. This 2B gets cancelled, A raised power X, A raised power gets cancelled, so I'll be only left with 2 raised power X. So when can be your LHS and RHS equal? LHS and RHS can only be equal if the value of X is 2, right? Wasn't I supposed to get these two values only? X and Y? So X I got to know as 2, Y I got to know as 1. So I would say the overall order of this particular reaction. Overall order of this particular reaction is going to be X plus Y. So 2 plus 1 comes out to be 3. I believe this is clear to everyone. I believe this is clear to everyone. Yeah? Perfect. Perfect, guys. Let's move on to one more question. My dear students, sometimes you'll be getting the question in this particular format. How do we solve this sort of a question? You are given with some rate law, but is it the simple rate law or complicated form of the rate law? In the simple rate law, like we have studied till now, there's only numerator. It is K concentration of A, concentration of B raised by X and Y, right? So it's not the simple rate law here. The rate law is given in a bit complicated form. The rate law is given a bit in complicated form. The reaction is also given. Calculate the order of the reaction. Number 1, if concentration of Br2 is kept very high. Number 2, if the concentration of Br2 is kept very low. See guys, how do we solve this particular question? Whenever you see a complicated rate law and imagine conditions like these are not specified. Whenever you see a complicated rate law like this and imagine these conditions are not specified, at that time you'll directly say order cannot be predicted. You'll directly say order cannot be predicted. But when the conditions are specified like this, then you can predict the order. And how exactly you can predict the order? Let's try to do the first question. You'll understand. See guys, as per the rate law, I would say R is equal to K1 multiplied by concentration of H2. And this is the concentration of Br2 whole raised power 1 by 2. Similarly, this is divided by concentration of Br2 plus K2 multiplied by concentration of HBr. This is the rate law that's given to me. Now look at the condition number 1. Condition number 1 says concentration of Br2 is kept very high. My dear students, if the concentration of Br2 is kept very high, if the concentration of Br2 is kept very high, and I say at that point of time, instead of Br2 plus K2 HBr, I can only write Br2. Why is that? As per the question, if the concentration of Br2 is kept very high, if Br2 is very high, that means you can neglect this term. If you can neglect this term, that means instead of these two, you can just write Br2, right? Now, write the rate law again. R is equal, this is K1, concentration of H2 raised power 1, concentration of Br2 whole raised power 1 by 2, divided by, instead of this entire term, I'll only write concentration of Br2. Correct? Now, take this Br2 up. When you take this Br2 up, it becomes Br2 raised power 1 by 2 minus 1 is minus 1 by 2. Perfect? Right? Clear till here? Now, my dear students, look at this particular rate law. Is it still looking complicated or it has become simple rate law now? It has become a simple rate law now. It's not complicated. And if it is a simple rate law, I would say order with respect to H2 is 1. Order with respect to Br2 is minus 1 by 2. So I would say the overall order of the reaction now is going to be X plus Y. The value comes out to be 1 by 2. Again, I'm repeating the same thing. If the conditions are not specified, at that time you'll say order cannot be calculated. Order cannot be predicted. If the conditions are specified, then you can calculate order like this. Similarly, look at the second part of the question. Look at the second part of the question. If the concentration of Br2 is kept very less, if the concentration of Br2 is kept very less, if the concentration of Br2 is kept less, if the concentration of Br2 is kept less, at that point of time, instead of Br2 plus K2 multiplied by HBr, what should I be writing? I'll be only writing K2 multiplied by HBr. Okay? Because Br2 concentration has been kept very less. This is less. If this is less, you can neglect this term. So now, my rate law, it becomes equal to R is equal to K1, concentration of H2, concentration of Br2 raised power 1 by 2. And in the denominator, what do we have? In the denominator, we only have now K2 multiplied by HBr. K2 multiplied by HBr. So R will be equal. K1 is a constant, K2 is a constant. Division of two constants will be one more constant, which I'm representing by K dash, right? And then you have got concentration of H2, then you have got concentration of Br2 raised power 1 by 2. Take this HBr up, it becomes concentration of HBr raised power minus 1. Now look at this rate law. Is it still looking complicated to you, or this becomes a simple rate law? It is a simple rate law now. It is the simple rate law now, people. So I would say order with respect to H2 here is 1, order with respect to Br2 is 1 by 2, order with respect to HBr is minus 1. So what do you think will be the overall order of the reaction? Overall order of the reaction now will be 1 plus 1 by 2 plus minus 1. The value comes out to be 1 by 2 only, because this term gets cancelled. The order of the reaction now also is going to be 1 by 2. Am I clear with this? Quickly, let me know in the chats, everybody. Yeah? Is it clear? Is it clear, people? Let me know. Perfect. I believe this is super clear to everyone. Okay. Now comes one more topic. What is that? That is experimental determination of order. How can we calculate order of the reaction experimentally? How can we calculate order of the reaction experimentally? Okay. My dear students, see, this particular topic I'll directly make you understand with the help of a question. Okay? I'll directly make you understand with the help of question, so that you'll exactly get to know how do we calculate order of the reaction experimentally. Look at the question strictly. You're given with a reaction and certain experiments have been carried out whose data is given to us. By looking at this particular data, we are supposed to get the order of the reaction. My dear students, one thing should be in your mind all the time. Whenever you are supposed to calculate order of the reaction, the first thing you're supposed to do, that write the rate law. Write the rate law. Okay? Write the rate law. Perfect. So, my first thing, I would be writing rate law for this particular reaction. When you write rate law for this particular reaction, you'll be writing R is equal to K, concentration of NO raised power X, concentration of H2 raised power Y. This is how my rate law looks like. Right? Right, people? Now understand. Look at experiment number 1. As per your experiment number 1, concentration of NO has been kept this much. Concentration of H2 has been kept this much. At that point of time, rate of the reaction comes out to be this much. Let's fit this data of experiment number 1 in our rate law. In our rate law. Fit the data of experiment number 1 in the rate law. So, as per experiment number 1, what is the rate? Rate of the reaction is 3 into 10 raised power minus 5 is equal to K. What is the concentration of NO? Concentration of NO in the first experiment is kept this much, raised by x. Concentration of H2 in the first experiment is 2.5 into 10 raised by minus 3 raised by y. This is your equation number 1. This is your equation number 1. Okay. Similarly, people, fit the experiment number 2 data in our rate law. As per experiment number 2, rate of reaction, R value is nothing but 9 into 10 raised by minus 5 is equal to K. What is the concentration of NO here? Concentration of NO here is 15 into 10 raised by minus 3 raised by x. Similarly, what is the concentration of H2 here? Concentration of H2 here is 2.5 into 10 raised by minus 3 raised by y. This is your equation number 2. Similarly, can we make equation number 3 here? Yes, we can do. We need to fit experiment number 3 data into our rate law. As per experiment number 3, what is the rate of the reaction? It is 36 into 10 raised by minus 5 is equal to K, you are writing as such. NO concentration has been kept as 15 into 10 raised by minus 3 raised by x. H2 concentration has been kept as 10 into 10 raised by minus 3 raised by y. This is equation number 3. So how many equations I got? I got 3 equations. My dear students, since I got 3 equations, now it's the time to solve these 3 equations. How exactly? Simple. Let me do one thing. Let me divide equation 2 with equation 1. If I divide equation 2 with equation 1, so this term and this term gets cancelled, right? K and K gets cancelled. 10 power minus 5, 10 power minus 5 cancelled. 9 by 3 comes out to be 3. 3 is equal to, right? 10 power minus 3, 10 power 15 divided by 5 is 3. So it's going to be 3 raised per x on the right side. Rest all the terms are cancelled. When you are dividing second by first, this is something which you get at the end. And from this particular expression, you can say x value is nothing but 1. So you got the value of x. You got the value of x. Now what is left? Y is left. How do we get the value of y? How do we get the value of y? If I divide third equation with the second one, if I divide third equation with the second one, see what all terms will get cancelled. This whole term and this whole term gets cancelled, right? 10 power minus 5, 10 power minus 5 cancelled. 36 divided by 9 is 4 is equal to 10 power minus 3, 10 power minus 3 cancel. 10 divided by 2.5 is 4, but this is 4 raised per y. So when can be 4 equal to 4 raised per y? When y value is equal to 1. So you got the value of x, you got the value of y. If you got the value of x as well as y, so I would say simply overall order of this particular reaction is going to be 1 plus 1 coming out to be 2. This is the general way of solving this sort of equation. This is a general way of solving this sort of equation. Now, there is one shortcut as well. There is one shortcut as well, which you can use and solve the question. See what is the shortcut exactly. See what is the shortcut exactly. First of all, do one thing. Write the rate law. R is equal to K, concentration of NO raised per X, concentration of H2 raised per Y. This is our rate law. Correct? This is our rate law. Now guys, understand. If you look at first and second experiment, in the first and second experiment, concentration of H2 has been kept same. Right? In the first and second experiment, H2 concentration is kept same. So imagine as if in the rate law, H2 is kept constant. Nothing to do with H2. But what is happening to concentration of NO? 5, 15. So NO concentration has been increased 3 times. When NO concentration has been increased 3 times, what has happened to the rate? Rate has become 3 and this is 9. Rate has become 3 times. Look carefully, guys. When H2 concentration is kept same, keeping H2 concentration same, keeping H2 concentration constant, by increasing the concentration of NO 3 times, rate is becoming 3 times. So by increasing this 3 times, rate is becoming 3 times. Keeping H2 same, by making this 3 times, this is becoming 3 times. What can we conclude from here? We can conclude the value of x is 1 because 3 raised power 1 comes out to be 2. If this x was 2, then 3 ka square would have been 9. If this x was 3, then 3 ka cube would have been 27. Right? But as per the given data, on increasing the concentration of NO 3 times, rate is becoming 3 times, which is only possible when the value of x is 1. Which is only possible when the value of x is 1. Correct? Right, people? Now, similarly, look at one more thing. If you look at experiment number 2 and experiment number 3, concentration of NO is kept fixed. Now, imagine concentration of NO is fixed. Concentration of NO is fixed in these two. What is happening to concentration of H2? 2.5 and 10. It is becoming 4 times. When concentration of H2 is increased 4 times, what is happening to rate? Initially it was 9 into something, now it is 36. So rate is also becoming 4 times. On increasing the concentration of H2, 4 times. Rate is becoming 4 times. On increasing, keeping NO concentration same, increasing this 4 times, rate is becoming 4 times, which is possible only if Y value is also 1, right? Because if Y was 2, then 4 ka square, rate should have increased 16 times, which is not the case here. I believe this particular stuff is clear to everyone. If yes, let me know once in the chats quickly. If yes, let me know once in the chats quickly. Okay? If yes, let me know in the chats quickly. Right, people? Is it clear, people? Quick. Is it clear? If this is clear, can you solve this sort of a question? By using the same trick? Can you solve this question with the help of same trick quickly? Waiting for you, waiting for you. See, I'll show you both approaches. Again, I'll show you both the approach of solving the question. Okay. See, guys. First thing, write the rate law for this particular reaction. And your rate law says that R is equal to K, concentration of NO raised power X, and concentration of Cl2 raised power Y. Okay? Cl2 raised power Y. This is your rate law. If this is the rate law, now there are some experiments which are given to me. Now fit the data of experiment number 1 in our rate law. And as per experiment number 1, rate of the reaction is R value is 1 into 10 raised power minus 3 is equal to rate constant. What is the concentration of NO in the first experiment? It is 0.05 raised power X. What is the concentration of Cl2 here? 0.05 raised power Y. Following this is equation number 1. Similarly, experiment number 2 data in the same rate law. And as per experiment number 2, rate of reaction R is nothing but 3 into 10 raised power minus 3 is equal to K. NO concentration is how much? 0.05 raised power X. And Cl2 concentration is 0.15 raised power Y. Equation 2. Equation 3. Equation 3. Rate of the reaction is how much? 9 in 10 raised power minus 3 is equal to K. Concentration of NO is how much? 0.15 raised power X. Concentration of Cl2 is 0.05 raised power Y. This is your equation number 3. So how many equations we got here? We got 3 equations. If we got 3 equations, just solve these 3 equations. How exactly? I'm dividing 2 with 1. When I divide 2 with 1, 10 power minus 3, 10 power minus 3 cancel. 3 by 1 is 3. On left side, I got 3. This term cancelled. 0.015 divided by 0.05. That comes out to be 3, but it's going to be 3 raised power Y, which is telling you that Y value is nothing but 1. Y value is nothing but 1. Now, after this, people, after this, what exactly we are going to do? For example, if I divide equation 3 with equation 1. If I divide 3 with equation 1, so 10 raised power minus 3, 10 raised power minus 3 cancel. 9 by 1 is 9 is equal to what all terms? This particular term cancel. 0.15 divided by 0.05, that's 3, but this is 3 raised power X, which is telling you that x value has to be 2. X value has to be 2. Then only 3 ka square comes out to be 9. If you got the value of x, you got the value of y. That means simply you can say the overall order of the reaction is x plus y. So 2 plus 1 comes out to be simply equal to 3. Okay? 2 plus 1 comes out to be simply equal to 3. Perfect. This was the general procedure. And I hope you can easily solve this question with the help of shortcut too. Yeah? Is it clear? It is simple, guys. It is simple. How come it's simple? NO concentration is kept same. This is increased 3 times. What is happening to rate? Rate is also increasing 3 times. So, when you are increasing the concentration of Cl2 3 times, rate is becoming 3 times, which is only possible if y value is 1. Then only by increasing this 3 times, 3 ka square, this also becomes 3 times. So y is 1. Similarly, if you look at first and third experiment, in the first and third experiment, Cl2 is kept same. Now, NO is increased 3 times. NO is increased 3 times. What has happened to rate? Rate has become 9 times. So when you are increasing this 3 times, rate is becoming 9 times. When you are increasing the concentration of NO 3 times, rate is becoming 9 times, which is only possible if 3 ka square comes out to be 9. So x value is 2. That's what we got. Yeah? That's what we got. That's what we got. I hope this is again clear to every one of you. Right, people? Am I clear till here? Are all the concepts clear? Can you let me know once in the chats? Can you let me know once in the chats, people? Quickly, let me know in the chats if all the things are clear till here. Everyone. Now comes one of the important topics of this chapter, that is your zero order reactions. Okay, understand this properly, guys, because this is very important. This is very important. Zero order reactions. What are zero order reactions? How do we define them? How do we define them? See, if you talk about the zero order reactions, I'll say these are the reactions. These are the reactions in which rate of the reaction is independent of the concentration of reactant. Rate of reaction is independent of the concentration of reactant. See, guys, understand what exactly I'm going to say. For example, imagine that you have got the reaction like this. A gives B. Let's assume the rate constant of this reaction is K. Let's assume order of this reaction. Since I've got only one reactant, if there is only one reactant, that means whatever is going to be order with respect to A, same is going to be the overall order of the reaction as well, because there is only one reactant. And let's say that overall order of the reaction is 0. So now I'll be calling this particular reaction as the zero order reaction. So it is my zero order reaction. Okay, it is my zero order reaction. Now, people, understand few things. It is my zero order reaction. Understand few things. I'm writing time t is equal to 0. What does it mean? At time t is equal to 0, the reaction has not started. If the reaction has not started, can I say the container in which reaction is going to take place? At time t is equal to 0, there will be only a reactant in the container, right? Product will be 0 because the reaction has not started yet. And let me assume the concentration of reactant initially is nothing but A0. This has to be 0. Initially, let's assume the concentration of reactant is A naught, the concentration of product is 0. Perfect. Now, when the reaction starts, what's going to happen? When the reaction starts, concentration of reactant is going to decrease with time. Concentration of product is going to increase with time. So let's assume at some time t, concentration of reactant left is AT and concentration of product formed is BT. So first of all, you have to be careful with all the terminologies which I have mentioned over here. What is A naught? A naught represents the initial concentration of reactants. A naught represents the initial concentration of reactant at time t is equal to 0. What is AT? AT represents the concentration of reactant. Concentration of reactant left at time t. Left at time t. What is BT? BT represents the concentration of product. The concentration of product formed. Concentration of product formed at time t. Right? Concentration of product formed at time t. Let me make you clear all this stuff again. Initially at time t is equal to 0, the concentration of reactant will be A naught. Right? The concentration of product right now will be 0 because the reaction has not started yet. Now, as the reaction starts, concentration of reactant will keep on decreasing. Let's say at some time t, the concentration of reactant left in the container is AT and the concentration of product formed is BT. Right? These are the few terminologies which you are going to remember from now on. A naught, AT and BT. Okay? Now, my dear students, understand. First of all, I'm assuming that order of this particular reaction is 0. If the order of this reaction is 0, tell me one thing. Can I write rate law for this reaction? Rate law. R is equal to K. This is concentration of A. Since order is 0, so A raised power 0. Right? Now, people, is there any other way to calculate rate? Yes, differential form of rate. We have studied in the beginning. Right? What will be the rate of reaction with respect to A? It's going to be minus 1 upon stoichiometric coefficient, 1 upon 1, change in the concentration of A divided by dt. This term is also going to give you the rate of reaction. This term is going to give you the rate of reaction. This is going to give you the rate of reaction as per differential form. This is giving you the rate of reaction as per rate law. Correct? So, you can just equate these two. When you equate these two, it's going to be K. So, anything raised power 0 is 1. This dt is going to be on this side now. This is going to be minus d of A. Or you can simply say dA is equal to minus k dt. dA is equal to what? dA is equal to minus k dt. So if dA is equal to minus k dt, understand, I'm going to make one important equation here. Guys. D of A is equal to minus k dt. Let me just do one thing. Let me integrate from this side as well as this side. Here I'm integrating with respect to time, and time is going from 0 to t. Time is changing from 0 to t. Here you are integrating with respect to concentration of A, right? At time t is equal to 0. What was the concentration of A? At time t is equal to 0, the concentration of A was A naught. At time t, the concentration of A is, at time t, the concentration of A is AT. So I got the limits as well. Right? If I ask you what is integral of dx, integral of dx is x. So integral of dA means A. Integral of dA means A. Lower limit A naught, upper limit AT is equal to minus k comes out. Integral of dt is t, upper limit, lower limit. So it has to be t only. Okay. So it is going to be upper limit AT minus lower limit A naught is equal to minus kt. So I got one important equation. AT is equal to A naught minus kt. This equation I'll be using in all the questions of the zero order kinetics. And this equation I'll be calling as the integrated rate equation. This is something which I'll be calling as the integrated rate equation for what? For zero order reactions, right? Integrated rate equation for the zero order reactions. Perfect, right? This equation is going to relate T with A naught with AT. This equation will be used in order to solve almost all the questions of the zero order kinetics. I believe it's clear to everyone. Okay. So people, what is the zero order reaction? The reaction whose order is zero. Order zero means rate becomes independent of concentration of reactant. Rate becomes independent of concentration of reactant in case of zero order. Any such reaction whose rate does not change on changing the concentration of reactant, you'll be calling that a zero order reaction. As simple as that. Okay. So my first equation is AT is equal to A naught minus KT. This was my first point when it comes to the zero order reactions. Now, there are a few more points, and at the end, we'll be solving the questions then. Point number two. Point number two is something which you call as half-life. What about the half-life in case of zero order? Half-life, I'll be representing with either T half or I'll be representing it with T 50%. How do we define the term half-life? How do we define the term half-life? How do we define the term half-life? Simple. See, if I write the definition, the time taken to complete, the time taken to complete, the time taken to complete 50% of the reaction. The time taken to complete half of the reaction, 50% of the reaction, is something which you'll be calling as half-life of the reaction. Okay, have a look. For example, I've got the reaction like this. A gives B. Let's say its rate constant is K, and I'm assuming order of this particular reaction is 0. Okay. Initially, at time t is equal to 0, its concentration will be A naught. This will be 0. Now, my dear students, as the reaction starts, with the time, the concentration of reactant is going to decrease. Concentration of reactant is going to decrease with time. Can I say at time t is equal to, at t is equal to T half. At t is equal to T half. 50% reaction would have got completed. What is half-life? Time taken to complete 50% of the reaction. So at t is equal to T half, 50% of the reaction has got completed. What does that mean? That means 50% of reactant has got converted into products. That means 50% of reactant has got converted into product at time t is equal to T half. What is meant by 50% of reactant converted into product? Initially, the concentration of reactant was A naught. Now 50% of this amount has got converted into product. What is 50% of this amount? 50% of A naught means how much? That means A naught by 2. That means A naught by 2. Initially, I took A naught as the concentration of reactant. Now, at this time, at half-life, 50% of reactant has got converted. So, I would say from A naught by 2 has got converted into product. If from A naught by 2 has got converted, so how much will be left? How much reactant will be left? A naught minus A naught by 2, which comes out to be A naught by 2 only. This is the concentration of reactant left at half-life. This is the concentration of reactant left at T half. My dear students, I got one condition. At T is equal to T half, the concentration of reactant left, which is represented by AT, that's equal to A naught by 2. Okay? Because AT represents what? Concentration of reactant left. So concentration of reactant left at half-life is nothing but A naught by 2. Now, if I use this particular condition in the integrate rate equation, integrate rate equation is what? AT is equal to A naught minus KT. This is the equation valid for zero order reactions. Now, in this particular equation, if I use this condition, so what do I be writing? What I'll be writing? Instead of AT, I'll be writing A naught by 2 is equal to A naught minus K. Instead of T, I'll be writing T1 by 2, right? So from this particular expression, I can calculate T half. T half is equal to A naught divided by 2K. One more important expression. Half-life in case of zero order reactions. This is going to be the time taken to complete half of the reaction. This is going to be the time taken to complete 50% of the zero order reaction. Remember these expressions directly. AT is equal to A naught minus KT, first expression. Second, T half is equal to A naught divided by 2K. A naught divided by 2K. Now, the third parameter for the zero order. The third parameter for the zero order. That's what you call as completion time. That's what you call as completion time, represented by T 100%. Now, how do you define this particular completion time? What is meant by the term completion time? Guys, it's again very simple. Completion time. Completion time is defined as simply the time taken Completion time is simply defined as the time taken to complete 100% of the reaction. The time taken to complete 100% of the reaction. See, what was your half-life? Time taken to complete 50% of the reaction. Time taken to complete half of the reaction. What is going to be our completion time? The time taken to complete 100% of the reaction. Now look at the screen carefully. See guys, for example, you have got the reaction A gives B. I'm assuming its rate constant is K, and at the same time, I'm assuming order of this reaction is 0. Then only I'll be calling this as the 0 order reaction. Yeah? Now, initially at time t is equal to 0, the concentration of reactant is A0. This has to be 0. Correct? Initial concentration of reactant, we always represent with A0. Now, with time, when the reaction starts, concentration of reactant is going to decrease with time. Right? Because the reactant will keep on getting converted into product. If I say at time t is equal to t 100%, what does it mean? It means this is the time at which 100% reaction has got completed. This is the time at which 100% reactant has got converted into product. Now people, if 100% reactant at this time has got converted into product, how much reactant would be left? Nothing, because entire 100% has got converted into product. I'm left with nothing at completion time. And concentration of reactant left is represented by what? It is represented by AT. So again, I got a condition. The condition is at time t is equal to 100%. At time t is equal to 100%, AT is equal to 0. Now, my dear students, what is our integrated rate equation? Integrated rate equation is AT is equal to A0 minus KT. Just do one thing. Use this particular condition in this expression. Instead of AT, you are going to write 0. This is going to be A0 minus K. Instead of T, you are going to write T half. I would say, sorry, not T half. This is going to be T 100%. Perfect. So I would say our T 100% is nothing but it is equal to A0 divided by K. This is the third expression, which is for the 0 order reactions. My dear students, time taken to complete 100% of the 0 order reaction is equal to A0 by K. What was the time taken to complete 50% of the reaction? Time taken to complete 50% of the reaction was A0 by 2K. A0 by 2K. This was the time taken to complete 50% of the reaction. And similarly, time taken to complete 100% of the 0 order reaction. How much that is? A0 by K. If I call this as equation 1, calling this as equation 2, let me divide 1 with 2. If I divide 1 with 2, I would be getting T 100% is equal to 2 times the T 50%. What does it mean? What does this particular result mean? This particular result means that a 0 order reaction is 100% completed. A 0 order reaction is 100% completed in. A 0 order reaction is 100% completed in how many half-lives? It is completed in 2 half-lives. It is completed in 2 half-lives. Okay? Remember this particular point as well. This can be asked in your exam, right? Okay? Am I clear with this? Time taken to complete 100% of the 0 order reaction. That's always equal to 2 times the time taken to complete 50%. Let's say you have got a 0 order reaction, which is getting complete in 10 minutes. Sorry. Let's say you have got a 0 order reaction. Okay? Its half-life is 10 minutes. Its half-life is 10 minutes. How much time does it take to complete 100% of the reaction? Quick. If the half-life of the 0 order reaction is 10 minutes, how much time will it take to complete 100% of the reaction? 2 times half-life, 2 into 10, 20 minutes. Right? It will take 20 minutes to complete 100% of the reaction. Is it clear? Is it clear, people? Yeah? Perfect. So this was the third parameter when it comes to what? Zero order reactions. The first parameter was the integrate rate equation in the zero order reactions. Then comes the half-life of the zero order reactions. Then comes completion time in the zero order reaction. Now, the fourth parameter. The fourth parameter. What is that? That is degree of dissociation. Degree of dissociation alpha in case of zero order reactions. How do we calculate degree of dissociation alpha? My dear students, recently in chemical equilibrium, I've taught you what is degree of dissociation. It is simply equal to number of moles of reactants dissociated into products divided by initial moles of reactants, right? Number of moles of reactants dissociated into products divided by initial moles of reactants. Do you remember? This is how we calculate alpha. Alpha is always equal to number of moles of reactants which get dissociated into products divided by initial moles of reactants. Now imagine like this. Let's say you got the reaction A gives B. Rate constant K. Order of the reaction is 0. Okay? Order of this reaction is 0. Let's say at time t is equal to 0. For example, at time t is equal to 0. Let's assume the initial moles of reactants are A0. I'm assuming the initial moles of reactants are A0. This has to be 0. At time t, let's assume moles of reactant left is going to be 80, right? Earlier, I used to call this A0 as initial concentration of reactant. I can call it as initial moles of reactant as well. Okay? These are the initial moles of reactants. These are the moles of reactants left at time t. Now tell me one thing. If I want to calculate alpha, alpha is Nd divided by Ni. What is Nd? These are the number of moles of reactants which got converted into product. Can you let me know how many moles of reactant got converted into product? I started with A0 moles of reactant. I'm left with 80 moles of reactant. So how many moles of reactant got converted into product? I start with A0. I'm left with 80. So A0 minus 80. Can I say these are the moles of reactant which are getting converted into product? Divided by. What are the initial moles of reactants? Initial moles of reactants are A0. So this is going to be A0. What is 80? 80 is A0 minus KT. So A0 minus KT. Instead of minus plus KT. Divided by A0. So A0 cancels. So my final expression is going to be KT divided by A0. This is how you calculate alpha for the zero order reaction. Right? For the zero order reaction, A gives B. So it is KT divided by A0. This is the value of alpha. This is the value of alpha, right? For that zero order reaction, right? In which A is getting converted into B. So this question is directly asked, what is the value of alpha for the zero order reaction A gives B? So you should be remembering these expressions directly. Okay? In the examination hall, you should not be, solving it and getting the value of alpha. No, you should be remembering. These expressions should be on the tip of your tongue. So this was the fourth parameter which can be asked directly in case of zero order reaction. Okay? Let's have a look on the fifth parameter. Let's have a look on the fifth parameter. Dear students, for example, you have got the reaction A gives B, whose rate constant is K and its order is 0. So this reaction follows zero order kinetics. Now understand. Let's say at time t is equal to 0, its initial concentration is A0. Let's say at time t is equal to 0, the initial concentration of reactant is A0, right? This will be surely 0. Let's say at some time t1, the concentration of reactant left is AT1. At time t2, the concentration of reactant left is AT2. Okay? These are few things which I'm assuming. Let's say at time t is equal to 0, the concentration of reactant is A0. Let's say at time t1, the concentration of reactant left is AT1. At time t2, the concentration of reactant left is AT2. Now understand. Understand one thing. First of all, in this time interval, 0 to t1, in this time interval, the concentration of reactant is going from A0 till AT1. Right? Sir, electrochemistry part 3 video. Electrochemistry is complete in 2 parts only. Why do you need part 3? There are only 2 parts in electrochemistry. Okay. See guys, what I'm trying to say, in 0 to time t1, the concentration of reactant is changing from A0 to AT1. Similarly, in the time interval, this 0 to T2, 0 to T2 time interval, the concentration of reactant is going from A0 till AT2. There are two time intervals, 0 to T1, 0 to T2. 0 to T1, it is that time interval wherein the concentration of reactant is going from A0 till AT1. 0 to T2, it is that particular time interval wherein the concentration of reactant is going from A0 till AT2. For example, if they ask you the question, how long will it take for the concentration of reactant? How long will it take for the concentration of reactant to go from AT1 to AT2? That means at that time, you're asked about this particular time interval, which is T2 minus T1, right? Which is T2 minus T1. I hope you're getting what I'm trying to say. For example, if they ask you, how much time does it take for the concentration of reactant to go from AT1 to AT2? That means this time interval they're asking. This one, from T1 to T2. Right? So which time interval exactly? They're asking about this time interval delta T, which I'm representing with T2 minus T1. Okay? And in this particular time interval, I would say the concentration of reactant is going from AT1 till AT2. So here, in order to solve this particular question, I would be giving you one direct expression. I'm not deriving that, right? Let me give you one direct expression by means of which you can solve this sort of equation. The expression at that time will be AT2 is equal to AT1 minus K delta T, which is T2 minus T1. This is the expression which you'll be solving in order to calculate the time interval delta T wherein the concentration of reactant is going from AT1 till AT2. This again, one important question. From this particular expression, you'll be getting one important question. So this was my fifth parameter. This was my fifth parameter, guys. Remember this. Now, let's have a look on the sixth parameter, on the zero order reactions. What is my sixth parameter here? Sixth parameter is going to be simple, units of rate constant. Units of rate constant. And you know, the units of rate constant K for the zero order reactions is nothing but, it's going to be moles, liter inverse, second inverse. Or you can say it is ATM second inverse. If time is in seconds, pressure is in ATM, etc., etc. This is my sixth parameter for the zero order reactions. Now, the seventh parameter. The seventh and the important parameter. Understand. For example, you have got the reaction like this. A gives B. Let's say this is the reaction. Okay. Now, for example, people, if you have got the reaction A gives B, whose rate constant is K, and let's say a table in this format is given to us. A table in this format is given to us. A table is given to us like this. A table is given to us, for example. Let's say the table is like this. Here I'm writing concentration of reactant. Here I'm taking time. Concentration of reactant in moles per liter, or I can say molar, for example, time in seconds. Okay, which is understood. Concentration in molar, moles per liter, and time in seconds. Time in seconds. See guys. Well, this can be concentration of reactant. This can be pressure of reactant. This can be moles of reactant. Remember this, guys. This can be here concentration of reactant, it can be moles of reactant, or it can be pressure of reactant. And over here, just to make you understand, let's say at time T1, let's assume the concentration of reactant was A1. Let's say at time T2, the concentration of reactant was A2. Let's say at time T3, the concentration of reactant left was A3. Let's say at time T4, the concentration of reactant left was A4. Understand what exactly I'm saying. Understand what exactly I'm saying. Let's say you are given with a reaction and a table like this is given to me. And it's mentioned that at time T1, the concentration of reactant is A1. At time T2, the concentration of reactant left is A2. At time T3, the concentration of reactant left is A3. At time T4, the concentration of reactant left is A4. Okay, now understand. If, for example, if the time interval is same, if time interval is same, what is meant by same time interval? Same time interval means if T2 minus T1, if T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3. This is what I call a same time interval. From here to here, here to here, here to here. If the time interval is same. Remember guys, if in the same time interval, A2 minus A1 comes out to be same as that of A3 minus A2, comes out to be same as that of A4 minus A3. If in the same time interval, A2 minus A1 is equal to A3 minus A2 is equal to A4 minus A3. At that point of time, I can say these concentrations of reactants, their common difference is same. If their common difference is same, I can say they are forming arithmetic progression. And remember, this arithmetic progression is formed in case of zero order reactions only. So at that point of time, you can say the order of the reaction is zero. Right? This is one more way of checking the order of the reaction. If you are given with the table, if in the same time interval, the concentrations of reactants, if they are forming the arithmetic progression, if their common difference is same, at that point of time, directly you are going to say order of the reaction is nothing but zero. Okay? But if, for example, A2 by A1 comes out to be equal to A3 by A2, which comes out to be equal to A4 by A3, at that point of time, I cannot say common difference is same. I'll have to say common ratio is same. I'll have to say common ratio is same. And remember, common ratio is same. Common ratio of these concentration of reactants is same. That means they are not forming arithmetic progression right now. They are forming geometric progression. And remember, geometric progression is formed in case of first order reactions. Remember, geometric progression is formed in case of first order reactions. So you need to remember this stuff as well. Okay. If in the same time interval, concentrations of reactants, they are forming arithmetic progression, then it's going to be your zero order reaction. If they are forming geometric progression, then it's going to be the first order reaction. I believe this is clear. I believe this is super clear to everyone. Is it? Is it, people? Is it, people? Quick. Yeah? Perfect. Let me know quickly in the chats. This was one more very important point. Okay, this was point number 7. Now let's have a look on point number 8. What will be the point number 8? Yes, point number 8 will be like this. Concentration of product. Concentration of product formed at some time t. Concentration of product formed at time t. It's also one simple thing. For example, you have got the reaction again as A gives B, whose rate constant is K, and I'm assuming order of this particular reaction is 0. Now, for example, at time t is equal to 0, its concentration will be A0, this will be 0. At some time t, the concentration of reactant has to be what? AT. The concentration of product has to be BT. Sometimes they'll ask you, what is the concentration of product formed at time t? Basically, they're asking about this. Calculate the concentration of product formed at time t. Now think about it. Concentration of product formed at time t. Concentration of product formed at time t. See guys, the initial concentration of reactant was A0. The concentration of reactant left at time t is AT. So I started with A0. I'm left with AT. So if I take the difference, can I say this particular concentration of reactant, A0 minus AT, this is the concentration of reactant that has got converted into product. So I would say concentration of product at time t will be equal to A0 minus AT. Simple. A0 minus AT. I started with A naught concentration. How much I'm left with? I'm left with 80. So A naught minus 80, it is going to give me that concentration of reactant which has got converted into product. That's something I'm supposed to calculate. Concentration of product at time t. So A naught minus 80. I would say BT is equal to A naught minus. What is 80? 80 is A naught minus KT. Minus minus becomes plus. So A naught cancelled. So concentration of B at time t is nothing but K multiplied by T. This is one more expression which I would want you guys to remember. For the zero order reaction, A gives B. If you have got the zero order reaction, A gives B. If they ask you to calculate concentration of product formed at time t, it is simply equal to K times T. That's it. I'll show you a lot of questions based on this in some time. Okay, this was the 8th expression related to what? Zero order reactions. Now ninth point related to zero order reactions. What is that? These are going to be some important graphs. Some important graphs related to zero order reactions. Some important graphs related to zero order reactions. And what are these important graphs which are related to zero order reactions? Let's have a look. First graph I'm going to make between rate of reaction versus the concentration of reactant. The concentration of reactant. This is going to be my first graph. Second one. The second graph is going to be between AT versus T. AT versus T. Third graph is going to be between T half versus A naught. T half versus A naught. Next graph is going to be between T 100% versus A naught. Next graph is going to be between alpha versus A naught. Alpha versus A naught. Is there any other graph which we can make? Just a second. Alpha A naught, T 100%, T half, 80. Okay. Yeah, these are the graphs which we can make over here. See guys. First of all, rate versus concentration of reactant. What do you think will be the nature of the graph? Rate versus concentration of reactant. You know, in zero order reaction, R is equal to K, concentration of reactant raised power 0. So rate is independent of concentration of reactant. A raised power 0 is 1. So rate is independent of concentration of reactant. So if you change the concentration of reactant, if you increase or decrease the concentration of reactant, nothing is going to happen to the rate. So constant, right? AT versus T. You know, in case of zero order reactions, AT is equal to A naught minus KT. Now, AT right now you are plotting along y-axis. T you are plotting along x-axis. This becomes your M. The sign here is minus. And this is C. So y is equal to minus mx plus C. Remember, y is equal to minus mx plus C. What has to be the nature of the graph? Y is equal to minus mx plus C. Straight line with negative slope. And what about the slope here? Slope will be equal to minus K. What about the intercept here? Intercept from here to here is nothing but A naught. It is going to be A naught. I believe this clear. T half versus A naught. You know, T half is nothing but A naught divided by 2K. Or you can say A naught multiplied by 1 by 2K. T half is equal to A naught by 2K. Now T half you are plotting along y-axis. Okay. A naught you are plotting along x-axis. So 1 by 2K becomes my M. Y is equal to mx. Straight line passing through origin. Its slope has to be equal to how much? Its slope has to be equal to 1 upon 2K. Similarly, this is also going to be a straight line. But its slope is going to be 1 upon K. 1 upon K. Alpha versus A naught. For zero order reactions, alpha is equal to KT divided by A naught. Now, alpha and A naught, they are inversely proportional. They are inversely proportional. And whenever you are supposed to make a graph between two variables which are inversely proportional, the nature of the curve is going to be hyperbola. So these are the graphs which can be plotted when it comes to the zero order reactions. This was the 9th parameter. And my dear students, the 10th parameter. The 10th parameter. Where is that? The 10th parameter. Just a second. The 10th parameter. This is our 10th parameter, which you are going to remember directly when it comes to the zero order reaction. This is going to be our 10th parameter. Examples of the zero order reactions. The first example, that is photochemical reaction between H2 and Cl2. This is the pure example of the zero order reaction, right? Second, decomposition of NH3 over molybdenum. Decomposition of NH3 over molybdenum, right? Decomposition of Hi over gold. These are the common three examples. These are the common three examples of what? These are the common three examples of the zero order reaction. Okay? Perfect. Perfect, guys. Is all the stuff clear? Guys, anything can be asked out of these 10 parameters which are related to zero order reactions. This is your first one, integrated equation. Then comes your half-life. Then comes your completion time. Then comes your degree of dissociation. Then comes your 81, 82. Then comes your these particular parameters. Then concentration of B at time t. Graphs related to zero order, right? And the examples which are related to the zero order kinetics. I believe this is clear. I believe this is clear. Okay. Should we take a break here or should we solve its questions first? What do you think? Should we take a break here or should we solve its questions first? Questions of zero order. What do you want? Break here or questions first? A lot of students are asking for questions, so let's complete the questions first, then we'll go for the break. After questions, we'll go for the break. Let me just remove certain slides here, which are of no use to us because we have discussed all this. This is done, this is done. All right. Look at the first question, guys. Look at the first question here. Look at the first question here. Look at the first question here. Understand? See how exactly I'm going to approach towards the questions. Okay, and remember the approach, that's important. Remember the approach, that's important. We'll take a break at 10:30 now. Okay, have a look. Understand. As per the reaction we have got, as per the question, we have got a zero order reaction A gives B. As per the question, we have got a zero order reaction A gives B. Order of the reaction is 0. Okay. Let's say its rate constant is K, and let's say the initial concentration of reactant is A0. This is going to be 0. Now, as per the question, it was observed at the end of an hour. It was observed at the end of an hour. At t is equal to 1 hour. At t is equal to 1 hour. 75% of A has reacted. What does that mean? That means 75% of A has got converted into product. 75% of A has reacted means 75% of A has got converted into product. What does that mean also? I took A0. 75% of A0. 75% of A0 has got converted into product, which means 3/4 of A0. Initially, I took A0. This was the amount of reactant. Now, from this much amount of reactant is getting converted into product. So, how much am I left with? A0 minus 3/4 A0. A0 minus 3/4 A0 comes out to be A0/4. I would say this is the concentration of reactant left at 1 hour. and concentration of reactant left, we represented with AT. This is my condition number 1. This is my condition number 1. So I got to know, I start with A naught. Now, as per the question, after 1 hour, I would say 25% of reactant has got converted. Sorry, 75% of reactant has got converted into product. So I'll be left with only 25% of reactant. 25% of reactant means 25% of reactant means A naught by 4. Right? This will be the concentration of reactant left after 1 hour. What are they saying? At what time, as per the question, at what time A will be 10% unreacted? At what time A will be 10% unreacted? What does that mean? That means at what time A will be 10% left. 10% left means 10 by 100 into A naught. 10 by 100 into A naught means A naught by 10, right? So at what time A will be 10% left, right? 10% left means concentration of reactant left right now will be A naught by 10. Okay? So this is going to be my AT right now. So how many conditions I got? I got 2 conditions. Condition number 1. Sir, do you know Chaitanya sir? Which Chaitanya sir? Where is he from? I might be knowing, but I don't exactly remember. If you give me some hints, maybe I'll be remembering. What does he teach and where he teaches? Okay, look at this now. As per the question, 2 things were given. The first thing was, at time t is equal to 1 hour, 75% of A has reacted. That means 25% of A is left. At what time 10% of A will be left in the container? This is the question. Now guys, what is our integrated rate equation? That is AT is equal to A naught minus KT. Perfect. That is AT is equal to A naught minus KT. What I'll be doing? First of all, I'll be using this condition here. As per this condition, AT is equal to how much? A naught by 4 is equal to A naught minus K. T is equal to how much? 1 hour. So from this particular equation, K comes out to be equal to 3 by 4 A naught. So first of all, by using condition number 1, I got K. Now, use the second condition in the same equation. AT here is nothing but A naught by 10 is equal to A naught minus K value I've already calculated, 3 by 4 A naught, multiplied by what? Multiplied by T, multiplied by this T, which we are supposed to calculate. So A naught is cancelled. So what are we left with? 1 by 10 is equal to 1 minus 3 by 4 multiplied by T. So 3 by 4 multiplied by T is going to be equal to 1 minus 1 by 10, which comes out to be 9 by 10. So I can say 3 by 4 multiplied by T is equal to 9 divided by 10, or 3, 1, 3, 3, 4 3s are 12. 12 by 10 is 1.2. And since time is mentioned in hours, so this is going to be the time. Did you understand? I would say at 1.2 hours, the concentration of reactant left will be 10% of the initial. 10% of the initial. At 1.2 hours, the concentration of reactant left will be A naught by 10. So it would take 1.2 hours for the concentration of reactant to reduce from A naught till A naught by 10. Till A naught by 10. Okay? I believe this is clear. If this is clear, go for this one. If this is clear, go for this one. Solve it. Kill it. And you should be in a position to solve this one as well. Understand how? As per the question, imagine that you have got the reaction A gives B. And as per the question, it's mentioned it follows a zero order kinetics, right? It is a zero order reaction. Now, initially at time t is equal to 0, its concentration is A naught. This has to be 0. Now, in the question, they are mentioning that a zero order reaction is 20% complete in 10 minutes. So, at t is equal to 10 minutes, the reaction is 20% completed. What does that mean? That means 20% of the reactant has got converted into product. 20% of the reactant has got converted into product. So, how much reactant will be left? 80% of reactant will be left. 80% of what? 80% of this amount. 80% of A naught will be left. So 80% of A naught means 0.8 A naught. This is the concentration of reactant left at 10 minutes. This is my condition number 1. Now, at what time it will be 80% completed? 80% completed means at what time 80% of reactant would have got converted into product? When 80% reactant gets converted into product, I think I'll be left with only 20% of reactant. 20% of what? 20% of A naught, which means 0.2 A naught, right? So at this particular point of time, this is the concentration of reactant left. At what time concentration of reactant is going to be 0.2 A naught. Now, we know the procedure. What is our procedure here? What is our procedure here? The procedure is write the integrated rate equation. AT is equal to A naught minus KT. First, use the first condition. In the first condition, AT is nothing but 0.8 A naught is equal to A naught minus K. What is the value of T? 10. So K will be equal to, from this particular equation, K will be equal to how much? 0.2 A naught divided by 10. So I got the value of K. Now, put the second condition here in this particular expression. AT is 0.2 A naught is equal to A naught minus K is already 0.2 A naught by 10 multiplied by T, which we are supposed to calculate, right? So A naught and naught cancelled. So when you solve, T value comes out to be 40. So I would say it will take 40 minutes. It would take 40 minutes to complete 80% of the reaction. It would take 40 minutes to complete 80% of the reaction. Yeah? Right, people? It would take 40 minutes to complete 80% of the reaction. I believe this is clear. Yeah? Perfect. Let's move on to one more question. Look at this one. Look at this one, guys. This question says that calculate the rate constant for the reaction. I'm giving the reaction. Reaction is A gives B. This is the reaction, zero order reaction, and a table is given. The table is simple. At time t is equal to 0, concentration of reactant is 1 molar, right? And at time t is equal to 0, concentration of reactant is basically represented by A naught. Technically, A naught is given to me as 1 molar. Look at this. At 120 seconds, concentration of reactant is 0 molar. What does that mean? That means this is the time when 100% of reaction is being completed. So T 100% is given to me as per the question. 120 seconds. What am I supposed to calculate? Rate constant K. It's simple. T 100% is nothing but A naught by K. And A naught by K is nothing but 120. So K will be equal to A naught divided by 120. A naught is already 1. 1 divided by 120. And its units are going to be, since it's zero order, moles, liter inverse, second inverse. This is the answer of the question. Yeah? Isn't it clear? Isn't it clear, people? This was one basic question. See, at time t is equal to 0, concentration of reactant was given. Right? Right, people? Okay. Now, similarly, at 120 seconds, concentration of reactant is 0 molar. What does that mean? At 120 seconds, concentration of reactant is 0 molar. That means entire reactant has got converted into product. Entire reactant has got converted into product. Okay? If entire reactant has got converted into product, so there will be no reactant left at 120 seconds. Yeah? Am I clear with this? Okay? So, technically, I'm given with the completion time. Completion time is equal to 120 seconds and T 100% is equal to A naught by K, and it's done. Perfect, guys? All right. Try to solve this question. Try to solve this question, guys. Quick. T half for the zero order reaction is 1 hour. Let's say we have got the reaction like this. A gives B. It is mentioned in the question that the reaction follows the zero order kinetics. And its half-life is equal to 1 hour. Its half-life is equal to 1 hour. Okay. Initial concentration of reactant at time t is equal to 0. Concentration of reactant is equal to how much? 2 molar. How much time does it take for its concentration to reduce from 0.5 molar to 0.25 molar? See, initially the concentration of reactant is 2 molar. Let's say at time t1, the concentration of reactant would have reached 0.5 molar. Similarly, at further some time t2, the concentration of reactant left would be 0.25 molar. Now they are asking me how much time does it take for the concentration of reactant to go from 0.5 to 0.25. That means this time interval t2 minus t1 they are asking. They are asking about the time interval t2 minus t1. They are asking about this time interval delta t, which is nothing but t2 minus t1. If you remember, I already gave you one direct expression to solve this question. If you remember, I gave you an expression, AT2 is equal to AT1 minus K, T2 minus T1. They are asking us to calculate the time taken, to calculate the time in which the concentration of reactant goes from 0.5 molar to 0.25 molar. So from 0.5 to 0.25. That means which time interval that is? This is 0 to T1. This is 0 to T2. So T2 minus T1 means this particular time interval. In this particular time interval, the concentration of reactant changes from 0.5 to 0.25 molar. Right? Now, half-life is given to me as 1 hour. Half-life means A naught by 2K. So A naught by 2K is equal to 1 hour. So from here you can calculate K. K is equal to A naught by 2. And A naught as per the question is 2. So 2 by 2 is equal to 1. And its units are going to be moles, liter inverse, R inverse. Because time is given in hours, I think. Yeah, exactly. So I got the value of K first of all. If you got the value of K, put all the values here in this expression. AT2 is 0.25. AT1 is 0.5. Minus K is 1. T2 minus T1 I have to calculate. So T2 minus T1, which I'm representing with delta T, right? This is equal to, it will be 0.25 hours. So it will take 0.25 hours. It will take 0.25 hours for the reactant to reduce its concentration from 0.5 molar to 0.25 molar. Am I clear with this one as well? Am I clear with this one as well? Quickly in the chats, everybody. Quickly in the chats, everybody. The rate constant of the reaction A gives B. The rate constant of the reaction A gives B. I'm given with the reaction A gives B, whose rate constant K is equal to 0.6 into 10 raised power minus 3 moles liter inverse second inverse. So this is the basically a zero order reaction because units of rate constant are moles per liter per second. So it's a zero order reaction. Now, if the concentration of A is 5 molar, what will be the concentration of B at 20 minutes? At T is equal to 20 minutes, what would be the concentration of B? So they are asking about the concentration of product at time T. Have I given you the direct expression? Direct expression I've given you long back. Concentration of B at some time is nothing but K multiplied by T. Simple. Right? What is K? K is given to me as 0.6 into 10 raised power minus 3 moles per liter per second. What is T? T is 20 minutes. They're asking you to calculate the concentration of B at 20 minutes. Right? Concentration of B at time T is equal to K into T, where T is 20 minutes. So 20 multiplied by 60, so that this term comes in seconds. Because this particular K was in moles per liter per second, that's why I took time also in seconds. And when you solve this, I think this value comes out to be 0.72 molar. Right? This is the concentration of B which is formed at 20 minutes. Perfect, guys? Is it clear? One last question of zero order. Here you might do a mistake. The reaction here is 2 times A gives P. Half-life of the reaction is given to me as 120 seconds. Okay. Initial concentration of the reactant A naught is given to me as 2 molar. What am I supposed to calculate? I'm supposed to calculate rate constant of the reaction. Now, I know normally you will think like this. T half is nothing but T half is A naught divided by 2K. This is the normal thinking procedure of majority of the students. A naught is 2 divided by 2K, it comes out to be 120. So they will think that rate constant of the reaction is equal to 1 upon 120. Is that? And time is given in seconds. So it will be moles, liter inverse, second inverse, right? And a lot of students will mark this answer as the correct answer. But this is not the correct answer. Why is that? My dear students, if you remember the expressions which I gave you, all the expressions which I gave you. For example, if I start from here, this is the integrated rate equation valid for the reaction A gives B, wherein stoichiometric coefficient of the reactant is A. This is the half-life of the zero order reaction when the stoichiometric coefficient of the reactant is 1. But here in this question, in this particular question which I'm solving right now, what is the stoichiometric coefficient of reactant? It is 2. Whenever you see such kind of the question, wherein stoichiometric coefficient of the reactant is not 1, it is other than 1. At that time, in all these expressions, wherever you see K, that is not the rate constant of the reaction. At that time, it is basically the rate constant of disappearance of A. At that time, it is the rate constant of disappearance of A. Whenever you see such kind of the stuff, wherein the stoichiometry of the reaction is other than 1, at that time, wherever you see K, that is not the rate constant of the reaction. That is going to be the rate constant of disappearance of A. And if you got the rate constant of disappearance of A, right? You know, rate constant of disappearance of A is nothing but rate constant of reaction multiplied by stoichiometric coefficient of A. So I can say rate constant of reaction is equal to Ka divided by stoichiometric coefficient of A. What is Ka? Ka is how much? That is 1 upon 120. What is stoichiometric coefficient of A? That is 2. So 1 upon 120 divided by 2 comes out to be 1 upon 240. This is going to be moles, liter inverse, second inverse. This is going to be the rate constant of the reaction. Remember this particular question. Okay. And with this, we'll take a break. And then we are going to start the first order kinetics. I hope the zero order kinetics is completely clear to you. So let's have the dinner break. It's 10:23. Let's meet up at 11. Huh? But I would want every one of you to be back at 11. I would want every one of you to be back at 11, okay? Right? All right, people, I would want every one of you to be back exactly at 11. Till then, you guys can have your dinner. I'll have my dinner too. Right? Chalo, I'll see you after the break. Is everyone back? Is everyone back or not? Is everyone back or not? Let me know in the chats quickly. Yeah. So guys, tell me in the chats, what all things we have discussed till now. Is every single thing clear to everyone? Let me know in the chats quickly. Let me know in the chats quickly if all the things are like super clear to every one of you. And after that, we shall be starting the first order kinetics. Yes. Sir, please update the short revision videos also. Surely, why not? Surely, let's start that series as well. Short revision. Entire chapter in 10 minutes, 12 minutes, like that. We want that? Are you talking about that short revision series? Like entire revision of the chapter in like 10, 20 minutes, like that? Sure, why not? Let's do that. Let's start that from day after tomorrow. All right, then. Let's get going. Let's get started with the first order reactions. Okay. What are, first of all, the first order reactions? How do we define the first order reaction? This is, I would say, the most important topic of the chapter, right? Dear students, let me tell you, whenever question is framed from kinetics, most of the times from the kinetics chapter, the question is framed from this particular topic, that is the first order reaction. Okay, so consider this as the most important topic of the chapter. Let's try to analyze this particular topic and let's try to understand things. And over here, I'm not going to derive any results. I'll just give you the results and I'll show you how to apply them, right? Like in zero order, we derived every result, but here we are not going to derive the results. I'll be giving you the results and we shall be applying those results in the questions. Okay. So first of all, what is the first order reaction? Any reaction whose order is 1. Any reaction whose order is 1, right? Or in other words, I'll say these are the reactions. I would say these are the reactions in which rate of the reaction varies linearly with the concentration of reactant. Varies linearly with the concentration of reactant. Varies linearly with the concentration of reactant if there is only one reactant. If there is only one reactant in the reaction. For example, see what it means. Let's say you have got the reaction like this. A gives B. Okay? A gives B. I'm assuming its rate constant is K. And since there is only one reactant, so I would say whatever is going to be order with respect to A, that is going to be the overall order of the reaction as well, which I'm assuming as 1. Let's say the order of the reaction is 1. Okay? Now, my dear students, again the similar things. Let's say at time t is equal to 0, the concentration of reactant initially is A naught. This is going to be 0. And now as the reaction starts, concentration of reactant keeps on decreasing and concentration of product that keeps on increasing. Let's say at time t, the concentration of reactant left is AT and the concentration of product formed is BT. Okay. The first thing, since I'm assuming this particular reaction in which only one reactant is involved, right? I'm assuming order of the reaction is 1. If order of the reaction is 1, can't we write the rate law for the reaction? R is equal to K, concentration of reactant raised by order 1. This is the rate law for the first order reaction that is given to me. A gives B. Okay. Number 1. Number 2. My dear students, like we derived the integrated rate equation for the zero order reactions, right? Similarly, over here we have got integrated rate equation for the first order reactions as well. And I'm not deriving that now. I'm just going to give you the expression. And we'll see how to apply those expressions. So the first form of the integrated rate equation, or before talking about the first form of the integrated rate equation, since this is the rate law, right? Can I say as per this rate law, rate of the reaction varies linearly with the concentration of reactant? What does that mean? That means if you double the concentration of reactant, rate of the reaction will double. If you triple the concentration of reactant, rate of the reaction will triple. If you make this 4 times, this becomes 4 times. If you make this 5 times, this becomes 5 times. So rate of reaction is varying linearly with the concentration of reactant. Okay. Now, the first form of the integrated rate equation for the first order reactions. What is that? That is the ln of AT is equal to ln of A naught minus KT. This is the first form of the integrated rate equation of the first order reactions. Number 1. We have got different forms of the integrated rate equation here. Now, one more is going to be log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This is one more form of the integrated rate equation in case of the first order reactions. So till now, I got 2 forms. There are many more, right? The third form of the integrated rate equation of the first order reactions. What is that? That I'll be writing like this. Ln of let me write it like this. K is equal to 1 divided by T ln of A naught divided by AT. This is one more form of the integrated rate equation in case of the first order reaction. Similarly, there is one more form. What is that? K is equal to 2.303 divided by T, and it's going to be log of A naught divided by AT. This is one more form of the integrated rate equation of the first order reaction. Similarly, the fifth one. The fifth one is going to be AT is equal to A naught e raised power minus KT. This is the fifth form of the integrated rate equation of the first order reaction. So in total, I must say we have got 5 different forms of the first order integrated rate equations. Okay. In zero order, there was only one form. AT is equal to A naught minus KT. Here we have got 5 different forms when it comes to the integrated rate equation of the first order kinetics. Okay. Similarly, my dear students, the 6th point, that is half-life. Do you remember the half-life? What is meant by half-life? We have discussed it. Time taken to complete 50% of the reaction, right? Time taken to complete 50% of the reaction. In case of first order reactions, let me tell you the half-life, its expression is 0.693 divided by K. This is how you calculate half-life of the first order reaction. Okay. This is how you calculate half-life of the first order reaction. In case of zero order, half-life used to be A naught divided by 2K. I hope you remember. Okay. Now, the 7th point here, that is the completion time. 7th point in case of first order, that is the completion time. Completion time in case of first order reaction, 300%. Now, this is something which needs a bit of explanation. Okay. This is something which needs a bit of explanation. First of all, how have we defined the completion time? Completion time is defined as time taken to complete 100% of the reaction. You know it already, right? Time taken to complete 100% of the reaction. For example, understand properly. Let's say you have got the reaction A gives B, whose rate constant is K. I'm assuming order of this particular reaction is 1. It follows the first order kinetics. Let's say at time t is equal to 0, the initial concentration of reactant is A0. This is 0, right? Now, my dear students, if I say at t is equal to t 100%, what does that mean? That means I'm talking about the completion time. When 100% reaction would have got completed. When 100% reactant would have got converted into product. And you know, when 100% reactant would have got converted into product, I'll be left with nothing. So this is the concentration of reactant left at t is equal to 100%. This is the concentration of reactant left at t is equal to 100%. And you know, concentration of reactant left is represented by AT. Now, my dear students, understand. If you remember your integrated rate equation used to be K is equal to, one of its forms was 1 by T ln of A0 divided by AT. Okay? Or, let me do one thing. Let me use this condition in this particular expression. What do I get? Let me write T here. Instead of T, I'll be writing T 100% is equal to 1 by A here ln of A0 as such. What is the value of AT here? AT value is 0. AT value is 0. Now, my dear students, division by 0 is infinite. So, can I say this whole term is coming out to be infinite? The 100% is approaching towards infinity. What does that mean? What does this particular point mean? It means that a first order reaction takes infinite time to get 100% completed. A first order reaction takes infinite time to get 100% completed. So, in other words, I can say a first order reaction. In other words, I can say a first order reaction never undergoes 100% completion. A first order reaction never undergoes 100% completion. I would say a first order reaction takes infinite time for 100% completion. Do remember this particular point. This is important. Okay? This can be directly asked as a theoretical question. So how many parameters we got till now? We got 7 parameters. Now, the 8th parameter in case of first order. 8th parameter in case of first order. That is, how do we calculate degree of dissociation here? How do we calculate degree of dissociation in case of first order reaction? Degree of dissociation alpha. And if you remember, how do we calculate alpha? How do we calculate alpha? It is equal to number of moles of reactants which get dissociated into products divided by initial moles of reactants. Number of moles of reactants dissociated into products divided by initial moles of reactants. For example, have a look. Let's say you have got the reaction A gives B, whose rate constant is K, and I believe order of this particular reaction, for example, is 1. Okay. For example, at time t is equal to 0, the initial moles of reactants are nothing but A0. A0 represents here the initial moles of reactant. Okay. And moles of product right now would be 0. Now, you know, as the reaction starts, moles of reactants are going to decrease with time. Let's say at some time t, the moles of reactant left are equal to AT. AT represents here the moles of reactant left. Right now, I'm talking in terms of moles. I'm calling this A0 as the initial moles of reactant. I'm calling this AT as moles of reactant left at time t. Okay. Now, people understand. If I want to calculate alpha, alpha is equal to number of moles of reactants dissociated into products divided by initial moles of reactants. Now, if I ask you how many moles of reactants got dissociated into products, understand. Initially, I took A0 moles of reactant. Now, I'm left with 80 moles. I took A0. I'm left with 80. So, how many moles of reactants got converted into product? I'll say initially, I took A0. Now, I'm left with 80. So, A0 minus 80. These are the moles of reactant which got dissociated into product. Divided by initial moles of reactant is nothing but A0. Now, my dear students, A naught minus. What is AT? Few minutes back, I gave you one expression. AT is equal to A naught e raised power minus KT. Divided by what? Divided by A naught. So can I say A naught, A naught, A naught gets cancelled out, and I'll be getting the direct expression as 1 minus e raised power minus KT. So remember this particular expression directly. In case of first order reactions, alpha is nothing, that is 1 minus e raised power minus KT. In case of your zero order, what was alpha? Alpha was KT by A naught. In case of zero order, alpha was KT by A naught. Here, the alpha is 1 minus e raised power minus KT. My dear students, in this particular expression, which is valid for which reaction? It is valid for first order reaction. If you talk about the zero order reaction, in case of the zero order reaction, what was alpha? Alpha was equal to KT divided by A naught. So in case of zero order reaction, alpha was dependent on A naught. But in case of first order reaction, alpha is independent of A naught. Remember this particular point as well. Remember the degree of dissociation. Remember the degree of dissociation. The degree of dissociation of a first order reaction is independent of what? Is independent of the initial concentration of reactant. Whereas in case of zero order, it was dependent. Here it is independent. This is one more important point, and this is the direct expression which you will be remembering. Alpha is equal to 1 minus e raised power minus KT. Am I clear till here? Am I clear till here? This was alpha, guys. This was alpha in case of the first order reaction. This was the 8th point. Now the 9th point. 9th point in case of the first order reactions. What is that? That is time taken to complete X% of the first order reaction. How much time does it take to complete X% of a first order reaction? This X can be anything. 20%, 10%, 30%, 40%, 60%, right? How much time does it take to complete 25% of the reaction? How much time does it take to complete 40% of the first order reaction? How much time does it take to complete 90% of the first order reaction? So in general, I'm writing time taken to complete X% of the first order reaction. I'm directly giving you its expression. I'm directly giving you its expression without the derivation, because derivation is of no use to us. Remember the expression, and I'll show you how to apply it in the questions. So time taken to complete X% of the first order reaction is equal to 2.303 divided by K log of 100 divided by 100 minus X. Okay, this is one very, very, very important expression. For example, I'm asking you, calculate the time taken to complete 20% of the first order reaction. That means put the value of X as 20 here, put the value of X as 20 here. Solve the question. Time taken to complete 40% of the first order reaction. Put the value of X as 40 here, put the value of X as 40 here. You'll be getting the answer, which I'll show you in the questions in some time, right? Am I clear till here? This was time taken to complete X% of the reaction. One thing if you realize, guys, one thing if you realize, in this particular expression, do you see A naught anywhere? There is no A naught anywhere in this result. What does that mean? That means a certain percentage. That means a certain percentage of the first order reaction. Or let me write it like this. Let me write it like this. Time taken to complete. Time taken to complete. A certain percentage of a first order reaction. Time taken to complete a certain percentage of a first order reaction is independent. Is independent of what? Is independent of the initial concentration of reactant. Is independent of the initial concentration of reactant. Now you must be thinking what is meant by this particular point. Must be thinking what is meant by this particular point. See guys, this particular point is important. Why is that? Have a look. For example, I'm writing a reaction like this. A gives B. Okay. Its rate constant is something, right? Let's say when the initial concentration of reactant was 10 molar. I'm assuming this is the first order reaction. Let's say when the initial concentration of reactant was 10 molar, Let's say at that point of time, it was observed that 20% of the reaction was getting completed, for example, in 50 minutes. Let's say when the initial concentration of reactant was 10 molar, at that point of time, for example, 20% of the reaction was getting complete in 50 minutes. Now, in the same reaction, if I keep the initial concentration of reactant as 20 molar, can you let me know the same 20% of the reaction would be getting complete in how much time? I would say, again, the 20% of the reaction would be getting complete in 50 minutes only, because of this particular statement. Time taken to complete a certain percentage of reaction. That is independent of initial concentration of reactant. Here I had kept 10 molar. Here I had kept 20 molar. But still, a certain percentage of the reaction will be getting completed in same time. But remember, this is valid only for which reaction? It is valid only for the first order reactions. This is a super important point, which will make your question solving easy. You will see that in some time. Right? Perfect. So this was our 9th parameter. Let's have a look on the 10th one. My dear students, some direct expressions which I'm going to give you, which will ease out a lot of things. Have a look. Remember them. Remember, time taken to complete 75% of the first order reaction, it's always equal to 2 times the half-life. That means 75% of the first order reaction is getting completed, will be getting completed in how many half-lives? 2 half-lives. This is one direct expression. This will be very useful in question solving, this particular expression, right? Similarly, time taken to complete 87.5% of the first order reaction, it's always equal to 3 times the half-life, right? This again one more important expression. Similarly, time taken to complete 99.9% of the first order reaction is equal to the 10 times half-life. Okay, this is again one very important expression. Perfect. So is it clear till here, guys? Is it clear? Let me know once in the chats. Quickly, let me know in the chats, quick. Yeah? Perfect. Here I'm going to give you one more expression. Time taken to complete 99% of the first order reaction is equal to 2 times the time taken to complete 90% of the reaction. Remember this particular expression as well. And all these expressions are basically valid for what? All these expressions are basically valid for first order reactions. Direct expressions from which direct questions will be asked. Now, the 11th part. What is that? That is, how do we calculate concentration of product at some time t? How do we calculate concentration of product at time t? Understand. Simple. How do we calculate concentration of product at time t? See guys, for example, you have got the reaction A gives B, whose rate constant is K, and it's following the first order kinetics. Let's say at time t is equal to 0, its initial concentration is A0, this is 0, right? Let's say at some time t, concentration of reactant left is AT, concentration of product formed is BT. Perfect. Now, for example, they're asking me to calculate concentration of product formed at time t. Basically, they're asking me to calculate the value of BT. BT represents concentration of product formed at time t. Now, how do we do it? See guys, the initial concentration of reactant was A0. At time t, concentration of reactant left is AT. I started with A0, I'm left with AT. So A0 minus AT. And I say, this is the concentration of reactant that got converted into product. I started with A0, I'm left with AT. So A0 minus AT, this gives me that concentration of reactant which got converted into product. Convert into product means this is basically going to give you the concentration of product at time t. Concentration of B at time t. Now, you can use it like this, A0 minus AT, you already know for the first order, that's A0 minus KT, right? So this is going to be one direct expression, which you can remember to calculate the concentration of product formed at time t. So how many expressions till now? 11 expressions. Now, the 12th one. The 12th one, guys. The 12th one. That is important. Okay, from that, this particular expression which I'm going to give you, a direct question will be asked. Let me first of all make the expression. For example, you have got the reaction like this. A gives B, rate constant is K, order of the reaction is 1. So it's a first order reaction. Let's say at time t is equal to 0, initial concentration of reactant is A0. So product will be 0. Let's say at some time t1, the concentration of reactant left is AT1. Okay, and let's assume at this particular point of time, rate of reaction was R1. Let's say at time t2, the concentration of reactant left is AT2 and rate of reaction at this particular point of time is R2. You know, in case of first order reactions, rate of reaction depends on the concentration of reactant. Now in first order, when concentration of reactant decreases with time, therefore rate of the reaction also will decrease with time. In case of first order reaction. In case of first order reaction, rate is directly proportional to concentration of reactant. If the concentration of reactant is decreasing with time, so rate of reaction will be decreasing with time too. Right? Right, people? Now understand. First of all, I'm going to mark certain time intervals. 0 to t1. This is the time interval wherein the concentration of reactant changes from A0 to AT1. This is the time interval 0 to t2 in which the concentration of reactant goes from A0 to AT2. For example, if they ask you in what time interval, concentration of reactant goes from AT1 to AT2. In what time interval the concentration of reactant goes from AT1 to AT2? That means they're asking about this time interval, which is T2 minus T1. So which time interval they're asking? Delta T, that represents T2 minus T1. So how do we get this time interval? To calculate this time interval, again, I'm going to give you one direct expression. What is that direct expression? Remember that. K is equal to 2.303 divided by T2 minus T1. It's going to be log of AT1 divided by AT2, or you can write it like this. 2.303 divided by T2 minus T1, it's going to be log of R1 divided by R2. These are the two expressions which are used to calculate the time interval in which the concentration of reactant goes from AT1 till AT2. If you remember in zero order reactions, what was that expression? This is the expression which is valid for first order reactions. In case of zero order, K used to be equal to what? In case of zero order, expression used to be AT2 is equal to AT1 minus K delta T, which was T2 minus T1. This was the expression for zero order. This was the expression for zero order reactions. And this is now the expression for the first order reaction. I'm not deriving it. I'm just giving you the expression. You are going to remember it. Okay? Right, people? So this was my 12th important point. Now comes one more. 13th. That is calculation of the concentration of reactant left. Calculation of the concentration of reactant left after n half-lives. After n half-lives. See guys what it means. For example, you have got the reaction like this. A gives B. Rate constant K. Reaction follows the first order kinetics. It is a first order reaction. Okay. Now we will tell me one thing. Let's say you have got the reaction A gives B. Okay. Let's say I'm telling you its half-life is 10 minutes. For example, I'm telling you the half-life of this reaction is 10 minutes. So, I'm for example asking you, what is the amount of reactant left after 30 minutes? I'm asking you to calculate the amount of reactant left after 30 minutes. Right? I'm telling you one thing, that half-life of this reaction is 10 minutes. Tell me, what is the amount of reactant left after 30 minutes? First of all, if the half-life of the reaction is 10 minutes, can you tell me this 30 minutes means how many half-lives exactly? 10 minutes means 1 half-life, 20 minutes means 2 half-lives, 30 minutes means 3 half-lives. So technically, I'm supposed to calculate the concentration of reactant left after how many half-lives? After 3 half-lives. Do you understand this? Technically, I'm asking you to calculate the amount of reactant left after how many half-lives? After 3 half-lives. Okay. Similarly, my dear students, in general, if I say, how do we calculate the concentration of reactant left after n half-lives? First of all, how do we calculate number of half-lives? I told you we have got 3 half-lives here. We are given with 3 half-lives. How did I calculate it? T divided by T half. T divided by T half came out to be 3. Right? T divided by T half came out to be 3. Perfect. So I would first of all say number of half-lives. Number of half-lives is equal to total time divided by T half. Total time divided by T half. And this number of half-lives I'll be representing with n. Now, amount of reactant left after n half-lives. Amount of reactant left after n half-lives. It's always equal to A naught divided by 2 raised power n. This is one very, very, very important expression whose significance you will understand in some time. Right? One very important expression. This is how you calculate the amount of reactant left, concentration of reactant left after n half-lives. Okay? Right? So this was my 13th parameter when it comes to the first order reaction. Now, one more. That is 15th. This one is simple, you know it already. What are the units of rate constant in case of first order reactions? You know it, unit of rate constant is nothing. It is but units of time raised power minus 1. So it can be second inverse, minute inverse, hour inverse, month inverse, year inverse, whatever inverse, right? So this is the unit of the rate constant. Now similarly, there are some important graphs. Related to the first order reactions. Please take a note of these graphs as well because they are super important from which questions will be framed, which you will understand in some time. The first graph which I'm plotting is between rate of the reaction versus concentration of reactant. Can you let me know what will be the nature of the graph? In case of first order reaction, rate of reaction is equal to rate constant and concentration of reactant raised power 1. This is the rate law for the first order reaction. Now rate you are plotting along y-axis, concentration of reactant along x-axis. This becomes your m, y is equal to mx. Straight line passing through origin, right? So what about the slope of this particular curve? Slope of this particular curve means m, and m value is nothing but k. This is my first graph. Second graph, if I want to plot, that is between ln 80 versus t. My dear students, since you know, in case of your first order reactions, ln of 80 is equal to ln of A naught minus KT, right? Now this ln of 80 you are plotting along y-axis, t you are plotting along x-axis. So this becomes your m. The sign here is minus. This becomes c. Y is equal to minus mx plus c. Y is equal to minus mx plus c. It's a straight line with a negative slope, right? Straight line with a negative slope, and slope here, as you can see, slope here is equal to minus k, right? This was my second graph. Similarly, the third graph which I can plot in case of first order reactions, that is between log of k versus t. And you know the equation, log of 80 is equal to log of A naught minus k divided by 2.303 multiplied by t. Now this log of 80, you are plotting along y-axis, time you are plotting along x-axis. This entire term becomes your m, sign is minus, and this is c. Y is equal to minus mx plus c. Again, a straight line with a negative slope. So slope of this particular curve is nothing but slope is equal to minus k divided by 2.303. So these were the three graphs till now. Now, the fourth one. If I ask you, what will be the graph between half-life versus A naught? Half-life versus initial concentration of reactant. You know the expression already. Expression is T half is equal to 0.693 divided by K. So, if you look at this particular expression, is the half-life of the reaction dependent on the initial concentration of reactant? No, not in case of first order reactions. So, on changing A naught, nothing happens to half-life. So, it remains independent. Perfect. Similarly, if I want to make a graph between alpha and A naught, between alpha and A naught. In case of the first order reactions, alpha is equal to, few minutes back we derived, alpha is equal to 1 minus e raised power minus kt. Alpha is equal to 1 minus e raised power minus kt. So alpha is independent of A naught again. So a straight line. Okay. For example, if I want to draw a graph between AT versus T. My dear students, you already know AT is equal to A naught e raised power minus kt. Right? AT you are plotting along y-axis. T you are plotting along x-axis. So the format of this equation is y is equal to e raised power minus x. Y is equal to e raised power minus x. So y is equal to e raised power minus x will be exponentially decreasing. Exponentially decreasing, right? Exponentially decreasing. Perfect. Now, one question if I ask you, can this graph touch the time axis anytime? Can this graph touch the time axis? The answer is a big no. Why is that? Because if this graph touches the time axis, at that point, AT value will be 0. AT is equal to 0 means concentration of reactant left is 0. Concentration of reactant left is 0 means what? Means 100% of reaction has got completed. But a first order reaction never undergoes 100% completion. So this graph is never going to touch the time axis. Do you understand this? Okay. So these are all the important graphs which can be framed in case of the first order kinetics. You can make a lot of other graphs as well. It is just you should know how to draw the graphs. All the other graphs you can easily make. Perfect. I believe it's all clear. And if it is all clear, there is one more thing which I would want to give you here. What is that? Just give me a second. That is examples of the first order reactions. This is something which is directly asked. Which of the following is the example of the first order reaction? This is my 7th parameter. Examples of the first order reaction. You have to remember them directly. You have to remember them directly because any reaction will be given and they'll ask you what is the order of the reaction. These are some important reactions of the first order. Like we had 3 important reactions in 0 order. Photochemical reaction between H2Cl2, that was the example of 0 order. Decomposition of NH3 over molybdenum, that was the example of 0 order. Decomposition of Hi over gold, that was the example of 0 order. Similarly, these are 4-5 reactions which are directly the examples of first order, right? You have to remember them. A memory-based question can be asked out of these examples. Okay? Now, since we have discussed all the terminologies, all the results related to the first order, now we are fit enough to solve the questions based on the first order, right? Let's try some questions of the first order kinetics so that you'll understand them properly. Just a second, let me remove certain slides here because this is something which we have discussed in the handwritten format. Okay. You are going to tell me the answer of this question. Look at the question, read the question carefully and solve it. Read the question carefully and let me know its answer quickly. Quickly, people. Quickly, everyone. The concept behind this particular question I already gave you. Concept behind this particular question I already gave you. Quick. Everyone, give it a try. There is no calculation needed in this question, by the way. If you remember the concept that I gave you a few minutes back, there's no calculation needed in this question. Without using pen and paper, you should be in a position to solve. Without using pen and paper, you should be in a position to solve this. Exactly. The answer of this question is 73%. Amazing. Good. Have a look. As per the question, imagine you have got the reaction that's A gives B. This is the reaction. Now, in the question they are saying, when the initial concentration of reactant was kept 200 molar, at that point it was observed that 73% of the reaction was getting completed in 100 minutes. 73% of the reaction was getting completed in 100 minutes. And the reaction was given to me as first order. The reaction is first order. Now, in the same reaction, what they are doing? In the same reaction, they are keeping the initial concentration of reactant as 600 molar. Right? They are keeping the initial concentration of 600 molar. And they are telling you, they are asking you, what do you think in 100 minutes, how much percentage of reaction would be getting completed? Your answer will be same 73%. Right? Time taken to complete a certain percentage of the reaction that is independent of the initial concentration of reactant. Right? Whatever you want to keep, whatever initial concentration of reactant you want to keep here, same percentage of reaction will be always completed in same amount of time, right? But only in case of first order reactions. Okay, perfect. I believe this is fine. I'm moving on to one more question. Even this particular question, this should not take more than 20 seconds to solve now. A first order reaction is 75% completed in 100 minutes. First order reaction is 75% completed in 100 minutes. Calculate the time taken for 87.5% completion. This should not take more than like 20 seconds to solve. What do you think? See guys, imagine the first order reaction is given to me like this, A gives B. Let's say this is the first order reaction. As per the question, it's mentioned that time taken to complete 75% of the reaction is equal to how much? Is equal to 100 minutes. Now they're asking us to calculate the time taken to complete 87.5% of the reaction. This is to be calculated. This is given, this is to be calculated. Now how exactly you're going to solve this? See guys, it's simple. Time taken to complete 75% of the first order reaction is equal to 2 times the half-life, right? Few minutes back only I gave you an expression. So from this particular expression, T half will come out to be 50 minutes. So you got the half-life. Since you got the half-life, time taken to complete 87.5% of the reaction is equal to 3 times the half-life. So it is 3 times 50. That means 150 minutes. So it will take 150 minutes for the 87.5% completion of the first order reaction. I hope this is clear. Okay. All right. Moving on to one more. Look at this particular question. Look at this particular question, guys. The question is for an elementary reaction. Oh my God, just a second. Okay. Can you all hear me? Can you all hear me? Say yes or no. Can you all hear me? Quick. Is the mic working fine? All right. Look here then. As per the reaction, we are given with an elementary reaction, X gives Y plus Z. In the question, it's mentioned that the reaction is elementary, right? If the reaction is elementary, we have discussed already, for the elementary reaction, order is equal to molecularity. What is molecularity of this reaction? 1. So I would say order of this reaction will be 1 also, right? Because, you know, for the elementary reaction, order is equal to molecularity. So molecularity is 1, so the reaction is first order. Its half-life is given to me, T half. T half of the reaction is 10 minutes. So first of all, from T half, we know T half is equal to 0.693 divided by K. It is equal to 10. So I would say K will be equal to 0.0693. Now the units of K will be minute inverse. So I got the rate constant of the reaction. Now in the question, they are mentioning that in what period of time would the concentration of X be reduced to 10% of its original value? In what period of time would the concentration of X, would the concentration of reactant be reduced to 10% of initial value? So how much percentage of completion they are asking? They are asking about 90% completion. They are asking about how much time does it take to complete 90% of the reaction. Do you understand that? Because when 90% reaction gets completed, at that point itself, 90% of reactant would have got converted into product. So I'll be left with only 10% of reactant. So technically, they're asking to calculate time taken to complete 90% of the reaction. And you know, time taken to complete X% of the reaction is equal to 2.303 divided by K. It is the log of 100 divided by 100 minus X, right? And the value of X here is 90. So I would say time taken to complete 90% of the reaction is equal to 2.303. K value already we have calculated, 0.0693. Log of 100 divided by 100 minus 90 is 10. So 100 minus 90 is 10. So 100 divided by 10 is 10. Log 10 is 1, right? So log 10 is 1. Solve this and get the answer in minutes. That's all, right? So people are saying the answer is coming out to be 33 minutes. So okay, so let me write it as 33 minutes. So it will take 33 minutes for this particular reaction to get 90% completed. Okay? Perfect. Now similarly, let's move on to one more question. See guys, an organic compound undergoes a first order decomposition. Right? An organic compound undergoes a first order decomposition. Time taken for its decomposition to 1/8 and 1/10 of its initial concentrations are this and this respectively. Calculate T1/8 divided by T1/10 multiplied by 10. It's again a simple question only. See. Let's say the reaction is like this. A gives B. It is following the first order kinetics, whose rate constant is K. Initially at time T is equal to 0, for example, the concentration of reactant is A0. This will be 0. Now they are mentioning at time T is equal to T1/8. At time T is equal to 1/8. This is the time at which the concentration of reactant has reduced to 1/8 of its initial value. So at T1/8, concentration of reactant will be A0 divided by 8. This is the concentration of reactant left at T is equal to T1/8. Similarly, they are giving you one more time, that is T1/10. And they are telling you this is the time at which the concentration of reactant has reduced to 1/10 of its initial value. So the concentration of reactant here is going to be A0/10. The concentration of reactant left here will be A0/10. So these are the two conditions which I got here. If these are the two conditions which I got here, dear students, what is my integrate rate equation? The general form of integrate rate equation is T is equal. One of the expressions is like this, 2.303 divided by K. It is log of A0 divided by 80. Okay. If I put this condition here in this expression, so instead of T, I'll be writing T1/8 is equal to 2.303 divided by K log of A0 divided by. What is the value of 80 here? 80 is A0 divided by 8. A0 cancel, 8 comes up. If 8 comes up, so 8 can be written as 2 raised power 3. 8 can be written as 2 raised power 3, which can be written as 3 log 2. 3 log 2. It can be finally written as 3 log 2. Log 2 is 0.3. So 0.3 multiplied by 3 is 0.9. So in short, I'll be writing it just multiply by 0.9. Right? Similarly, if I put this particular condition in this expression, instead of T, I'll be writing T1/10 is equal to 2.303 divided by K. It is the log of A0 divided by. What is the value of 80 here? 80 value is A0/10. So A0 cancel. Log 10 comes out to be 1, right? Log 10 comes out to be 1. Perfect. Now, what am I supposed to calculate? I'm supposed to get this value. T1/8 whole divided by T1/10 multiplied by 10. This value I'm supposed to get, right? This value I'm supposed to get. What is T1/8? T1/8 is this. T1/10 is this. If you divide them, this term gets cancelled. So you're only left with 0.9 multiplied by this 10. The value comes out to be 9 exactly. The answer of this particular question is coming out to be 9. Is it clear? Is this question clear to everybody? Let me know in the chats quick. Okay. Similarly, guys, look at this one. Look at this one. For the first order reaction, choose the correct value of half-life. Choose the correct value of half-life. The reaction is first order, and for the first order reaction, you know, half-life is equal to 0.693 divided by K. So I just need the value of K. For that, some graph is given us. Graph is given to us. Graph is between log 80 versus T. So from this particular graph, I need the value of K first of all. From this particular graph, I need the value of K. If you remember, few minutes back, we have drawn this graph, log 80 versus T. And we have mentioned that slope of this particular graph between log 80 versus T was minus K divided by 2.303. This used to be its slope. Now, what is slope basically? Slope is tan of theta. What is theta? Theta is the angle that this particular graph makes with the positive x-axis in the anti-clockwise direction. So this is theta here, 135. So tan of 135 is how much? Tan of 135 is minus 1. Minus 1 is equal to minus K divided by 2.303. So I would say K comes out to be equal to 2.303. I think time is given in minutes. So K units will be directly in minute inverse. So if you got K, you are done. It will be 0.693 divided by K. K is 2.303. I think the answer will be 0.3 minutes. Right? Perfect. So this is how you are going to calculate half-life for this particular, for the reaction whose graph is given to me. Well, they can ask you one more thing here. They can ask you to calculate time taken to complete 99.9% of the reaction. That will be simply equal to 10 times the half-life. Since you have calculated half-life, just multiply that with 10, get T 99.9%. Similarly, get T 75%. That will be 2 times half-life. Get T 87.5%. That will be 3 times half-life. Since you have calculated the half-life, now you can easily calculate all the other things. What do they ask you? My point is you should be in a position to solve this sort of equation on your own. Okay. Moving ahead. Moving ahead. Look at this particular question. This is one more type of the question that can be asked. The question is the rate constant of the first order reaction. We are given, for example, with a first order reaction A gives B, its rate constant is given to us as 1.386 minute inverse. Okay. Calculate the concentration of reactant left after 8 minutes. Calculate the concentration of reactant. Concentration of reactant left at time t is basically 80. Concentration of reactant left at time t is nothing but 80. So 80 we have to calculate. We have to calculate the concentration of reactant left after 8 minutes. And you know 80 is nothing but it's A0 divided by 2 raised per n. A0 divided by 2 raised per n. And we have to get the answer in terms of A0. Let me tell you. The answer has to be in terms of A0. So in order to calculate 80, what do I need? I need n. What is n? N is total time divided by t half. Total time divided by t half. I think something is missing in this question. I feel something is missing in this particular question. I believe so. There should be one graph given. There should be some graph given, I believe. Or let's see first of all whether we can solve. No, there is no need of graph here. Why is that? Because in this particular question, K is already given to us. If K is given, you can easily calculate half-life. And half-life is nothing but 0.693 divided by K. Right? So it is 0.693 divided by K. K value is your 1.386. The value comes out to be how much? 1 by 2. So 0.5. So half-life is 0.5 minutes. If you got the half-life, total time divided by T half. Total time is 8 minutes. Half-life is 0.5. So how many half-lives are we given with? We are given with 16 half-lives. So as per the question, we are supposed to calculate the concentration of reactant left after 8 minutes, or you can say after 16 half-lives, because I converted these 8 minutes into a number of half-lives and I got to know 8 minutes means 16 half-lives. So technically they can ask you the question in two formats. First one, they can ask you to calculate the concentration of reactant left after 8 minutes, or they can ask you directly to calculate the concentration of reactant left after 16 half-lives. So it's going to be A0 divided by 2 raised power 16 molar. This is the concentration of reactant left. Either you say after 8 minutes or you can say after 16 half-lives. Am I clear with this? Yeah? Did you understand this particular question? Did you understand this particular question, people? Everybody? Let me show you one more similar sort of question so that it becomes properly clear. What amount of reactant for the first order reaction will be left after 3.5 minutes? You have to again give the answer in terms of A naught. You have to give the answer in terms of what? You have to give the answer in terms of A naught. So right now, as per this particular question, what amount of reactant is left? That means AT we have to calculate, right? And you know AT is equal to A naught divided by 2 raised power n. Perfect. N is nothing but it is total time divided by T half. Total time divided by T half. And as per the question, total time is given to me as 3.5 minutes. 3.5 minutes divided by T half. So basically, we have to calculate the concentration, the amount of reactant left after 3.5 minutes. So first of all, I'll check it out that this 3.5 minutes means how many half-lives. I'll convert it into number of half-lives. Number of half-lives means total time divided by T half, right? Total time is given to me as 3.5. Now, I just need to calculate first of all the half-life. Half-life for the first order reaction, you know, that is 0.693 divided by K. Now, in this question, K is not given, but K we can calculate. K we can calculate from here. This is ln AT versus T graph. Ln AT versus T, its slope is always equal to minus K. We have discussed this. Slope is nothing tan of theta. This theta will be 45, 90, 45. So this is 135. So tan of 135 will be minus 1. Minus 1 is equal to minus K. So K is equal to 1 minute inverse. If you got K, that means you got the half-life, 0.693 minutes. If you got the half-life, you can calculate number of half-lives. Total time, that is 3.5 divided by T half is 0.693. So it is 5 half-lives. So over here in this particular question, 3.5 minutes will represent 5 half-lives. So technically, you are supposed to calculate the amount of reactant left after 5 half-lives. Or you can say amount of reactant left after 3.5 minutes. 3.5 minutes here is 5 half-lives. So it's going to be simply A naught divided by 2 raised power 5. Or you can say A naught divided by 32 molar. This is the concentration. This is the amount of reactant left after 5 half-lives. Okay. All clear, people? All clear with this? Right? In order to solve this question, in order to solve this question, I gave you one specific result just to solve this question. See guys, as per the question is concerned, we are given the reaction, for example, A gives B. Right? A gives B. At some time T1, which is for example 10 minutes, at time T is equal to 10 minutes, rate of the reaction is given to me as 0.04 moles liter inverse second inverse. Similarly, at time T2 equal to 20 minutes, at time 20 minutes, rate of the reaction is given to me as 0.03 moles inverse second inverse. What am I supposed to calculate? I'm supposed to calculate half-life. Half-life of the first order reaction is 0.693 divided by K, right? So my first point would be to calculate K. My first point would be to calculate K. Now, how do I calculate K? There was one expression which I gave you, if you remember. 2.303 divided by T2 minus T1, it is going to be log of R1 divided by R2. Do you remember this? Yeah. R1 we know, R2 we know, T1 we know, T2 we know. So from here you can calculate K, and once you calculate K, put it here and get the half-life of the reaction. We are done. We are sorted. Right? So I believe you can solve these sort of questions easily from now on. Similarly, look at this one. Look at this one. One more different type of question. In what time the molar ratio of ethylene to cyclobutane becomes 1? At what point of time the ratio of moles of these two becomes 1? Understand, guys, what the question says. For example, initially at time t is equal to 0, let's say we have got A moles of this reactant. So this would be 0, correct? Now what would happen? When the reaction starts, moles of reactants will keep on decreasing. Moles of products will keep on increasing. Can I say there will be a time when moles of reactants and products will become equal? there would be a time when the moles of reactants and products would become equal. There would be a time when the moles of reactants and products will become equal. And when the moles of reactants and products becomes equal, at that point of time, I'll say the ratio of the moles of reactant products will be 1. At that point of time, the ratio of the moles of reactant and product will be 1. Agreed? Moles of reactant will keep on decreasing with time. Moles of product will keep on increasing with time. There will be a time when moles of reactant product will be equal. At that point of time, I would say the ratio of the moles of reactant and product become 1. Right? I have to calculate at what time, the ratio of the moles of reactant product becomes equal to 1. Or in other words, I have to calculate at what time the moles of reactants and products would have got equal. At what time the moles of reactants products have become equal. Now understand. Initially, I start with A moles of reactants. Let's say at time t, out of A moles of reactant, let's say X moles got converted into product. So I'll be left with A minus X moles. Initially, I start with A moles. Let's assume at this time t, out of A moles of reactant, X moles got converted into product. Now, 1 mole of reactant gives 2 moles of product. So X will give 2X. Perfect. And I'm assuming that this is the time when the moles of reactants and products are becoming equal. So this is the time which I have to calculate at which the moles of reactants and products are becoming equal. So I'll simply say 3x is equal to A, or I'll say x is equal to A by 3. X is equal to A by 3. So till here I solved the question. Now guys understand. Now understand. What do I have to calculate? I have to calculate T. I have to calculate this time. Time at which their moles have got equal. The time at which the molar ratio of these two has become 1. So now if I use the integrated equation, T is equal to 2.303 divided by K log of A naught divided by AT. Right? Perfect. Now, if I use this particular condition, here, T I am writing as such is equal to 2.303 divided by K is given to me as per the equation, which is 2.3 into 10 raised power minus 4 log of A naught represents the initial concentration. Here it represents the initial moles divided by AT represents concentration of reactant left at time t. Here AT represents moles of reactant left at time t, which is A minus X. X is nothing but A by 3. So it becomes 3A minus A. 3A minus A, which comes out to be 2A by 3. So A cancels. A cancels. It becomes log of 3 by 2, which is nothing but log 3 minus log 2. Okay. So 2.3 cancel. 10 raised power minus 4 comes up. So 10 raised power 4. Log 3 is 0.47. Log 2 is 0.3. The value comes out to be 1700 seconds. It will take 1700 seconds for the moles of reactants and products to get equalized. It will take 1700 seconds for the molar ratio of reactants and products to be equal to 1. Yeah? Am I clear? Am I clear with this? Let me know once in the chats quick. Did you understand this question? If yes, then solve this basic question. This one basic simple question. You are given with a reaction whose rate constant is given. Time required for 40 grams of reactant to reduce to 10 grams will be, right? A reaction is given. Initially, what is the amount of reactant given? 40 grams. As per the question, at what time the amount of reactant left, which is represented by 80, will be equal to 10 grams. Perfect. Use simple, the integrated equation. T is equal to 2.303 divided by K. K is 2.3 into 10 raised power minus 3. Log of A naught by 80. A naught is 40. 80 is 10. So this becomes log of 4. Log of 4 is 0.6. Right? 0.6. So this term cancels. T comes out to be 0.6 multiplied by 10 raised power 3, which comes out to be approximately 600 seconds. So it will take 600 seconds for the amount of reactant to reduce from 40 grams to 10 grams. Yeah? Is this particular question clear? This should be. Similarly, you can solve this question easily. Find out the time required for two-third completion of a first order reaction. Find out the time required for the two-third completion of a first order reaction. What does it mean? You have got the reaction like this, A gives B, for example, whose rate constant K is given to me. K is equal to 4.3 into 10 raised power minus 4 second inverse, right? Now, initially, for example, the initial concentration of reactant is A naught, this is 0, right? We have to calculate the time required for two-third completion. Time required for two-third completion. What does that mean? That means time required to complete two-third completion. Two-third completion means two-third of reactant would have got converted into product. Two-third reactant would have got converted into product. So how much would be left? Initially, we start with A naught. Now, two-third of A naught is getting converted into product. So how much will be left? It will be A naught by 3. This is the amount of reactant left at two-third completion. At two-third completion, your AT. At two-third completion, your AT would be nothing but A naught by 3. Now, we use this particular condition in the integrated rate equation. And my integrated rate equation is T is equal to 2.303 divided by K. It is the log of A naught divided by AT. Now, if you use this condition here, instead of T, you will be writing this 2.303 divided by K. What is K? K is 4.3 into 10 raised power minus 4 log of A naught divided by, what is AT? AT is A naught by 3. A naught cancel. Log 3 comes up. Instead of log 3, you can write 0.47. Instead of log 3, you can write 0.47 and solve this particular expression and get the value of T two-third in seconds. So this is going to give you the time taken to complete two-third of the reaction, right? And my dear students, with this, we are done with the first order simple reactions. Now, we are going to move into the first order gaseous phase reactions. Okay, all clear till here? All clear till here? Let me know quickly in the chats if every single thing is clear. Perfect. Let's take a break for 10 minutes and be back. Okay, I'll take a break for 10 minutes and be back. But I want everyone to be here. Don't leave. Okay? I'll be back at 12:20. Okay? Let's take a short break, but be back. Okay? Don't leave or something. Or else I'll have to end the session. Perfect? It is not going to take us more than 2 to 3 hours. That's it. So be back on time. I'll be back also. All right, are you all back? Are you all back? Let me know in the chats quick. Are you all back or slept? I think a lot of people have already slept, yeah? I think a lot of people have already slept. Yes? Perfect. So we are done with the first order, right? So is everything clear till here? Let me know once in the chats quick. All the things clear, whatever things we discussed till now? Yeah? Perfect. Now let's move on to the kinetics of the gaseous first order reaction. Guys, this is also important, and from this particular topic also, questions are frequently asked. Okay? So now let's get to know what these gaseous first order reactions are all about and what about their kinetics. Let's understand this in detail. See guys, first of all, imagine that I'm taking a reaction like this. A gas, it gives B gas plus C gas. Let's say this is one general chemical equation. A gas gives B gas plus C gas, right? First of all, as you can all see, this A is in gaseous state, B is also in gaseous state, C is also in gaseous state. So it is the example of what? It is the example of homogeneous gaseous phase reaction. It is the example of homogeneous gaseous phase reaction. I'm assuming that this particular homogeneous gaseous phase reaction, it is carried out at constant volume and temperature. I'm assuming that this particular homogeneous gaseous phase reaction, it is carried out at constant volume and temperature. Perfect. Now, my dear students, you know, PV is equal to nRT. Since volume and temperature is kept constant, R is already constant, so I can say pressure is directly proportional to moles. Pressure is directly proportional to moles. If moles are decreasing, pressure will be decreasing. If moles are increasing, pressure will be increasing. Now, since you know, when the reaction proceeds, moles of reactant will keep on decreasing. Moles of reactant will keep on decreasing. And if moles of reactants are decreasing, I would say pressure of reactant would be also decreasing. Correct? If moles are decreasing, if moles of reactants are decreasing, so I would say pressure of reactants would be decreasing with time. Similarly, moles of products are increasing. Therefore, I would say pressure of products would be also increasing. So in short, one thing I would want you guys to remember here. What is that? Treat the pressure in the similar way. Treat the pressure in the similar way as we treat moles. The way we treat moles, in the similar way we are going to treat the pressure. Okay? Now tell me one thing. For example, I'm writing time t is equal to 0. At time t is equal to 0, there will be only reactant in the container. Right? Let's say this particular reaction is carried out in a container, for example. This is the container, a closed container. Now, initially at time t is equal to 0, there will be only reactant present in the container. So, I would say there will be only gas A present in the container at time t is equal to 0. Right? I'll be saying that there will be only gas A present in the container at time t is equal to 0. Right? So, whatever will be the pressure in the container at time t is equal to 0, that is due to gas A only. Let that pressure due to A at time t is equal to 0 is P naught. Right? So this is going to be 0, this is going to be 0. Right? Now people, as the reaction proceeds, moles of gas A will keep on decreasing, so pressure due to A will also decrease. So let's say at time t, pressure due to A is now P naught minus X. Let's say at time t, pressure due to A is P naught minus X. Now we use the stoichiometry. 1 mole gives 1 mole, so X will be giving X. 1 gives 1, so X gives X. Right? So if I ask you at time t, how many gases will be there in the container? I would say at time t, there will be some moles of gas A in the container, some moles of gas B would have got formed, and similarly, some moles of gas C would have got formed. So at time t, there will be a gaseous mixture present in the container. At time t, there will be a gaseous mixture present in the container. Let the total pressure of the mixture at time t is Pt. Let the total pressure of the gaseous mixture at time t is Pt. So can I say total pressure of the mixture, total pressure of the gaseous mixture at time t would be equal to the sum of the partial pressures. It's going to be P naught minus X plus X plus X, right? So X and X gets cancelled out. So Pt is nothing but, it is P naught plus X, or you can say the X over here is nothing but, that is Pt minus P naught. So this is my X. Understand the process which I'm doing. Follow the process which I'm doing. Now, my dear students, as this reaction keeps on happening, let's say I'm writing at t is equal to infinite. At t is equal to infinity. Since this is the first order reaction, and the first order reaction takes infinite time to complete. First order reaction takes infinite time to complete. Okay? First order reaction takes infinite time to complete. Now, my dear students, at time t is equal to infinity, when this reaction would have got completed, when entire reactant would have got converted into product. So can I say at t is equal to infinity, pressure due to reactant will be 0 because that entire reactant has got converted into product. Right? So what is the pressure due to be at t is equal to infinity? Say 1 gives 1 from P naught, I would have got P naught. This would be also P naught. So what is the total pressure at t is equal to infinity? Now at t is equal to infinity, how many gases you will find in the container? There will be 2 gases, B and C in the container. There will be no A in the container at t is equal to infinity. There will be only B and C in the container at infinity. Right? So P infinite, total pressure of the mixture at t is equal to infinite is going to be P naught plus P naught, which makes it 2 times P naught. So from here, you can calculate P naught, which comes out to be P infinite by 2. So P naught you calculate as P infinite by 2. Right? Now, my dear students, the first question that's asked here, what is that? Rate constant expression in terms of P naught and Pt. This will be the first question which will be asked. What is the rate constant expression in terms of P naught and Pt? Now, people, just understand. If you remember, K is equal to 2.303 divided by T, log of A naught by AT. This used to be our integrated rate equation in the first order kinetics. But here, what we'll be doing, log of A naught used to be initial concentration of reactant. A naught used to be initial concentration of reactant, right? But here, I won't be using initial concentration of reactant. Here, I'll be using initial pressure of reactant. And how much is initial pressure of reactant? That is P naught divided by what used to be AT. AT used to be called as concentration of reactant left at time t. But here AT I'll be calling as pressure of reactant left at time t. So pressure of reactant at time t is how much? P naught minus 6. Pressure of reactant at time t is nothing but P naught minus 6. Now, my dear students, we are almost done. K is equal to 2.303 divided by T. It's going to be log of P naught divided by P naught minus. What is X? X we have already calculated if you see. Pt minus P naught. X is equal to Pt minus P naught here. Now, if you finally make this expression, it will be 2.303 divided by T. It's going to be log of P naught divided by 2 times P naught minus Pt. This is the direct expression which is asked. You'll be given with a reaction like this. You will be given with a reaction like this. Okay? And you will be asked to make the expression of K in terms of P naught and Pt. Right? Right, people? Is this clear? This is the first question which will be asked. The second question which will be asked here, that will be write the rate constant expression in terms of. write K in terms of PT and P infinite. Write K in terms of PT and P infinite. My dear students, you have already made the rate constant expression in terms of P naught and PT. And what is that expression? That expression is K is equal to 2.303 divided by T, and it is log of P naught divided by 2 times P naught minus PT. But you have to write the expression in terms of PT and P infinite. Now, already we have discussed that P naught here is P infinite by 2. P naught here is P infinite by 2. So wherever you see P naught in this expression, just replace that with P infinite by 2. So K will be equal to 2.303 divided by T. It is a log of, instead of P naught, you'll be writing P infinite by 2 whole divided by 2 times. Instead of P naught, you'll be writing P infinite by 2 minus PT. So this 2 gets cancelled out. So K comes out to be equal to 2.303 divided by T log of, this is going to be P infinite divided by 2 times P infinite minus PT. So this is the expression of K in terms of PT and P infinite, which is the second type of the question that can be asked. Okay, the first question is expression of K in terms of P naught and PT. Second is expression of K in terms of P infinite and PT. But remember, these are the two expressions which you are not going to remember directly. You should be able to make these expressions. Because if I just change the stoichiometry of this reaction, entire scenario is going to change. Right? Perfect. Am I clear with this? Am I clear with this, people? Now see, if I just change the stoichiometry of the reaction, every single thing will be changed on its own. Let me change the stoichiometry and let's see what is going to happen. See guys, for example, let's say the reaction that's given to us, for example, that reaction is like this. For example, it's 2 times A gives, or let me make it a bit simple. For example, you have got the reaction like this. A gas, it gives 2 times B gas plus 3 times C gas. For example, this is the reaction. The first question is, write the expression of K in terms of P naught and PT. The second question is, write the expression of K in terms of PT and P infinite. Right? The same process we are going to follow. Understand, guys. Initially, at time t is equal to 0, pressure due to A will be P naught. This will be 0, this will be 0. Now, at time t, pressure due to A is going to be simply P naught minus x. Now, 1 gives 2, x gives 2x. Similarly, this is 3x. Similarly, at infinity, pressure due to A will be 0. Now, 1 gives 2, so from P naught, you would have got 2 times P naught. 1 gives 3, so from P naught, you would have got 3 times P naught. If I first of all ask you, what is the total pressure? What is the total pressure at time t? Total pressure of the mixture at time t will be equal to this plus this plus this. So it's P naught minus x plus 2x plus 3x. I would say PT is equal to P naught. This is plus 4x. Or I can say x will be equal to 1 by 4 PT minus P naught. This is the value of x which we got. This is the value of x which we got, right? Similarly, if I ask you what is total pressure at infinity, total pressure at t is equal to infinity is 3 times P naught plus 2 times P naught. That's 5 times P naught. So from here, you can calculate the P naught value. That will be P infinite divided by 5. That will be P infinite divided by 5. Correct? So first two things you calculate already. Now, we have to make the first question is calculate the expression of K in terms of, write K in terms of P naught and PT. I believe you should be in a position to write the expression now. K in terms of P naught and PT. How would I be writing it? I would be writing K is equal to 2.303 divided by T. It used to be log of A naught. A naught used to be initial concentration of reactant. Here I'll be using initial pressure of reactant. That is P naught. Divided by, it used to be A naught by AT. A naught by AT. AT used to be concentration of reactant left at time t. But here I'll be using pressure of reactant left at time t, which is P naught minus x. Pressure of reactant left at time t, which is P naught minus x. And my dear students, x value already we have calculated. X value already we have calculated. So it's going to be P naught divided by P naught minus, what was X? I think X was 1 by 4 PT minus P naught. Was this the value of X? X was 1 by 4 PT minus P naught, right? So if you got X, so get the final value of K here, 2.303 divided by T. It is the log of, first of all, you'll be writing P naught divided by, this is going to be 4 P naught minus PT plus P naught. 4 P naught minus PT plus P naught divided by 4, that 4 comes up. Okay, so final expression of K, I would be getting something like this, 2.303 divided by T. It is log of 4 P naught divided by 5 P naught minus PT. This is the expression of K in terms of P naught and PT. Perfect. This is the expression of K in terms of P naught and PT. Now, similarly, they can ask you the expression of K. Similarly, they can ask you the expression of K in terms of PT and P infinite. And at this particular point of time, if they ask you something like this, what do you need to do? Write the same expression again. K is equal to 0.303 divided by T log of 4 P naught divided by 5 P naught minus PT. But we already know P naught is equal to P infinite by 5. We already know P naught is equal to P infinite by 5. So replace P naught with P infinite by 5 and we are done. So K is equal to 2.303 divided by T. It's going to be log of 4 times. Instead of P naught, I'll be writing P infinite by 5 whole divided by 5 times. Instead of P naught, P infinite by 5 minus PT. So 5 got cancelled. So K comes out to be equal to 2.303 divided by T. It is the log of 4 times P infinite divided by 5 times P infinite minus PT. So this is the expression of K in terms of what? This is the expression of K in terms of P infinite and PT. So these expressions can be directly asked in your examination, and once the same expression was asked in your AIMS examination. Perfect? Right? You should be in a position to make these expressions. No matter what will be the stoichiometry, right? You just have to change the stoichiometry. I mean, no matter what will be the stoichiometry and the process which I showed you exactly, right? This is something which you are going to remember. You are just going to remember the process. You are not supposed to remember the results, right? Results will vary when you change the stoichiometry of the reaction. Okay, I believe I'm clear with this. And if I'm clear with this, then let's try to solve one question. Look at this particular question, guys. Look at this particular question. I'm given with a reaction. X gas gives 3 times Y gas plus 2 times Z gas. This is the reaction that's given to me. First of all, I need to calculate the order of the reaction. Okay. How do I get the order of the reaction? My dear students, if you remember, this is the table that's given to me. At time t is equal to 0, pressure due to X is this much. At time t is equal to 100 minutes, pressure due to X is this. At time t is equal to 200 minutes, pressure due to X is this. So first of all, check if the time interval is same. 0 to 100 is 100. 100 to 200 is again 100. So the time interval is same. Now in the same time interval, since the time interval is same, as per the question, time interval is same. Now in the same time interval, check whether these pressure of reactants are forming arithmetic progression or geometric progression. Check it out. The 400 by 800 is equal to 1 by 2. Similarly, 200 by 400 is equal to 1 by 2. So I would say in the same time interval, common ratio is same. And common ratio is same, that means, what are they forming? They are forming geometric progression. And common ratio is same. That means the pressure of X is forming geometric progression. And geometric progression is formed in case of first order reaction. So the first thing which I solved, order of the reaction is solved, order of the reaction is 1. Perfect? This is something which we have discussed long back. If in the same time interval, the concentrations or pressures or moles of reactants, if they are forming arithmetic progression, it is 0 order. If they are forming geometric progression, then it's first order. So I got the order of reaction, that's first. Okay? The order of reaction is 1. Number 1. Number 2. Let's do one thing. Let's calculate this one first. Rate constant. Let's calculate rate constant. How do I get the rate constant? K is equal to 2.303 divided by T. It is log of A naught by AT. This is how we get the rate constant. Now, we are given 3 columns. Just select 2 of the columns. Just select 2 of the columns, right? Either first and second column, or second, third, or first, third. Choice is all yours. What I'm going to do, I'm going to select this and this column, right? At time t is equal to 0, pressure due to x is 800. At time t is equal to 100, pressure due to x is 400, right? So, I'll be calling this as, or let me not write it like this, let me write it like this. K is equal to, since I'm selecting the first 2 columns, 2.303 divided by t. What is the time interval here? It's 100. It's 100. Log of A naught. A naught used to be initial concentration of reactant. Here it's going to be initial pressure of reactant. Initial pressure of reactant is how much? 800 divided by AT used to be concentration of reactant left at time t. Here it's going to be pressure of reactant left at time t. Left at time t. That's 400. So 800 by 400 is 2, right? So K I'll be getting here 2.303 divided by 100. It's going to be log of 2. Log of 2 is nothing but 0.3. Solve this and get the answer in minute inverse. So you got the rate constant here, correct? You got the rate constant. Since you got the rate constant, now calculate half-life. Half-life is nothing but 0.693 divided by K. Since K we have calculated, put the value of K here and get the half-life. After getting the half-life, we are supposed to calculate T75. T75 is nothing but 2 times the half-life. Since we have calculated half-life from here, right? So 2 times half-life will give us T75%. Okay. Now look at this question. This is nice. Total pressure when pressure due to X is 700. Write the reaction again. Reaction is X gas. It gives 3 times Y gas plus 2 times Z gas. Now initially at time t is equal to 0, what is pressure due to X? Pressure due to X is 800. So this will be 0, this will be 0. Now they are asking to calculate the total pressure when pressure due to X is 700. When pressure due to X is 700. Okay, they are asking us to calculate total pressure when pressure due to X is 700. Now, when pressure due to X is 700, how much has been the decrease in pressure? 800 minus 700. That means 100. 100 is decrease in pressure. Now, 1 gives 3. So, 100 would have given 300. 1 gives 2. 100 would have given 200. Perfect. So, what is the total pressure of the mixture right now? Total pressure of the mixture when pressure due to X is 700. So, I'll say total pressure of the mixture now will be 700 plus 300 plus 200. That comes out to be 1200 mm of Hg. This is the total pressure of the mixture when pressure due to X is 700 mm of Hg. Right? Is it clear, people? Is this particular question clear? Well, all these questions won't be asked in your examination. In the examination, they'll just give you one of these four questions. Over here, these are 4 or 5 questions which are given. But in the actual examination, they'll just give one of it. Yeah? Is it clear? Is it clear, people? Let me know once. Perfect with this? Okay, if this is perfect, then comes one more topic. That is calculation of order from half-life. This is one more important topic from which questions are frequently asked. Calculation of order from half-life. Okay? Calculation of order from half-life. See, guys. First of all, if you remember one thing, in case of your zero order reaction, if n is equal to 0, in case of your zero order reaction, your half-life is equal to A naught divided by 2K, where A naught is the initial concentration of reactant. And in case of first order reaction, your half-life is nothing but, it is 0.693 divided by K. Okay? 0.693 divided by K. This is for your zero order reaction. This is for the first order reaction. So in case of zero order reaction, half-life is directly proportional to initial concentration of reactant. Here, half-life is independent of initial concentration of reactant. In general, remember something like this. In general, remember, half-life is directly proportional to the initial concentration of reactant, which I'm representing with small a whole raised power 1 minus n. This is the general expression, where a here represents the initial concentration of reactant. A here represents initial concentration of reactant or initial pressure of reactant or initial moles of reactant. Okay, you can check it out also. In case of zero order reaction, n is 0. So half-life will be directly proportional to concentration of reactant. Half-life would be directly proportional to initial concentration of reactant. If n is 1, first order, 1 minus 1, 0. Anything is power 0, 1. So half-life is independent of the initial concentration of reactant. Similarly, if you have got the second order reaction, n is equal to 2. If n is 2, 1 minus 2 is minus 1. So this a comes to the denominator. So half-life would be inversely proportional to the initial concentration of reactant. So this is the general statement which you have to remember. Okay, this is the general statement which you have to remember. Number 1. Number 2, one more thing. For example, you have got the reaction like this, A gives B. Let's say its order is n. Perfect, its order is 1, n. Imagine that when the initial concentration of reactant was A1, the half-life of the reaction was T half 1. Similarly, when the initial concentration of the reactant was kept A2, half-life of the reaction was T half 2. This is something which I'm assuming. When the initial concentration of reactant was A1, half-life of the reaction was T half 1. When the initial concentration of reactant was A2, half-life of the reaction was T half 2. Right? Okay? This is not just initial concentration. These can be initial moles, these can be initial pressures. Right? Be careful with that. Now, let's do one thing. From this particular expression, I can make one more expression. It's going to be T half 1 divided by T half of 2 is equal to, this is going to be A1 divided by A2 whole raised power 1 minus n. From this particular expression also questions are asked. Okay, and let me tell you what is the meaning of all this. T half 1, this is the half-life of the reaction when the initial amount of reaction was A1. Initial concentration, initial pressure or initial moles. This is the half-life of the reaction when the initial moles, initial pressure or initial concentration of reactant was A2. Perfect. So these are first the two important expressions. Now, after dealing with these two important expressions, there are few more which we have to make here. See guys, if you look at this particular expression, from this particular expression, just do one thing, just remove this proportionality sign. When you remove this proportionality sign, it is going to be constant k multiplied by a raised power 1 minus n. Okay. If I multiply this equation with log, it becomes log of t half is equal to log m into n is a log m plus log of n, log of a raised power 1 minus n, which comes out to be 1 minus n log a. 1 minus n log a. Why I gave you this expression in terms of log? Because I have to make a graph here. And this particular graph, I am, for example, plotting between log of t half versus log of a. And my dear students, when you plot a graph between log t half versus log a, log t half you are plotting along y-axis. So this is your y. Log a you are plotting along x-axis. This is x. This becomes your m. This becomes your c. Sign is plus, in between equal to. Y is equal to mx plus c. Y is equal to mx plus c means straight line like this. And its slope here will be represented by m, and m is nothing but 1 minus n. Correct? So sometimes they'll give you a graph between log t half and log a. Log t half and log a. And my dear students, its slope would be given. From the slope, you should be in a position to get the order of the reaction. See, from the slope, you'll be getting the value of 1 minus n. From 1 minus n, you can calculate the value of n. Right? Perfect. And here, we can make one more expression here. We can make one more expression here. That's again important. And what is that expression? Let's have a look. See guys. In this particular equation, if you multiply this particular equation with log, it again becomes log of t half of 1 divided by t half of 2 is equal to log of this particular term. This becomes finally 1 minus n log of a1 divided by a2. Log of a1 divided by a2. Correct? So log of m by n becomes log m minus log of n is equal to, this is going to be 1 minus n and log A1 minus log A2. Log A1 minus log A2. So I can say 1 minus n is equal to log of t half 1 minus log of t half 2 divided by log of A1 minus log of A2. Or I can say n is equal to 1 minus log of t half 1 minus log of t half 2 divided by log A1 minus log A2. Sometimes this particular expression will be directly used. Okay? And from this particular expression, you can get the value of n, where n represents the order of the reaction. Okay? So all these expressions are equally important. Got it? Now see what kind of question can be framed. Look here. For example, look at this particular question. Look at this particular question. This is the table that's given to me. And the table is between concentration of reactant versus half-life. Okay? What do we have to calculate? We have to calculate order. We have to calculate order of the reaction. See guys. First of all, look at the data. When the initial concentration of reactant is 50 molar, half-life of the reaction is 4 seconds. When the initial concentration of the reactant was 100 molar, half-life of the reaction is 2 seconds. Okay? Right? So, let me just choose these two columns. Let me call this as T half 1. Let me call this as T half 2 because I'm choosing the first two columns only. So, this is going to be your A1 and this is going to be your A2. Correct? Expression already I have given you. What is that? That is T half of 1 divided by T half of 2 is nothing but it is A1 divided by A2 whole raised power 1 minus n. Okay. So T half of 1 is 4. T half of 2 is 2 is equal to A1 is 50. A2 is 100 whole raised power what? 1 minus n. We have to get the value of n where n represents order of the reaction. Now guys, see 4 by 2 is nothing but 2. 2 is equal, this will be 1 by 2 raised power 1 minus n, or I'll say 2 is equal to, this will be 2 raised power n minus 1, which tells you n minus 1 is equal to 1, or you can say the value of n here is equal to 2. Correct? Is that clear? N value is equal to 2. N value is equal to 2 means this is the order of the reaction. It is something I was supposed to calculate, right? I assumed in the beginning order of the reaction is equal to n. So this finally came out to be the order of the reaction, n, which came out to be 2. Got it? I hope this is clear. If this is clear, then you should be in a position to solve one more question as well. Look at this one. Look at this one, guys. For the reaction A gives B, calculate order. The graph is given between log T half and log A. Few minutes back only we discussed one thing. Slope of this particular graph. It used to be 1 minus n. Slope means what? Slope means tan of theta. Tan of theta. What is theta? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. If this is 45, this is 90, this is 45, so this has to be 135. So it is basically tan of 135, right? So 1 minus n is equal. Tan of 135 is minus 1. So n value here comes out to be 2, right? N value here is coming out to be 2. What is n? N represents the order of the reaction. So order of the reaction which we used to represent with n, that is nothing but 2. Done and dusted. Perfect. So this sort of a question, they can also be asked. These sort of questions can also be asked in your examination. So be careful with all of this stuff. I hope I'm clear with this. Okay. All clear, people? All clear with this? Now, before going into the Arrhenius equation and collision theory, there is one more topic that I would want to discuss with all of you. That is going to be mechanism of the reaction. Okay, that's going to be mechanism of the reaction. From mechanism, different sorts of the questions can be asked. You would have seen these sort of questions given in your notes, reference books, wherever you're studying, right? These sort of questions are given. And let me show you how do we deal with these sort of questions. Okay. Let me show you what these questions are all about. How do we deal with them? First of all, what is a mechanism? How do we define the mechanism of the reaction? It's simple. Mechanism of the reaction is nothing but it is the series of steps which are proposed to write the net reaction. Series of steps which are proposed to write the overall reaction. Okay. For example, let's say I'm writing like this. Let's say I've got the reaction A gives B, right? Let's say this reaction is, for example, in equilibrium. Let's say, perfect. Let's say I've got the reaction B gives C, perfect. Let's say one of the step is slow, one of the step is fast. Let's say this is the slow step, this is the fast step, for example, perfect. For example, if you add the two steps, BB gets cancelled. So my net reaction is going to be A gives C. So this A gives C. Is this happening in one step? No, it is happening in two steps, right? It's happening in two steps. Perfect. If it is happening in two steps, then it's going to be your complex reaction. And you know, the steps which are involved in order to write the complex reaction, they are always elementary in nature. This is elementary. This is elementary. Now, my dear students, one more thing. The series of steps which are proposed to write the overall reaction, that describes basically the mechanism of the reaction. Perfect. Now, from the mechanism, what kind of the questions are asked? First of all, in the mechanism, some of the steps will be fast, some of the steps will be slow. And the slowest step in the mechanism, that is going to decide the overall rate of the net reaction. The slowest step in the mechanism is something which you call as the rate determining step, RDS. Okay, so what is mechanism first of all? It is the series of steps of elementary reactions by which overall chemical reaction occurs. The slowest step given in the mechanism is going to decide the overall order of the reaction, right? And that slowest step is something which you'll be calling as rate determining step. Now, people, see what kind of stuff is asked and how do we deal with them. Understand. See, this is your complex reaction here. If I ask you to calculate order of this particular complex reaction, my dear students, remember one thing. In order to calculate order, what do we need to write? We need to write rate law. In order to calculate order, we always need to write rate law. Perfect. Now, we are not going to write the rate law for complex reaction. We will be writing the rate law for the slowest step. Because slowest step is the rate determining step that is going to decide the overall rate of the reaction. So whenever order of a complex reaction is to be calculated, you are going to write the rate law, but not for the complex reaction, for the slowest step involved in the mechanism. Okay? For the slowest step involved in the mechanism. One more thing. So first of all, rate law is written for what? Rate law is written for the slowest step. Rate law is written for the slowest step to calculate order of the complex reaction. Perfect. To calculate order of the complex reaction. Now, guys, comes one more point. See, when you added these two reactions, this B and B got cancelled. Remember that term which gets cancelled when you add the two reactions. Okay, that term which gets cancelled when you add the two reactions. That term should not be present in the rate law. So remember, when you write the rate law, B should be excluded. I would write B should be not included. B should be not included in the rate law. What is meant by all the stuff? Let me tell you all the stuff in the form of questions. Understand properly what I'm going to say. For example, look at this particular question. Mechanism of the reaction is given. Mechanism of the reaction is given. Step 1, step 2. Step 1 is fast, step 2 is slow. Calculate the order of the overall reaction. Calculate order of the overall reaction. Now, first of all, in order to calculate order of the overall reaction, I will have to write the rate law. But rate law will be written for the slowest step. What is my slowest step here? This is my slowest step. Write its rate law. It is going to be rate constant K, concentration of O raised power 1, concentration of O3 raised power 1. Why I did not write X and Y? Because this is elementary. And for elementary reactions, you know already, law of mass action is truly valid. Right? That's why I directly wrote 1 and 1. But if you look at this particular rate law which I mentioned over here, no doubt, I made the rate law. But if you look at this particular rate law, see, when you add these two reactions, which term gets cancelled out? OO gets cancelled out. So O should not be there in the rate law. O should not be there in the rate law. But since I wrote the rate law, but in the rate law here, O is there. In the rate law, O is there. So what do I need to do? I need to remove this O somehow. In order to remove this O, in order to remove that term which gets cancelled out when you add these two reactions, in order to remove this O from the rate law, I will be considering that reaction which is in equilibrium. Which reaction is in equilibrium? First reaction. If the first reaction is in equilibrium, write the equilibrium constant for this reaction. It is going to be, start with the products. Concentration of O2 raised power stoichiometric coefficient 1, concentration of O raised power stoichiometric coefficient 1, divided by concentration of O3 raised power stoichiometric coefficient 1. So here you can calculate O value. O will be equilibrium constant multiplied by O3 divided by O2. Okay. So since you got the value of O, now put this value of O here in this expression. When you put this value of O in the expression, what do I get? R is equal to K. Concentration of O. Concentration of O means KEQ multiplied by O3 divided by what? Divided by O2. And here you are again writing O3, which is what was there in the expression. Okay. So see, K is equal. This is constant. Write new constant K dash. O3 makes it O3 ka square. This O2, take it up. It's going to be O2 raised power minus 1. Now look at this particular rate law. Is it having O in it? It is not having O in it. That O is out of the rate law. So this is my perfect rate law now. This is my perfect rate law. Now, in this particular rate law, look at the concentration terms. Look at their powers, right? So I would say order of the reaction with respect to O3 here will be directly 2 plus order of reaction with respect to O2 here is equal to minus 1. So overall order of the reaction is going to be 1. This is the overall order of the overall reaction. Did you understand how do we get the order of the overall reaction? First of all, do one thing, write the rate law for the slowest step, right? Okay. The term which gets cancelled out when we add these two, you have to remove that term from the rate law with the help of that particular step which will be in equilibrium. Perfect. And eventually you'll be getting the rate law which is free of that term which gets cancelled when we add these two. So this rate law is free from O right now. So it's my perfect rate law. So if it is perfect rate law, so order of the reaction will be X plus Y, 2 plus minus 1, that comes out to be 1. Okay. Let me solve one more question of the similar manner so that it will be properly clear to you. Look at this particular question. Mechanism of the reaction is given, right? Mechanism of the reaction is given. What do we need to calculate? We need to calculate order of the overall reaction. Order of the overall reaction. First of all, if I add these two, which term gets cancelled out? NO3. So if NO3 is there in the rate law, it has to be removed. It has to be removed. So first of all, I will be writing the rate law. And rate law will be written for that particular step which is slowest. Which one is slowest? Second step is slowest. So write the rate law for the second step. It is K1 multiplied by concentration of NO3 raised power 1. And this is concentration of NO raised power 1. Perfect. So in this particular rate law which I made, do you see NO3 here? Yes, I can see NO3. This NO3 should not be here. We have to remove this NO3. And this NO3 I'll be removing by considering that particular step which is at equilibrium. This particular step is at equilibrium. So I'll be writing equilibrium constant for this reaction. Equilibrium constant for this reaction is going to be concentration of NO3 raised power 1 divided by, it's going to be concentration of NO raised power 1 multiplied by concentration of O2 raised power 1. So from here, I can say concentration of NO3 is equal to KEQ multiplied by concentration of NO multiplied by concentration of O2. So put this NO3 into this particular expression. What do we get here? I'll be getting R is equal to K1. What is the concentration of NO3? Concentration of NO3 is nothing but KEQ. Concentration of NO, concentration of O2, and here already we have got NO, right? So I would be writing R is equal to constant makes it new constant K dash, NO makes it NO ka square, right? And with this I'll be writing O2 as well. Now look at this rate law. It is free of what? It is free of NO3. So now it is my perfect rate law. If it is my perfect rate law, so I would say overall order of the reaction has to be equal to 2 plus this 1, right? 2 plus 1, which comes out to be 3. So overall order of the reaction is going to be, overall order of the complex reaction is going to be 3. I believe this is clear to everyone. Yeah? Is it? Is it clear, guys? Let me know in the chats. Is it clear? Is it clear? All right. Similarly, let me give you one more question. So, here in this particular question, I'm given with the mechanism and I'm supposed to calculate the order. I'm supposed to calculate order of the net reaction, order of the overall reaction. First of all, when I add these three reactions, which all terms will get cancelled out? When I add these three reactions, I plus I makes it 2I. That 2I with this 2I gets cancelled out. IH2 gets cancelled out. So there are two terms which are cancelling out. One is I and one more is IH2. So first of all, these two terms should not be included in the rate law. We need to, if these two terms are included in the rate law, I mean, if these two terms are there in the rate law, you have to remove them from the rate law. Now see how exactly. First thing which I'll be doing, let me write the rate law for the slowest step. This is the slowest step, and rate law is equal to R is equal to rate constant K, concentration of IH2 multiplied by concentration of I. Look at this rate law. In this rate law, IH2 as well as I, both are there. IH2 as well as I, both are here. So we have to remove both, I as well as IH2. Okay, I as well as IH2. Now, in order to remove these two, I'll be considering those reactions which are at equilibrium. Okay, so let me consider this reaction first. If I consider the second reaction first, if I write its equilibrium constant, is K2. Equilibrium constant is K2, which is nothing but concentration of IH2 raised power 1 divided by, this is going to be concentration of I raised power 1 multiplied by concentration of H2 raised power 1. Okay, so from this particular expression, you can say concentration of IH2 is equal to K2 multiplied by concentration of I multiplied by concentration of H2. So put the value of IH2 here in this particular expression. So R is equal to K. Instead of IH2, I'll be writing K2 multiplied by concentration of I multiplied by concentration of H2. And here is already I and I makes it I square. Okay. Look at this particular expression. Still in this expression, no doubt, we have removed IH2, but still there is I. We have to remove I as well. So in order to remove I, I'll be considering one more reaction with that equilibrium. That is the first reaction. Its equilibrium constant is K1. So K1 expression is going to be concentration of I raised power 2 divided by, it's going to be concentration of I2. So I would say I square here is going to be K1 multiplied by concentration of I2. So this I square here, if you can see. Now instead of this I square, you can write this particular term, right? Instead of I square, you can write the term. So I would say R is equal to K, K2. Instead of I square, I'll be writing K1 multiplied by I2 concentration multiplied by H2 concentration. Now see, constant. New constant, that is K dash multiplied by I2 concentration multiplied by H2 concentration. Now, if you look at this particular rate law, is this rate law now including I or IH2? This rate law is neither including I nor IH2. Perfect. So this is my perfect rate law. If this is my perfect rate law, so you can calculate order from this perfect rate law. It's going to be 1 plus 1. That comes out to be 2. So order of the overall reaction comes out to be 2. I hope this is clear to everyone. So these are the questions which can be framed from the mechanism. Okay. Perfect, guys. Right? Now there are a few more questions which can be framed. For example, mechanism of the reaction is given like this. A gives B, rate constant K1. A gives C, rate constant K2. A gives D, rate constant K3. Calculate net rate of disappearance of A. Calculate net rate of disappearance of A. See guys, how do we deal with these questions? Understand and remember them. So first of all, if you break this particular reaction into 3 parts, the first part is going to be A gives B. The second part is going to be A gives C. The third part is going to be A gives D. I've broken down this particular reaction into 3 parts. A gives B, A gives C, A gives D. Rate constant of the first one is K1. Rate constant of the second one is K2. Rate constant of the third one is K3. Okay. What do we have to calculate? Rate of disappearance of A. Net rate of disappearance of A. A is included here also, here also, here also. So I will have to consider all the 3 reactions. I'll have to consider all the 3 reactions. In the first reaction, A is the reactant. A is the reactant. If A is the reactant, if I ask you, what is the rate of reaction with respect to A? You'll start with minus 1 by stoichiometric coefficient 1 by 1, change in the concentration of A divided by dt. This is the rate of reaction with respect to A. And as per rate law, it has to be equal to, rate of the reaction has to be equal to K1, concentration of reactant raised power 1. Correct? Similarly, look at the second one. Here also, you have got A. A is the reactant. So write the rate of reaction with respect to A, minus 1 upon 1. Change in the concentration of A divided by dt. This is going to be equal to K2 multiplied by, as per rate law, concentration of A raised power stoichiometric coefficient 1. Yeah. Now look at the third reaction. Here also A is the reactant. So write the rate of reaction with respect to A. So it's minus dA upon dt is equal to, as per rate law, it's going to be K3 multiplied by concentration of A raised power stoichiometric coefficient 1. What do I have to calculate? Net rate of disappearance of A. See, net rate of disappearance of A. If you look carefully, this is giving you rate of disappearance of A. This is also giving you rate of disappearance of A. This is also giving you rate of disappearance of A. So if you want to write net rate of disappearance of A, if you want to write net rate of disappearance of A, net rate of disappearance of A will be equal. See, A is getting disappeared from here as well as from here as well as from here, right? So net rate of disappearance of A is going to be K1, concentration of A raised power 1, plus K2, concentration of A raised power 1, plus K3, concentration of A raised power 1, right? Or you can take concentration of A common. It's going to be concentration of A common. Then it's going to be K1 plus K2 plus K3. This particular term is giving us the net rate of disappearance of A. It's giving us net rate of disappearance of A. Yeah? I believe it's clear. I believe this is clear. Similarly, guys, you can get similar stuff of questions from the mechanism part, right? For example, one of the questions you'll be getting like this. One of the questions you'll be getting like this. And look at it. Look at it. 2A in equilibrium with B. Calculate rate of disappearance of A and rate of appearance of B. So what I'll be doing first of all? What we'll be doing first of all? Understand. My dear students, first of all, I'll break this reaction into parts. The first part is going to be 2A gives B, whose rate constant is K1. The second part is going to be the reverse reaction. That is B gives 2A, whose rate constant is K2. Okay, this reversible reaction I broke into 2 parts, forward and backward. Okay. Now, if you look at the first question, in the first question we are supposed to calculate rate of disappearance of A. So first of all, I'll be considering, see, A you can see here also, here also. So to calculate rate of disappearance of A, I'll be considering both these reactions. Now here A is the reactant. What will be the rate of reaction with respect to A? Minus 1 divided by stoichiometric coefficient. Change in the concentration of A divided by dt. This will be equal to, as per rate law, it has to be equal to K1 multiplied by concentration of A raised power 2. So minus dA upon dt from here is coming out to be what? It is coming out to be 2 times K1 multiplied by concentration of A ka square, right? Now here A is the product. So calculate rate with respect to A. So it's plus 1 by stoichiometric coefficient T of A divided by dt. Perfect. Now calculate the rate as per rate law. It is K2 multiplied by concentration of reactant raised power stoichiometric coefficient. So here you'll be getting d of A divided by dt is equal to 2 times K2 multiplied by concentration of B raised power 1. But do I have to calculate dA upon dt or minus d upon dt? I have to calculate minus d upon dt. Here already I got minus d upon dt. So here I'll be multiplying with minus sign. So I got minus d upon dt. So what is the net minus d upon dt? What is the net rate of disappearance of A? Net rate of disappearance of A is going to be this term plus this particular term. So it's 2 times K1 multiplied by concentration of A ka square plus this particular term, which comes out to be minus 2 times K2 multiplied by concentration of B raised power 1. Okay, perfect. So this gives me the net rate of disappearance of B here. Net rate of disappearance of A. Similarly, you can calculate this particular term on your own, I believe. Can you do that? Can you do that? Can you do this on your own? I think you should be in a position to do this. See guys, we have to calculate dB upon dt. So B is here as well as B is here. So I'll have to consider both these reactions. So look at the first reaction. Write the rate of the reaction in terms of B. It will be plus 1 upon 1 d of B upon dt. Now write the rate of same reaction as per rate law. It will be K1 multiplied by concentration of reactant raised power 2, raised power stoichiometric coefficient. Okay, so you can write it like this, or yeah, it's done. Look at the second reaction one now. Calculate rate of reaction in terms of B. So it's going to be minus dB upon dt. Minus dB upon dt. Now calculate it with respect to rate law. K2 multiplied by concentration of B raised power 1. But do I have to calculate minus dB upon dt or plus? I have to calculate plus. So I'll be multiplying this equation minus. Minus minus becomes plus and this is minus. So net rate of appearance of B will be how much? dB upon dt net will be equal this term plus this term. So it's K1 multiplied by concentration of A ka square plus this term, which is minus K2 multiplied by concentration of B raised power 1. Okay. I hope this is clear. These sort of questions you should be in a position to solve. One question over here I'm giving you as the homework. You are going to give this a try on your own. This is your homework question. This is your homework question. These are two questions basically, which I'm putting as the homework. Okay. Perfect, guys. I hope this is clear to everyone. I hope this is clear to everyone. Break for 10 minutes? Yeah? Or not? Should we take a break for 10 minutes? Let's take a break and come back, huh? Okay, let's take a break for 10 minutes and be back. But all of you should be back, huh? Okay. So 1:32 I'll start. 1:32 I'll start, but I would want everyone to be back. 1:32 I'll start. See you in a while. Yes, yes, you guys are back. I'm back too. Majority of the students have slept. Should we start then? Should we start? Should we start? Should we start? Are you here or sleeping? Are you guys here or sleeping? Right now the time is 1:34. I think you're sleeping with one eye open, huh? Sleeping with one eye open. Okay. Let's now start with the collision theory, right? Let's start with the collision theory first. After that, we'll discuss the Arrhenius equation, right? Perfect, guys. Perfect, perfect, perfect. So first of all, if I talk about the collision theory, let me tell you the collision theory, it is based on kinetic theory of gases. I believe you would have studied the KTG, kinetic theory of gases. This collision theory is completely based on what? It is based on kinetic theory of gases, right? Now, my dear students, as per KTG, if you have studied in physics, as per kinetic theory of gases, the molecules are assumed. The molecules are assumed to be hard and rigid spheres. You must have studied in KTG, the molecules, which are the reacting species basically, they are assumed to be hard and rigid spheres, right? This is the basic assumption of KTG. Now let's understand what this collision theory is all about. And so one more thing, as per your KTG is concerned, we consider the collisions to be bimolecular. As per your KTG is concerned, we consider the collisions to be bimolecular. Now we are going to discuss this collision theory in detail. See guys, what this collision theory is all about. As I told you, it's completely based on your KTG, and KTG says that the molecules are assumed to be hard and rigid spheres, right? We are going to consider the bimolecular collisions here. Now what the collision theory states. My dear students, as per collision theory is concerned, I would say for the reaction to occur, or I would say for the reaction to happen, the reacting species, they must collide first. They must collide first. This is the first point. For any reaction to happen, for any reaction to occur, reacting species, they must collide first. Reacting species have to collide first. Second point. Let me tell you, not all the collisions between the reacting species, not all the collisions between the reacting species lead to the formation of product. Leads to the product formation. Not all the collisions between the reacting species leads to the product's formation. There are only some selective collisions. There are only a few collisions between the reacting species which are going to form the colloids. Which are going to form the products. I'll write only a few collisions between the reactants only a few collisions between the reactants leads to the product formation. Leads to the product formation. And those collisions between the reactants which lead to the product formation, what do we call those collisions as? We call those collisions as the effective collisions. We call those collisions as the effective collisions. Okay. So first of all, as per your collision theory is concerned, it is completely based on your KTG. All the collisions are considered to be bimolecular here, right? As per collision theory is concerned, reacting species must collide first. Okay. Not all the collisions between the reacting species leads to the formation of products. There are only some selective, some few collisions between the reacting species which are going to form the products, and those collisions by which product is formed, you call those collisions as the effective collision, right? Now, for the collision to be effective, there are two factors. There are two factors which are going to decide. Two factors are there which are going to decide whether the collision between reactants is going to be effective or not. First factor is what we call as energy factor. And second factor is what we call as orientation factor. These are the two factors which are going to decide whether the collision between the reactants is going to be effective or not. These are the two factors which are going to decide whether due to the collision between the reactants, product is going to get formed or not. Okay, so first of all, not all the collisions lead to the formation of products. Only few collisions lead to the formation of products. You call them as the effective collision. So, by means of effective collisions, products are formed. By means of effective collisions, products are formed. Right? Not by means of all the collisions of products are formed. No, only by means of effective collisions, products are formed. Now, for the collision to be effective, two factors are going to decide. One is energy factor, one is orientation factor. Okay, these two factors, they are going to decide whether the collision between the reactants is going to be effective or not. So one by one, we'll discuss both the factors. The first factor is your energy factor. The first factor is your energy factor, right? Let's discuss energy factor in detail. My dear students, for example, let's say you have got the reaction like this. Reactants gives products. Okay. For example, this reaction is, let's say, endothermic in nature. If this reaction is endothermic in nature, that means its delta H, enthalpy change will be positive. Its enthalpy change, delta H, will be positive. Okay. Now, as per your energy factor is concerned, reacting species, they will be colliding and forming a complex, which is what you call as activated complex. And this activated complex, it finally breaks down into the products, right? Energy of this activated complex is very high. Therefore, its stability is very low. Hence, as soon as the activated complex is formed, it gets broken down into products, we can say. First of all, as per your energy factor is concerned, reacting species, they are going to collide, they are going to form the activated complex, and this activated complex further breaks down into products. First of all, energy carried by reactants, I'm representing with ER. Energy carried by products, I'm representing with EP. And energy carried by activated complex is more than that of energy of reactants as well as products. Okay. Since delta H, since reaction is endothermic in nature, so its delta H is positive. Delta H means EP minus ER. EP minus ER is positive. If EP minus ER is positive, that means EP will be greater than ER. Okay. Let me make you understand this with the help of the graph. For example, here I'm plotting energy, and here I'm plotting progress of reaction. Here I'm plotting progress of reaction. My dear students, if you look carefully, at this particular point, progress of reaction is 0. That means the reaction has not started yet. Right? Reaction has not started yet. If the reaction has not started yet, I would say in the container, there'll be only reactant. And energy carried by the reactant, I'm representing that with ER. Let's say this point represents your ER. Now your reacting species, they are colliding and forming the activated complex. Energy carried by the activated complex is more. Let's say this point represents your activated complex. And once this activated complex is formed, when it gets broken down into products, so this graph will come down. Let's say this particular point represents your products. Okay, this point represents your products. And my dear students, let me tell you one more thing. This particular point represents your energy of products, and this particular point was representing energy of reactants. Okay, I can say something like this. I can say for the reactants to form the products, can I say a reacting species must cross this energy barrier? Right? Can I say this energy barrier from here to here? I would say reacting species must cross this energy barrier to form the products. Correct? Or let me tell you one more thing. Say, for the reaction to occur as per energy factor, for the reactants to form products, I would say reacting species, they must cross this barrier over here. They must cross this energy barrier. Let me tell you, people, let me tell you, all the reacting species, they do not have the sufficient energy with them. All the reacting species, they do not have the sufficient energy to cross this barrier, right? Let me tell you, the minimum extra energy required by the reactants, the minimum extra energy required by the reactants to cross the energy barrier, or I would say to form the products, or let me directly write to cross the barrier, to cross the energy barrier is called as the activation energy. I told you not all the reactants can cross this barrier and form the products, right? The minimum energy required by the reactants to cross this barrier, right? The minimum energy required for the reactants to cross this barrier is something which we call as activation energy, right? That means this particular barrier from here to here. Perfect. This is the minimum amount of energy required by the reactants to cross the barrier, and you call this as activation energy. And since I'm right now talking about this particular reaction, forward reaction, so this is something which I'll be calling as activation energy of forward reaction. Similarly, if I talk about backward reaction, in which products gets formed, products get converted into reactants. In which products have to get converted into reactants. What should I be calling this barrier as? From here to here. This is something which I'll be calling as activation energy of backward reaction. Right? For products to get converted into reactants, I would say all the products won't be having the sufficient energy to cross this barrier and form the reactants. No. The minimum energy which is required by the products to cross this barrier, that means this energy barrier I'm talking about, the minimum energy required by the products to cross this particular barrier and form the reactants, that's something which I call as activation energy of backward reaction. Okay. So this is the graph which is valid for what? This is valid for endothermic reactions. Why is that? Because in case of endothermic, EP is greater than ER. You can see EP is greater than ER, right? This is the graph which is valid for endothermic reaction. Now, my dear students, your delta H is basically EP minus ER. EP is from here to here. ER is from here to here. This is ER, this is EP. So EP minus ER, that means this energy gap. This energy gap is something which you'll be calling as delta H. This energy gap which is something you'll be calling as delta H. Delta H is this energy gap. How do we calculate this energy gap? I would say this energy gap will be equal to EAF minus EAB. EAF minus, this is EAF, this is EAF, and this EAB. So EAF minus EAB. EAF, activation energy of forward reaction, minus activation energy of backward reaction. It's going to give you delta H of the reaction. Remember this is important from which questions are asked. Delta H is equal to EAF minus EAB. Okay, delta H is equal to EAF minus EAB. Number one. Number two, as per energy factor, when can I say the collision is effective? I would say, what is the criteria as per the energy factor for the collision to be effective? As per energy factor, what has to be the criteria? What has to be the criteria as per the energy factor for the collision to be effective? I would say for the collision to be effective, as per energy factor, for the collision to be effective as per energy factor, for the collision to be effective as per energy factor. Effective collision is the one which leads to the formation of products. For the collision to be effective as per energy factor, I would say energy of reactants should be greater or equal to the activation energy barrier. Energy of reactants should be greater or equal to this barrier, then only they can cross the barrier and form the products. Okay? Then only they can cross the barrier and form the products. So I would say this is the criteria for the effective collision as per energy factor. As per energy factor, for the reaction to happen, for the product formation, reacting species should be having the energy greater or equal to the activation energy barrier, then only they can cross the barrier and form the products, right? One more thing. The fraction of molecules which have got energy greater or equal to activation energy. The fraction of molecules which have got energy greater or equal to activation energy. So that means I'm talking about those fraction of molecules which are going to collide effectively, right? The fraction of molecules which have got energy greater or equal to activation energy is equal to e raised power minus Ea by RT. This particular term is something which you call as Boltzmann's factor. This term is what you call as Boltzmann's factor. This is what you call as Boltzmann's factor. So this is basically the term which is giving you the idea about those fraction of molecules which have got energy greater or equal to activation, which can form the products, right? Now think over one thing. More the value of this particular term, more the value of Boltzmann's factor. That means there will be more fraction of molecules which have got energy greater or equal to activation. So more fraction of molecules can cross the barrier. And if more fraction of molecules crosses the barrier, more will be the product formation. More is the product formation. I would say more is the rate of reaction. So rate of reaction and Boltzmann's factor, they are supposed to be directly proportional. Rate of reaction and Boltzmann's factor, they're supposed to be directly proportional. Okay. Over here, one more term I'm defining. That's what you call as collision frequency. Collision frequency, which I'm representing with ZAB. What this collision frequency says? Collision frequency is defined as number of collisions taking place between the reactants per unit volume, comma, per unit time. Collision frequency, which I'm representing with ZAB, it is defined as number of collisions per unit volume per unit time, right? In a unit volume, in unit time, how many collisions are happening between the reacting species, that defines the collision frequency. Now just tell me one thing. More the collision frequency. Gunjan, just wait for it. I did not teach you effect of catalyst yet. Just wait. Okay. See. More the collision frequency. That means more are the collisions happening between the reacting species. If more collisions are happening between the reacting species, that means more is the probability of effective collisions. More is the probability of effective collisions as per energy factor. And if more is the probability of effective collisions, I would say more reacting species will cross the barrier and form the products. That means more will be the rate of reaction. So rate of reaction and collision frequency, they are again going to be directly proportional to each other. Perfect. I hope you got to know the idea about the energy factor. As per your energy factor is concerned, this is the criteria. Energy of reactants should be greater or equal to activation energy, then only they can cross the barrier, and then only they can form the products. Perfect. Now, I would say These are the fraction of molecules, which will give you the idea about. These are the fraction of molecules which have got energy greater or equal to activation, which can cross the barrier, which can form the products, right? One more term I defined, that's collision frequency. So number of collisions between the reactants per unit volume, per unit time, and your rate of reaction, it is directly proportional to the collision frequency as well. Okay. Now, if you want to define the same thing for the exothermic reaction, for example, if the reaction is exothermic, how the graph will look like? In case of exothermic reactions, my dear students, in case of exothermic reaction, I would say your delta H. In case of exothermic reaction, I would say delta H is negative. What does that mean? That means EP minus ER has to be negative, which is clearly telling you that EP has to be less than ER, right? And if you make the reaction profile graph, it's going to be energy versus progress of reaction. Okay. Similarly, the graph which I made you already, similarly, I'm going to make one more graph. At this point, progress of reaction is 0. That means you'll be having only reactant with you. And this point represents energy carried by reactants, right? Reactants are going to collide and form the activate complex, which at the end will break down into products. And here products are going to come down. Perfect, because we have to represent that energy of products should be less than that of energy of reactants. Energy of products less than that of energy of reactants, because the reaction is exothermic. Now, if I talk about this particular gap from here to here, this is something which you will be calling as activation energy of forward reaction, right? And from here to here, this is something which you call as activation energy of backward reaction. Perfect. Now, EAF minus EAB. EAF minus EAB. That means which gap I'm talking about? This particular gap. This particular gap represents your delta H, which has to be always equal to EAF minus EAB. And it will come out to be negative in this particular case, right? Because EAF is less than that of EAB. And we know already in case of your exothermic reactions, delta H is negative. Or you can remember this in case of your exothermic reactions, EAB is greater than that of EAF, right? In case of what? In case of exothermic reaction. Perfect. Similarly, in case of your endothermic reactions, EAF is greater than EAB. In case of endothermic. Right? Perfect, guys. I believe this is clear till here. Right? Now, I told you for the collision to be effective, two factors are responsible for that. One is energy factor. And as per your energy factor is concerned, we got to know as per energy factor is concerned, energy of reactants should be greater or equal to activation energy. Then only they can cross the barrier and form the products. Now, orientation factor is simple. As per orientation factor is concerned, reactant species are supposed to collide with proper orientation. Reacting species are supposed to collide with proper orientation. Then only they can form the products, right? If the reacting species are colliding with improper orientation, they are not going to form the products. Okay? These are the two things which you need to remember. My dear students, for the collision to be effective, energy factor is going to decide and orientation factor is going to decide. As per energy factor, energy of reactant should be greater or equal to activation energy. As per orientation factor, the reacting species should be colliding with proper orientation. In that orientation wherein steric hindrance will be least. Now, both these factors are going to decide whether the collision is effective or not. If one factor favors and one factor does not favor, that means collision is not going to be effective. Both the factors should favor. What does that mean? That means energy of reactant should be greater or equal to activation energy. And at the same time, the reacting species, they should collide with proper orientation. Then only you can say collision is effective. Right? If one of the factors is opposing, that means collision won't be effective at all. Okay? That means collision won't be effective at all. Right, people? Now, one more thing. I told you already, rate of reaction, it depends on e raised power minus Ca by RT. Right? Rate of reaction depends on collision frequency as well. Do you see, if I want to make the equation, do you see is any term missing in this equation? See guys, this term is giving you the idea about energy factor. This term is giving you the idea about collision frequency. There is no term yet which is deciding about the orientation factor. Whereas we know orientation factor also plays the vital role to decide whether the collision is effective or not. So I'll be adding one more factor over here, which I'm representing with P, which is going to denote the orientation factor. So this P depends, this P is something which you call as orientation factor here. It represents your orientation factor here. The ZAB represents your collision frequency. Collision frequency, and this particular term, it represents your Boltzmann's factor. So this is one more equation. This one more equation with the help of which we can get the rate of the reaction. I believe this is clear to everyone. I believe this is clear to everyone. If this is clear, then this is one simple question which you should be in a position to solve. And these sort of questions are lately asked in the examination. You are given with a reaction, and as per the question, the reaction is exothermic. Okay. EAF is given, delta H is given, EAB is to calculate it. How do we do that? Simply, you already know delta H is always equal to EAF minus EAB. Delta H is always equal to EAF minus EAB. But delta H you won't be taking as 20 kilojoules since the reaction is exothermic. So sign has to be minus. This is where majority of the students do the mistake. So delta H we have to take as minus 20 kilojoules is equal to EAF is given as 30 kilojoules minus EAB. So I would say your EAB will be equal to 30 plus 20, that comes out to be 50 kilojoules, right? This is something which I was supposed to calculate. And these sort of questions are asked, frequently they are asked. Frequently they are asked, right? Remember this particular stuff. Okay? Am I clear with this? Am I clear with this, guys? Frequently, these sort of questions are asked. All right. Now, one more thing. What does a catalyst do? If you talk about effect of catalyst. If you talk about the effect of catalyst on the rate of reaction, what exactly a catalyst does? See, first of all, catalysts are basically of two types. One is called as positive catalyst. One is called as the negative catalyst. Positive catalyst and the negative catalyst, right? Positive catalyst and the negative catalyst. My dear students, if you talk about the positive catalysts are going to speed up the reaction without itself being consumed in the reaction. They are going to speed down the reaction. They are going to speed down the reaction. How come exactly? Positive catalysts are going to lower the activation energy barrier, and negative catalysts, they are going to increase. They are going to increase the activation energy barrier. They are going to increase the activation energy barrier. Now, my dear students, one more thing. If you want to have a look on the reaction profile here, you can do that. Let's say this energy, and this is, for example, your progress of reaction. Okay. For example, this is a graph which I'm making over here. This graph is made, for example, in absence of catalyst. This is in absence of catalyst. Now, in presence of catalyst, what's going to happen? In presence of catalyst, in presence of positive catalyst lowers the activation energy barrier. So, in presence of positive catalyst, this is now going to be the reaction profile, right? Activation energy barrier has decreased. This one is in presence of positive catalyst. And in presence of negative catalyst, what's going to happen? Negative catalyst increases the activation energy barrier. This is in presence of what? The negative catalyst. In presence of the negative catalyst. If I ask you, the gap from here till here, What do I call this particular gap as? Delta H. Right? What do I call this particular gap as? Delta H. Right? This particular gap is something which you call as delta H. So, does delta H change in presence of positive and negative catalyst? Does delta H change? I would say delta H is independent of catalyst. Okay? As you can see, in absence of catalyst, in presence of positive catalyst, or in presence of negative catalyst, delta H is remaining the same. So delta H has got nothing to do with the catalyst. Okay, it has got nothing to do with the catalyst. Right? I hope this particular point is clear. Now, one more important thing. In case of reversible reaction, remember this point. In case of reversible reaction, positive catalyst increases the rate of forward as well as the rate of backward reaction by equal amounts. Remember this particular point as well. When you add positive catalyst in a reversible reaction, in case of reversible reaction, rate of forward increase as well as rate of backward reaction increases. In case of reversible reaction, rate of forward as well as rate of backward increases. And rate of forward and backward increases by equal amounts. Right? That's what a positive catalyst does. Positive catalyst increase the rate of forward and the rate of backward reaction by equal amounts. Okay? Now guys, one more thing. If I ask you one more thing here. Let's say I'm giving you a question like this. For example, this is the reaction profile which I'm making over here. Energy versus progress of reaction. Okay? For example, the graph is like this. Let's say. Okay? From this particular graph, can you tell me how many steps? First of all, this particular graph is basically valid for some reaction. Right? It's valid for some reaction. In that reaction, can you tell me how many steps will be there? In that reaction, can you tell me how many steps will be there? See, this peak represents the activated complex 1. This peak represents the activated complex 2. So this has to be from here to here. Step number 1, step number 2. So number of peaks over here are going to represent the number of steps. Number of steps involved in the complex reaction. So the complex reaction whose graph is given to us. In this particular complex reaction, there will be 2 steps involved, right? 2 steps involved. Perfect. Now see, the first step has got more activation energy. Second step has got less activation energy. If first step has got more activation energy, so energy barrier in the first step is more. That means less molecules will be crossing it, right? If less molecules are crossing it, I'll tell you, if less molecules are crossing it, I'll say step number 1 is going to be the slowest step here. Right? It's going to be the rate determining step here. Step number 1, this step. Okay? Let's say this point represents A. So first of all, from A to B, then from B to C. The step A to B is going to be the rate determining step here. Remember this particular point as well. Okay? I believe this collision theory is clear to all of you. Right? Now, we shall be moving on to what? We shall be moving on to one more important thing. What is that? I feel this particular stuff is clear to everyone. Right? Okay. Now we are going to discuss the last topic of the chapter. That's going to be Arrhenius equation. Okay. This is the last topic of the chapter. That is Arrhenius equation. Perfect, guys. All ready for the Arrhenius equation? Because from this particular topic also questions are frequently asked, and many questions have been asked from this particular topic. And let's get to know this particular topic in depth, in detail. All ready for it? All ready for it? Let me know once in the chats. You're giving me the notion of you guys sleeping. Sir, is waqt. Yes. All right, let's have a look on the Arrhenius equation, which is also what you call as temperature dependence. You call this as temperature dependence of rate constant as well. Okay, understand what it's all about. My dear students, for example, imagine that I've got the reaction A gives B. This is the reaction whose rate constant is K. I'm assuming the reaction is, for example, following first order kinetics. Order of the reaction is 1. If order of the reaction is 1, and I say rate of the reaction is equal to K, concentration of A raised power 1. Okay, right? Now people, if concentration of reactant is taken as 1 molar, and I say at that point of time, your rate of reaction is equal to rate constant. And you should be knowing your rate constant of the reaction, it gives us the idea about the rate of reaction, right? Rate constant of the reaction gives us the idea about the rate of reaction. More the rate constant of the reaction, more is going to be the rate of reaction. Lesser the rate constant of the reaction, lesser is going to be the rate of the reaction. This is something which I believe you all would be knowing. Okay, this is something which we have discussed too. Now, if you remember, when I taught you the characteristics of rate constant, I told you there, rate constant of the reaction depends on temperature. Now, the point is how rate constant of the reaction exactly depends on temperature. Rate constant depends on temperature as per this equation. Rate constant of the reaction is equal to A, E raised power minus EA divided by RT. This is something which is what you call as Arrhenius equation. This is one of the forms of the Arrhenius equation. Now understand what exactly I'm going to say. First of all, this A is something which you call as free exponential factor. Free exponential factor, or sometimes you can call it as the frequency factor. Sometimes you can call it as frequency factor. Frequency factor, right? This EA denotes the activation energy of the reaction. EA denotes the activation energy of the reaction. Let me tell you, A and EA combinedly are called as the Arrhenius parameters. They are combinedly called as the Arrhenius parameters. A and EA are combinedly called as the Arrhenius parameters. Now, my dear students, understand. Let me tell you, this A over here, A, it takes into account two factors. A takes into account two factors. What all two factors this A takes into account? A takes into account the collision frequency. It takes into account collision frequency as well as the orientation factor. This A takes into account two factors. One is collision frequency, one is orientation factor. Now people, try to understand. Let's say you have got the reaction A gives B, okay, whose rate constant is K. Let's say you are increasing the temperature of this reaction. If you increase the temperature of the reaction, what will happen to the value of EA by RT? If you are increasing the temperature, that means you are increasing the denominator. If you increase the denominator, this whole term will be decreasing. If this whole term is decreasing, what will happen to minus EA by RT? If EA by RT is decreasing, that means minus EA by RT mathematically will be increasing. If minus EA by RT is increasing, so E raised power minus EA by RT. See guys, if this particular term is increasing, so E raised power, this term will be also increasing. And if this term is increasing, if you multiply this term with A, I would say A E raised power minus EA by RT. Even this term will be increasing. And if this particular term is increasing, what does that mean? That means the rate constant of the reaction will be increasing. So you can clearly say when you increase the temperature of the reaction, rate constant of the reaction, that increases. Okay? When you increase the temperature of the reaction, rate constant of the reaction, that increases. Rate constant of the reaction, that increases. Now, first of all, what is the logic behind that? What is the logic behind that? Before talking about the logic, let me tell you one more thing. On increasing the temperature of the reaction by 10 degree, rate constant of the reaction generally doubles, or even becomes more, or increasing. When you increase the temperature of the reaction by 10 degree, rate constant, or you can say rate constant of the reaction, or you can say rate of the reaction, it doubles or becomes even more than that, What is the reason for that? The reason is because on increasing the temperature, the fraction of molecules which have got energy greater or equal to activation energy, these fraction of molecules increases. On increasing the temperature, the fraction of molecules which have got energy greater or equal to activation energy, they increase. Hence, more molecules cross the barrier. Hence, more product is formed. If more product is formed, that means more will be the rate constant. Hence, more is the rate of the reaction. Remember this particular point. When you increase the temperature of the reaction by 10 degree, rate constant of the reaction generally doubles or even becomes more. Than double. Reason is because on increasing the temperature, those fraction of molecules which have got energy greater or equal to activation energy, they increase. Hence, more molecules cross the barrier and hence more product is formed. Hence, eventually, more will be the rate of the reaction. Okay? Clear with this? Now, my dear students, here I'm going to define a term that's called as temperature coefficient. I'm going to define a term called as temperature coefficient. And this temperature coefficient, I'm going to represent with N. How do we represent the temperature coefficient? It is defined as rate constant of the reaction. Rate constant of the reaction at temperature T plus 10 degree divided by rate constant of the reaction at temperature T divided by rate constant of the reaction at temperature T. Now, you know one thing. If you have got the reaction A gives B, when reaction is carried out at temperature, for example, T degree, let's say its rate constant is K. Now, the reaction is carried out temperature at T plus 10 degree. If the temperature is increased by 10 degree, rate constant generally doubles or becomes more than that. Here I am assuming rate constant is doubling. If it was K in the beginning, now for example, it's 2 times K. Okay. So if I want to calculate the value of N, N will be equal to rate constant of the reaction at temperature T plus 10, that is 2K, divided by rate constant of the reaction at temperature T, that is K. So value of N here comes out to be 2. So temperature coefficient of the reaction is coming out to be 2. So 2 is the temperature coefficient when rate constant exactly doubles on increasing the temperature by 10 degree. Now, I told you already, rate on increase the temperature by 10 degree, rate constant either doubles or becomes even more, right? So it can be 2 times K, it can be 2.1 times K, 2.2 times K, 2.3 times K. So remember, N value is always equal to, it is always greater or equal to 2, less than 3, depending on whether the rate constant is exactly doubling or increase the temperature by 10 degree or becoming more than double, right? So temperature coefficient values lies between, it is always greater or equal to 2, but less than 3. Okay? Always greater or equal to 2, less than 3. Now guys, one more important point. For example, you have got the reaction like this, A gives B. When the reaction is carried out at temperature T1, imagine that its rate of reaction is R1. Now the same reaction is carried out at temperature T2. Its rate of reaction becomes R2. Okay, its rate of reaction becomes R2. What Is there any relation which can connect all these four parameters? Yes, there is one relation. That is R2 divided by R1 is equal to temperature coefficient, which is generally 2. It can be 2.1, it can be 2.2, it can be 2.3, 2.4, right? If it is mentioned in the question, fine. If it is not mentioned in the question, then take it as 2. 2 raised power delta T divided by 10. 2 raised power delta T divided by 10. Where do I use this particular expression? For example, if a question is asked like this, let's say a question is asked. You have got the reaction A gives B. On increasing the temperature of the reaction from 10 degrees centigrade to 100 degrees centigrade. How many times rate of reaction? How many times the rate of reaction will increase? Since we know on increasing the temperature, rate of reaction increases. Now, how many times the rate of reaction is going to increase? See, you're going to follow the same concept. R2 by R1. R2 divided by R1 is going to be equal to 2 raised power delta T, change in temperature. Final minus initial, that's 90. 90 divided by 10 is 9. So I would say new rate of reaction is going to be 2 raised power 9 times earlier rate of reaction. So I would say new rate of reaction is going to be 2 raised power 9 times the earlier rate of reaction. Perfect. So remember, on increasing the temperature of the reaction from 10 degree till 100 degree, rate of the reaction increased by the factor of what? 2 raised power 9. These sort of questions are asked. Remember them. They're important. They are important, guys. Okay? They are important. One more direct conclusion I'm giving you. Direct conclusions I'm giving you, which might be asked in your examination. And after that, we'll go into the numericals as well, right? First of all, some important concepts. For example, you have got the reaction like this, A gives B. You have got one more reaction like this, C gives D. Okay? You have got two reactions, A gives B, and similarly, C gives D. Perfect. For example, let's say, just a second. All right. For example, this reaction is carried out, for example, at 0 degree. Even this reaction is, for example, carried out at 0 degree. Both the reactions are carried out at 0 degree. Okay. For example, activation energy of this reaction, let's say, just to make you understand, is, for example, 10 kilojoules. Activation energy of this reaction is, for example, 100 kilojoules. Okay. Activation energy of this reaction is, for example, 100 kilojoules. Let's say you are increasing the temperature of this reaction as well as you are increasing the temperature of this reaction. For example, you are increasing the temperature of this reaction by same amount. You are increasing the temperature of both the reactions by same units. Okay. For example, you are increasing the temperature here by 100 degree. Let's say you are also increasing the temperature by 100 degree. Right? On increase the temperature, rate constant increases. So I would say rate constant here as well as rate constant here will increase. But remember, increase in the value of rate constant for this reaction will be more than that of increase in the rate constant of this particular reaction. The point is, remember it. There's a mathematical explanation behind this. I'm skipping that part. I'm just giving you the important conclusion, which you have to remember. If you have got two reactions, right? If you are increasing the temperature of both the reactions by same units, rate constant of that reaction will increase more, whose activation energy is more. Remember this, I'm writing it in the form of conclusion. Okay? On increasing the temperature of both the reactions, by equal units, the rate constant of the reaction, the rate constant of that reaction the rate constant of that reaction increases more whose activation energy is more. Remember this particular point, this is important. Okay? If you increase the temperature of both the reactions, rate constant of that reaction will increase more, whose activation energy will be more. This is one more important conclusion which I'm giving you directly. It has got mathematical explanation as well. I'm skipping that. You have got nothing to do with that. Conclusion is important here. Okay? Similarly, guys. Similarly, one more thing. One more thing. What is that? What is that? Now we are going into the details of the mathematical expression. The first expression of K was K is equal to A e raised power minus A by RT. Okay, this is the first form of the Arrhenius equation. Well, if you multiply this equation by ln, it becomes like this. Ln of K is equal to ln of A minus EA divided by R multiplied by 1 by T. This is one of the forms of the Arrhenius equation, ln form. Similarly, there is a log form as well. Log of K is equal to log of A minus EA divided by 2.303 R multiplied by 1 by T. This is one more form of the Arrhenius equation. One more form of the Arrhenius equation. Similarly, one more, log of K2 divided by K1 is equal to EA divided by 2.303 R 1 upon T1 minus 1 upon T2. This is one more form of the Arrhenius equation. These are different forms of the Arrhenius equation from which questions are directly asked. One is the general form, second is ln form, log form, and this one more form which we derive basically, right? Okay, you just need to remember them. And after remembering them, you can plot certain graphs here. Let's say the first graph is between ln of K versus 1 by T. What do you think will be the graph between ln K and 1 by T? This is Y, this is X, this is M, this is minus, this is C. Y is equal to minus mx plus C. Minus mx plus C means straight line like this. So its slope will be equal to what? Minus EA divided by R, right? For example, I'm plotting one more graph. Let's say the graph is between log of K versus 1 by T. Log of K versus 1 by T graph, if you want to make log K versus 1 by T. Again, its Y is equal to minus mx plus C. It's a straight line. But its slope right now will be equal to minus EA divided by 2.303 R. Minus EA divided by 2.303 R. My dear students, one more thing. Since you know, when you talk about half-life and rate constant, imagine you have got a first order reaction. In case of first order reaction, half-life is equal to 0.693 by K. Half-life is equal to 0.693 by K. So half-life and rate constant, they are inversely proportional. So instead of K2 by K1, you can write log of T half 1 divided by T half 2 is equal to, this will be EA divided by 2.303 R, and this will be 1 upon T1 minus 1 upon T2. This is one more form of Arrhenius equation in terms of what? In terms of half-life. Because you know, when you particularly talk about first order reactions, in case of first order reaction, your T half is inversely proportional to rate constant, right? Your T half is inversely proportional to rate constant. Perfect. So if T half is inversely proportional to rate constant, so instead of K2 by K1, I can write T half 1 divided by T half 2. So basically, imagine when the reaction was carried out at temperature T1, half-life of the reaction was T half 1. When the same reaction is carried out at temperature T2, half-life of the reaction is T half 2. Okay, so this is one more expression which you need to know, which you need to remember, right? Which you need to remember. Now, there is one more thing which I would want to tell you over here. See guys, one equation I'm writing over here, that is ln of K2 by K1 is equal to delta H divided by 2.303 R 1 upon T1 minus 1 upon T2. This equation is something which you call as Van 't Hoff equation. This equation is something which you call as Van 't Hoff equation. And this K1, K2 here, these are not the rate constants. These are equilibrium constants. Why am I showing you this? Because over here, I have to show you some important points. For example, you have got the reaction like this. A gives B. Let's say this is a reaction which is at equilibrium. This reaction is at equilibrium. When this reaction was carried out at temperature T1, let's say its equilibrium constant was K1. When this reaction was carried out at temperature T2, its equilibrium constant was K2. Its equilibrium constant was K2. Okay? Its equilibrium constant was K2. My dear students, if you remember, few days back in chemical equilibrium, I've told you one simple thing. If you do not remember it for now. In case of endothermic reactions, equilibrium constant is directly proportional to temperature. In case of your exothermic reactions, this is something which we have recently discussed in the equilibrium chapter. In case of exothermic reactions, equilibrium constant is inversely proportional to temperature. Okay? Perfect. Equilibrium constant is inversely proportional to temperature. Now guys, one important thing. What is basically your equilibrium constant? Equilibrium constant is basically rate constant of forward reaction divided by rate constant of backward reaction. Equilibrium is basically rate constant of forward and rate constant of backward reaction. Remember one thing from now onwards. On increasing the temperature, rate constant always increases. On increasing the temperature, rate constant always increases. Be it the rate constant of forward or backward. Rate constant of forward as well as rate constant of backward reaction increases. Rate constant of forward as well as rate constant of backward reaction increases. Now, in case of endothermic reaction, when you increase the temperature, first of all, you know, equilibrium constant is equal to Kf divided by Kb, right? Now, when you increase the temperature, on increase the temperature, equilibrium constant has to increase. On increase the temperature, equilibrium constant of endothermic reaction has to increase. But at the same time, we know on increasing the temperature, Kf increases as well as Kb increases. Now, if Kf is increasing as well as Kb is increasing, and eventually Keq also has to increase. So, Keq can only increase if increase in the value of Kf will be more than that of increase in the value of Kb. I would say here, increase in the value of Kf will be more than that of increase in the value of Kb. Remember this point, it is very, very, very important. I'm writing in case of exothermic reactions. On increasing the temperature, rate constant of forward reaction increases more than that of rate constant of backward reaction. And that is the reason why equilibrium constant increases at the end. So let me show it properly here. I would say on increase in the temperature, Kf value will increase more than that of increase in the value of Kb. And eventually, the ratio comes out to be more, hence equilibrium constant increases for endothermic reactions. And now in case of exothermic reactions. In case of exothermic reactions, you know, equilibrium constant itself is equal to Kf divided by Kb. So when you increase the temperature, I know Kf increases as well as Kb increases. On increase the temperature, this increase. But when you increase the temperature, equilibrium constant has to decrease because inversely. How can equilibrium constant decrease? Since this is increasing as well as this is increasing, I would say Kb value will be increasing more than that of increase in the value of Kf. If the increase in the value of Kb is more than that of increase in the value of Kf, when increase in the value of Kb is more than that of increase in the value of Kf, then only Keq will decrease. Okay? I hope this is clear. On increase in the temperature, equilibrium constant decreases for exothermic reaction. When equilibrium constant decreases, but at the same time we know Kf increases, Kb increases. Remember, increase in the value of Kb will be more than that of increase in the value of Kf. And that is the reason why Keq decreases in case of exothermic reactions. So I'm writing it over here. On increase in the temperature, Kf increases, Kb increases. But increase in the value of Kb will be more than that of increase in the value of Kf. Right? Let me write it in the form of a statement. On increasing the temperature, Kb increases more than that of Kf. Okay, and that is the reason why Keq decreases at the end. I hope I'm clear with all this stuff. Now guys, let's exactly see what kind of questions can be framed out of this. See, the first and the basic question. Calculate the activation energy of the reaction. First in kilojoules per mole. Second in kilocalories per mole. The graph is given between log K versus 1 by T. The graph is given between log K versus 1 by T. First of all, if you look at this graph, log K versus 1 by T, its slope is always equal to, a few minutes back only we have discussed, its slope is equal to minus K upon, no, it was not minus K upon, what was it? It was minus EA upon 2.303 R. And what was slope? Slope was tan of theta, right? Slope was tan of theta. Now, theta is tan inverse minus 3. So, tan of theta will be minus 3. Tan of theta will be minus 3. So, I got to know EA is equal to 2.303 R into 3. Right? I'll be writing it like this. See, minus minus gets cancelled. So, EA will be this multiplied by this. Now, based on the value of R, we can give our final answer. So, EA has to be equal to, understand, I can write 2.303 into 3 into R. If I take R as 8.314 joules per Kelvin per mole, at that time the answer is going to be in joules. But I do not want in joules, I want in kilojoules. So I'm dividing with 1000, then only I'll be getting the activation energy in kilojoules. Now, in order to get the kilocalories, 2.303 multiplied by 3, R value I can take as 2 calories per Kelvin per mole. Units of this term right now is going to be calories. So divide with 1000. Now it's going to be in kilocalories. Perfect. So I hope you got to know how do we deal with these sort of questions over here. Okay. Similarly, guys, this is one general question which I believe you can easily solve, right? This is one general question which I believe can be easily solved. Rate constant of the reaction at this temperature are given. Calculate the activation energy. So K1, K2 is given. T1, T2, here you have to take in Kelvin. That's given. R value, 8.314. So from here you can calculate activation energy, right? One equation, one unknown. That's it. Yeah, that's it. Similarly, it is a simple question, guys, okay? What do you think about this particular question? For the reaction, activation energy is equal to 0. So you have got the hypothetical reaction for which activation energy is 0. Normally, activation energy of the reaction cannot be 0 as per your syllabus, as per your NEET syllabus, okay? Activation energy of the reaction normally cannot be 0 as per your NEET syllabus. This is something which I'm repeating, okay? Now, for the reaction whose activation energy is 0, first of all, K is equal to A, e raised power minus EA by RT. Now, if activation energy is equal to 0, so this term e raised power 0 becomes 1, so K becomes just equal to A. K becomes equal to A, right? So your rate constant becomes temperature independent for that reaction whose activation energy is 0. Now, at 200 Kelvin, rate constant is this. What will be the rate constant of the same reaction at 400? So since that reaction whose activation energy is 0, for that reaction, rate constant becomes independent of temperature. So on changing the temperature, rate constant is not going to change. Rate constant is going to remain as such. K value will be same as before. Because that particular reaction whose activation energy is 0, right? For that particular reaction, rate constant becomes temperature independent. So on changing the temperature, rate constant does not change. It's still going to remain the same. So answer is still this only. Okay? Look at this one. Look at this one. The slope of ln K versus 1 by T for a first order reaction is this. Calculate activation energy. We have recently, few minutes back only, we made a graph between ln K versus 1 by T. And if you remember, the slope of ln K versus 1 by T used to be how much? I think it used to be minus EA divided by R. And this slope is given to me as minus 5 into 10 raised power 3. So minus cancel. So I would say EA is equal to 5 into 10 raised power 3 multiplied by R. Now we have to calculate answer in kilojoules, right? Now the value of R is going to decide about that. So 5 into 10 raised power 3, R value I'll be using as 8.314 joules per Kelvin per mole. Right now this value will be in joules, but I have to get it in kilojoules. So divide with 1000, get the answer in kilojoules from here. Done? Okay. Now guys, one more thing. Look at this particular question. Which of the following correctly represents the Arrhenius equation? Which of the following correctly represents the Arrhenius equation? You know your K is equal to A e raised power minus EA by RT, right? So rate constant depends on temperature. So if I differentiate rate constant with respect to temperature, d upon dt of K is equal to, right? d upon dt of K is equal to what? Or wait, let me take the ln form because all the forms are in terms of ln. So ln form of Arrhenius is ln K is equal to ln of A minus EA divided by R multiplied 1 by T. So if I just differentiate this ln K with respect to temperature, so d upon dt of ln K will be equal to, this is the constant, its differentiation has to be 0, minus EA by R will come out, 1 by T differentiation is going to be minus 1 upon T square, minus 1 is plus, so it becomes EA divided by R, and this is going to be T square. Do you see any option like this? D upon dt of ln K is equal to EA by RT square. D upon dt of ln K is equal to EA by RT square. So I took the ln form of Arrhenius and differentiated this equation with respect to temperature and finally got the answer, which is matching with option number 2. Right? Now, one last question of the session. One last question of the session, guys. We have got two reactions. Their rate constants are given. The temperature at which K1 and K2 are equal. It's just the calculation based question. What is the temperature at which K1 and K2 will be equal? The temperature at which K1 and K2 will be equal. K1 is 10 raised power 16 e raised power minus 2000 divided by T is equal to K2 is nothing but 10 raised power 15 e raised power minus 1000 divided by T. Correct? Do the calculation. 10 raised power 15. This 10 got cancelled, so I am left with 10 is equal. This is e raised power minus 1000 by T divided by e raised power minus 2000 by T. Right? So 10 is equal to E common, it is going to be 2000 divided by T minus 1000 divided by T. These are same powers, sir. Subtract in case of division. Right? So guys, a bit of calculation now. So 10 is equal to E raised power. If I take 1 by T as common, so it's going to be 2000 by T minus 1000 by T becomes 1000 by T. Right? If I take ln on both the sides, it becomes ln of 10 is equal to ln of e raised power 1000 divided by T. Ln of 10 is nothing but 2.303. This will be simply 1000 divided by T. So T value is equal to 1000 divided by 2.303 Kelvin. Right? This is the temperature at which rate constants of both the reactions becomes equal. So my dear students, with this, your chemical kinetics is done and dusted. Okay. One topic I skipped here, by the way. One topic I skipped here. What is that? That is your parallel reaction. Okay. Parallel first order reactions. Parallel first order reactions, first of all, are not asked, right, in our NEET examination. But still, if you want to go through it, I'll just check the last year's marathon of chemical kinetics which I took. There I have taught parallel reactions for half an hour, right? You can complete that from there. But I'm telling you, parallel reactions are not asked in the NEET examination. Nowadays, not even in JEE examination. Okay? And guys, there is one more thing. Factors affecting rate of reaction. Something which you would have discussed for class 12 boards, right? These factors just you have to remember. What are the factors which on which rate of reaction depends? It depends on the nature of reactants, physical state of reactant, right? Those reactants which are in gaseous state reacts fastly than the ones which are in liquid, than the ones which are in solid, right? Perfect. I believe this is something which you all would be knowing. Similarly, second factor is physical state, right? More the surface area of the reactants exposed, more will be the interactions between reactant molecules, hence more is the rate of reaction. Okay, this is something which you get in boards examination. The third one is chemical nature. For different reacting species, number of bonds broken and their energies are different, which eventually is going to decide about the rate of the reaction. Therefore, requirement of activation energy is also different. New reactions having less value of activation energy will take place at faster rate, right? All this is completely theoretical. And again, I'm repeating the same thing. This is something which is not asked in your NEET examination. This is something which is asked in boards, right? Concentration of reactant. You know, when you write the rate law, rate of the reaction is directly proportional to concentration of reactant, right? So rate of reaction is directly proportional to concentration of reactant, except in case of zero order, right? So on increase in the concentration of reactant, rate of reaction increases. So directly proportional. Similarly, rate of reaction is directly proportional to pressure as well, right? For pressure as well, because you know rate of reaction is actually is directly proportional to active mass of reactant. If the reactant is gaseous state, so active mass at that time will be pressure, right? So rate of reaction is directly proportional to pressure of the reactant, right? You can explain it this way, or you can simply say rate of reaction increase on increasing pressure, because on increasing the pressure, effective collisions increase. You can say in that manner as well. You can say in that manner as well. Perfect. And catalyst, a positive catalyst increase the rate of reaction, negative catalyst decrease the rate of reaction. So if I summarize this, rate of reaction depends on nature of reactants, number one. Number two, surface area of the reactants, directly proportional. Concentration of reactants, directly proportional, right? Rate of reaction depends on temperature, right? On increase in the temperature, rate of reaction increases. Perfect. Rate of reaction depends on the concentration, directly proportional. Rate of reaction depends on the pressure, directly proportional, right? So these are the factors on which basically the rate of reaction depends on. Perfect. So that's it for today. I mean, with this, your chemical kinetics is also done and dusted. Okay, so all these topics we have covered except this one, parallel first order reaction. I'm telling you, this is not asked in your NEET examination, but still, if you want to go through it, check my last year's marathon. Therein, I have taught this for half an hour. That will be more than sufficient for you. Okay, all the other stuff is done. So your chemical kinetics again done and dusted. This is something which I would want in the comment section of this particular video. Okay. Yes, just solve like 100 to 150 questions after every chapter. You're done. Hello guys. I'm going to take a leave with this. Do let me know in the comment section also which chapter do you want the next. Okay. Do let me in the comment section of this particular video which chapter do you want the next. Right?